है, बाल लंबे हैं।
छोड़ अभी टाइम से हाई टाइम, क्योंकि पता है क्या ना, मैं खुद ही इसको दबा दूँगी ना, वो आगे चली जाएगी।
ट्राई कीजिए, लेकिन इसमें करना पीरियड में
आप करो।
थोड़ा सा बदल रख लीजिए। स्लाइड सब बंद करना है। डिस्प्ले हो रहा है सब कुछ।
ये जो है
इसका
मिनिस्टर है डॉक्टर है,
कौन बोल रहा है?
गायनेकोलॉजिस्ट है
तो डॉक्टर का नहीं इसे इसमें ऊपर इधर दिख रहा है पीछे।
पीपीटी में सर एसईमेल केवल निकाल देते हैं दोनों।
पीपीटी निकालो, हटा दो,
1 मिनट के हटा दो।
ये मिस्टर है ना, ये डॉक्टर है।
सर पीपीटी में डॉक्टर ही है।
डॉक्टर किया मिस्टर
ये
डॉक्टर
दूसरी पेन ड्राइव है कि डिस्टर्ब करती है, इसके साथ लगती है। सर अभी तो नहीं दिख रही कुछ। सर ये है ना हमारे पास। वेट इसको ठीक है। अब लगा ये है डॉक्टर खाने सब, इसका नहीं डॉक्टर ने लगाया था। ये हो गया ठीक है। एक पेन ड्राइव है ना उसके लिए ना, मेरे पास एक है, मैं लेते आऊँगा अगर चाहिए होगा तो। इसको फुल कर दीजिए। इसको रखना।
Good morning and very warm welcome to esteemed dignitaries, respected faculty members and all the participants. I am Shivani Rastogi and it is an immense honor to welcome you all to the inaugural session of Synchrotron X-ray User Outreach Workshop under DST India-DESY Germany collaboration. This workshop is jointly organized by IIT BHU Varanasi and JNCSR Bengaluru with the support of Nano and Advanced Materials Division DST. Today, we are gathered here to discuss and share knowledge about synchrotron research, a cutting-edge area that holds immense potential in various fields. This workshop offers a unique opportunity for knowledge sharing and collaboration, aiming to strengthen the impact of synchrotron facility in India. Now we shall commence our program by calling the dignitaries to the dais. Please join me in welcoming our chief guest, Honorable Dr. Subhash Sarkar, former Union Minister for Education, Government of India. Professor Amit Patra, Director IIT BHU. Professor G.U. Kulkarni, President JNCSR. Professor Kanishk Biswas, Principal Coordinator India-DESY Project. And Professor Sanjay Singh, Convener IIT BHU. Professor Chandan Upadhyay, Coordinator SMSD IIT BHU. Please have a seat. Next, we have auspicious lamp lighting ceremony and a floral tribute to Mahamana Pandit Madan Mohan Malviya ji. I kindly invite all the dignitaries to proceed with the lamp lighting and the tribute. Let us now proceed with the Kulgeet of BHU, which reflects the rich cultural and academic heritage of this prestigious institution. For this, I request Ms. Aishwarya and Mr. Malhar from SMST to join the stage.
मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी मधुर मनोहर अतीव सुंदर सर्ववेद्या की राजधानी राजधानी
ये तीनों लोकों से न्यारी काशी, सुज्ञान धर्म और सत्य राशि, बसी है गंगा के रम्य तट पर, ये सर्ववेद्या की राजधानी राजधानी।
मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी। नए नहीं है ये ईंट पत्थर, है विश्वकर्मा का कार्य सुंदर, रचे है विद्या के भव्य मंदिर, ये सर्वसृष्टि की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी।
यहाँ की है ये पवित्र शिक्षा कि सत्य पहले फिर आत्मरक्षा, बिके हरिश्चंद्र थे यहीं पर, ये सत्य शिक्षा की राजधानी राजधानी।
मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी। यह वेद ईश्वर की सत्यवाणी, बने जिन्हें पढ़ के ब्रह्म ज्ञानी, थे व्यास जी ने रचे यहीं पर, ये ब्रह्म वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी।
ये मुक्ति पद को दिलाने वाले, सुधर्म पथ पर चलाने वाले, यही फले फूले बुद्ध शंकर, ये राज ऋषियों की राजधानी राजधानी।
मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी। सुरम्य धाराएं वरुणासी, नहाए जिनमें कबीर तुलसी, भला हो कविता का क्यों ना कर, ये बाग वेद्या की राजधानी राजधानी। मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी।
विविध कला अर्थ शास्त्र गायन, गणित खनिज औषधि रसायन, प्रतीचि प्राची का मेल सुंदर, ये विश्ववेद्या की राजधानी राजधानी।
मधुर मनोहर अतीव सुंदर ये सर्ववेद्या की राजधानी राजधानी। ये मालवीय जी की देशभक्ति, ये उनका साहस, ये उनकी शक्ति प्रकट हुई है नवीन होकर, ये कर्मवीरों की राजधानी, राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व विद्या की राजधानी, राजधानी। मधुर मनोहर अतीव सुंदर, ये सर्व विद्या की राजधानी, राजधानी।
We now move to the felicitation of our distinguished dignitaries. I request Professor Amit Patra to felicitate our chief guest, Dr. Subhash Sarkar. Next, I request Professor Kanishk Biswas to felicitate Professor Amit Patra. Now I request Professor Sanjay Singh to felicitate Professor G.U. Kulkarni. Now I request Professor Akhilesh Kumar Singh to felicitate Professor Kanishk Biswas. Now I request Mr. A.N. Jayachandra from GNCSR to felicitate Professor Sanjay Singh. Now I request Professor Kanishk Biswas to felicitate Professor Chandan Upadhyay. Now I request Professor Nikhil Kumar to felicitate Dr. Poonam Yadav from DST. Now I request Professor Chandana Rath to felicitate Professor Dinakar Kanjilal, former Director, IUAC Delhi. Now, I would like to invite Dr. Sanjay Singh and Professor Kanishk Biswas for the welcome address.
Good morning to all. So, I and Professor Kanishka Biswas from JNCSR, as convener of this workshop, welcome you all and welcome to our esteemed dignitaries on dais, off dais, and respected faculty members from the institute, deans, and faculty member and participants. So, I am pleased to extend a warm welcome to all of you to this Synchrotron X-ray user workshop. This workshop is a key initiative of NAMD Division of Department of Science and Technology, and we are organizing it through DST and jointly with JNCSR and IIT BHU. And this workshop is aimed to facilitate basically Indian researchers and scientists to get introduced to the global synchrotron facilities, and where we have collaboration as well from India side. And we are deeply honored to have, so Professor Kanishka Biswas will give more about this. We are deeply honored to have distinguished guests with us today. So our chief guest, Honorable Dr. Subhash Sarkar, former Union Minister for Education, Government of India. So he is well-known face in Indian politics, and he served as constituency from 2019 to 24. He has also held the position of Union Minister of State in Ministry of Education and playing a significant role in shaping India's current educational policies and initiatives. So then we have Professor Amit Patra, our director, sir, from IIT BHU, and then we have Professor G.U. Kulkarni, President JNCSR Bengaluru. We have Professor Kanishka Biswas, who is principal coordinator of this India-DESY collaboration project. Then we have Professor Chandan Upadhyay, coordinator of our School of Material Science and Technology, IIT BHU. Then we have Dr. Kanji Lal, who was former director and IOC Ayuka Delhi. And then we have Dr. Poonam Yadav from Department of Science and Technology here. So I welcome you all, and I invite Professor Kanishka Biswas to take further.
Thank you, Sanjay. First of all, I would like to thank IIT BHU for hosting this workshop, especially Professor Patra. So, on behalf of organizer, I welcome especially the students who are the next generation leader and new users. So, the main aim of this workshop is to create new users in this country, because we have around 1,000 users in this India-DESY program. So we wanted to create more and more users so that India-German collaboration through this program become much more effective. With the and this I think Dr. Poonam Yadav will tell more about this collaboration in the meantime. So I wanted to mention, like when we floated basically the advertisement of this workshop, so we have around 700 applications from different parts of India. So local organizing committee has a very hard time to select students. So we selected around 100 students. Around like 17 to 18 states. Yes. So it's if we plot in a map, it is everywhere. Like it's Synchrotron users. We wanted to see that. With that, I asked Dr. Poonam Yadav to give the message of DST Secretary. Poonam.
Good morning, everyone, and thank you, IIT BHU and Patra sir, for hosting this workshop at BHU. Secretary sir could not be here for the event, and he have sent a message to all the participants as well as the organizers. So I'll read out the message. It is a great matter of pride that the national program funded by National Nanoscience Division of DST for utilization of synchrotron facility at Petra-DESY, Germany, coordinated by JNCSR, have been very successful in facilitating many researchers across India to carry out synchrotron experiments. Access to DESY synchrotron is dispensable for advancing high-impact research in frontier disciplines such as quantum materials, semiconductors, nanotechnology, health sciences, environment science, and advanced material research. The India-DESY collaboration is a strategic initiative designed by significantly enhance access to one of the world's most advanced synchrotron X-ray sources for Indian scientists. Petra 3 offers a plethora of possibilities classified into three major categories: diffraction, scattering, spectroscopy, and imaging. These facilities allow scientists to explore complex atomic and molecular structures with unprecedented precision, enabling groundbreaking advancements in areas such as energy conversion, storage, semiconductor technologies, drug development, catalysis relevant to clean environment as well as healthcare. From the preceding two phases, more than 1,000 users have leveraged the DESY facilities, and it is heartening to note that many good publications have come out of the experiments carried out at Petra. Also, there has been a significant increase in the number of submitted proposals by the Indian users to these beamlines and a continuous expansion in the number of participating institutions. In order to encourage participation, DST has extended the project to phase 2 for a period of 2 years. DST desires that this extension and workshop of this nature would enable new and more users to access synchrotron facilities, supporting their professional growth and development. Workshops of these kind are organized with an aim to spread the message to all the researchers in the country, particularly to those from teaching fraternity from remote universities. As listed in the program, many experts from various institutions in the country are delivering lectures and sharing their knowledge on important aspects of synchrotron facility at DESY. My best wishes to the organizers for arranging the workshop, and I am sure that the event will contribute to the national goal of creating expert human resource in sophisticated experimentation, which should facilitate addressing complex scientific challenges faced in the area of advanced material, nanotechnology, and life sciences. This was a message of Secretary DST for the organizers as well as the participants. We look forward to a wonderful workshop ahead. Thank you.
We thank Abhay sir and Poonam ma'am for the message, and we also thank Professor Singh and Professor Biswas for your warm welcome. Now I request Professor Amit Patra, Director IIT BHU, to deliver the opening remarks.
Guten Morgen, meine Damen und Herren. Actually, I was thinking that there will be a lot of German friends, so I practiced my first line in German, which says, "Good morning, my ladies and gentlemen." So, of course, now I come to know that this one is particularly for the Indian side of participants in this program. No matter, so we are all very much welcome to the IIT and the IIT BHU combined campus, and I am very happy, we are all very happy to have Dr. Subhash Sarkar, former Minister of State for Education, Union Government of India, as a chief guest on this occasion. And this actually, you can say it is a kind of providential, as he was passing by and we could just get him in time, and I think he will be just enough for continuing this program. And all others seated on the days, all the faculty members, deans and students, and all the participants from the outside. Once again, a warm welcome to all of you. And we have a very pleasant weather now. In Kashi, the winter is also harsh and summer is harsher. So this is a very perfect time for visiting Kashi. Of course, I am actually not equally beneficiary of this weather, in the sense that I have to travel between Kharagpur and BHU because on additional charge of Kharagpur. So I'm keeping on traveling, and then that has given a little bit of throat problems for me. So kindly excuse that. So IIT BHU, it was built along with 3 years after BHU started. BHU started in 1916, and 3 years later, the engineering college, Benko, Banaras Engineering College started, and then it had grown into, it has started other departments, and in 1968, these all combined into one unit called ITBHU, Institute of Technology, Banaras Hindu University. Until 2012, it continued as ITBHU and taking its undergraduate students from the joint entrance examination, which was done by all IITs. So it was felt appropriate that at that time, when second generation of IITs were coming up, the ITBHU was converted to IITBHU. In that sense, we are very lucky that we have a 100-year-old legacy, and about 12 years of recent past, where there has been enormous effort to convert the old ITBHU to an IIT, which is, where, we have the sort of the game gets changed. In an IIT, the targets that we set are different from that of a university. While in university, teaching is supreme, and of course, people can do research, especially fundamental research. In IITs, the target is to, create future generation leaders who will be either be researchers or entrepreneurs, or becoming even great academicians. So there the expected targets for these IITs is kept a little bit higher, and of course time will tell how much we can deliver. But IIT BHU is on its way to a great future, with the number of students now reaching almost 9,000, faculty strength crossing 360, and equal number of staff, and a lot of academic programs with 11 engineering programs, 3 science programs, architecture program, the humanistic program, which is yet to have its own flagship program, but we have a department. So we have all these departments, and then we have a lot of facilities, including a central research facility and precision engineering hub, and we are also a center for DRDO, Center of Excellence in Industry, Academia, and DRDO interface. So we have a lot of activity in that area, and going forward, we are planning few initiatives, particularly in electric mobility, hydrogen energy, healthcare, and in some of them we are also partnering with BHU, especially in the area of healthcare. And in future, we also have plans to collaborate with BHU in the area of agriculture and come up with a plan for an agrotech business park around this area, so that this region can benefit. So those are some of our targets. I think they are pretty lofty, and we hope that we'll be able to succeed in some of them. And this type of workshops are very much welcome, where we have the interchange of ideas between our faculty and the other faculty and scientists from other places, and that is how we learn from each other. And that's one more thing that we are giving a lot of emphasis to collaboration. And what we believe is that if we really want to do something big, we need to have teamwork and collaborations within the institutions, between the institution and outside, as well as outside the country, which is an example of that is happening in this workshop. We are going to discuss that, and so I think collectively we can look for a greater vision, greater future. Thank you very much.
Thank you, Professor Patra, for your insightful opening remarks. It is now a privilege to invite Professor Jeev Kulkarni, President JNCSR, to enlighten us about the India-DESY project.
Good morning. Honorable Dr. Subhash Sarkarji, former Union Minister of State, Ministry of Education, Government of India, Professor Amit Patra, Director, IIT BHU, Professor Dinkar Kanjilal, Chairman of the Proposal Review Committee, Dr. Poonam Yadav from DST, Professor Sanjay Singh, Professor Chandan Upadhyay, Professor Kanishka, and other organizing committee members at IIT BHU, distinguished speakers, prime users of DESY facility. I see Professor Chandrabas here, Professor Kalabaran Maiti just joined, Dr. Pranay is here. They're all prime users and also speakers for the workshop, and student participants. On behalf of JNCSR, the host institution for carrying out this activity, I welcome you all to this workshop. I must give a little background. On behalf of Department of Science and Technology, Government of India, we have been coordinating a couple of programs. This is one among them. We have a program at Tsukuba, KEK's Synchrotron, that's going very well, but primarily focused on powder diffraction. Okay, so India, our scientists have set up what is required at the beam line. Japanese scientists are providing powerful X-ray, and a lot of Indian scientists are going and making use of that. The other example is what we are taking up today. This is the DESY Synchrotron near Hamburg. And we also have an understanding with UK in terms of using their neutron and muon facility at Oxford. So these are the programs we are coordinating on behalf of DST. And it's such a pleasant activity. It brings in a lot of networking, and we get to know a lot of our scientist friends across the country. And such a wonderful activity. So at the outset, I must thank DST for extending the project term of DESY. In fact, I recall, I don't know, maybe 10 years ago, Professor Chandrabas was also involved. That during that time, under the Nano Mission, the chairman, Professor C.N.R. Rao, joined by Professor Ajay Sood, who is now the PSA, they actually worked out these arrangements with the DST. And now DESY program has entered its second phase. So we should be grateful to DST for all the effort they have put in. In fact, it was taken to a very high level committee, and just a month ago, signatures happened in Delhi. The German team had arrived here. So we now have an extended term for this particular program, and that should be facilitating many researchers across the country. And DST Secretary Professor Karandikar was very keen that it should not be just around the R&D institutions, like Indian Institute of Science or TIFR or JNC. This particular program should penetrate across the country. There should be good outreach activity to do that. So we took upon us to do an outreach program at Guwahati, IIT Guwahati hosted. That was with the RAL of UK. And this is probably the second one. We have done a couple of them in the past, but not really going out and doing. In fact, DST secretary pulled us out, and which is a good thing actually. We are very happy to be on the BHU campus today, so that we are sort of able to cover mid-India region this time. And the numbers now, 1,000 users. In fact, it's going to go up. I'm also coordinating writing a DPR for Government of India for advanced materials. In fact, access to sophisticated facilities across the globe is one important component in that. So we hope these numbers will be going up. Instead of 1,000, we'll get to get 10,000. For this country, for this size, we need bigger numbers. So 1,000 is nothing actually. So we need typically 10,000, 15,000 users across India doing various things, because these synchrotrons offer very powerful beam lines. Because of the presence of very powerful beam lines, we tend to have a lot of different facilities under one roof. Okay, be it absorption experiments, scattering experiments, imaging experiments, so on and so forth. So world expertise would be there under one roof. I'm talking to the young participants here. So, you will get to know through this workshop what these synchrotrons are capable of. In fact, they can do tremendous job, and the Indian community should make use of. And eventually, actually, also go with this, second synchrotron. We have one in Indore. Professor Kanjilal knows it very well. He has been also the root cause of that synchrotron. We should really go for much more powerful, the new generation synchrotron in India. Whatever it takes, the government should do that. And essentially, I have said everything what I have to say, except that I must be specifically thanking Dr. Mohanty, the head of the division there in DST, and particularly Dr. Poonam, who is here with us, who single-handedly moved all the papers for us. And now, fortunately or unfortunately, she has moved out of the division, and Dr. Ramya will be taking care of this activity. We welcome her. We have a steering committee. We have a review committee. Steering committee chairman is Professor Milan Sanyal, who is joined by Professor D.D. Sharma, Professor Priloskar, and Professor Yusuf from BRC, and so on. So many people who are helping us with this activity. JNC is only doing the project administration, but we have National Steering Committee, National Review Committee, assisted by Mr. Jayachandra, who is our coordinator, who is taking forward these activities. One important development is there. We are using currently what is known as Petra 3. Okay, so it is going to move into now Petra 4. So it is again yet another, much more sophisticated facility which DESY is going to put up, and we have pitched in actually. DST has given the expression of interest to go with DESY even with the Petra 4 project. So that is very heartening to note. So with these words, I'll close here and wish you all a wonderful time and fruitful deliberations. Thank you.
Thank you, Professor Kulkarni, for sharing the valuable details about the India-DESY project. Next, we are honored to invite Professor Dinakar Kanjilal, former Director IUAC Delhi, to enlighten us with a few words on synchrotron experiments for India.
Good morning, Honorable Dr. Subhash Sarkar, Professor Amit Patra, Professor U.G. Kulkarni, Professor Sanjay Singh, Professor Chandan Upadhyay, Dr. Poonam Yadav, Professor Kalbaran Maiti, Professor Chandrabas, and other dignitaries, and students and faculty members. So, beauty of synchrotron, particularly electron synchrotrons. Synchrotrons are of different types. Synchrotrons are there, offshoots of cyclotrons, as you know, in accelerator physics-wise. Largest synchrotron being CERN synchrotron, but that is ion beam synchrotron. But this this conference is connected to electron synchrotron, and products are photons. So the X-rays, using the fundamental principle of physics. This beauty of this X-rays, unlike the X-ray we are accustomed to, putting high energy electron beam on cathode, a particular characteristic X-ray comes that is limited to that beam, that particular energy and particular emittance, all those billions. That is very limited. We have been using, and it has done wonder from medical science to science, physics, industry, everywhere. These are special X-rays. These are special photons. Beauty of that, billions is tremendous, sometimes million times higher, particularly free electron laser based these photons. Billions is even more than million times higher. Another beauty is that it is having time structure up to femtoseconds, so you can see dynamics of materials. And third beauty is that experiments is done far away from the source. So you can choose the environment. It can be done tremendous high pressure, the materials, like geologically important materials and formation of earths and all those things, issues are in the mantle of the earth, and exotic states of materials under tremendous pressure. Those can be done. Even environment, you can put for biological research, environment is important, so you can create a local environment, get the beam, and do it. So, and then experiments are many, they will be described also in a series of talks are there. But these are the beauty. And we look forward from Indian perspective. India beauty is that we have scientists of all types and doing research and on top places, but supported nowadays quite good support from the government, from this scientific community. We are using all kind of mega sciences. And if you look at the site of PSA, you'll find vision, mega science vision, these notes for 2035. We want to achieve those. And already 3 are there, other 3 are coming up. This accelerator synchrotron to basis is there, and details about that utilizations. And detailed structure, I hope it will be funded soon, fully, but process is going to positive direction. And these visions we go through in the country every 10 to 15 years line. And I am coming from the lab which came from vision, having the ion accelerator, this peloton, so-called tandem accelerator it is called. And that point of time in 80s, it was state-of-the-art accelerator, and we have one of the 5 largest accelerators in the series in the country. And we started with about 10 users. Now there are hundreds of users, and many hundreds of PhDs come out of it and serving, doing science everywhere, all over the world, and in the country also. So when we took it up, I have been in the field for 4 decades. It was an imagination, but in reality it happened. The India things happens. If it is taken up, whether it is space, it is nuclear devices, whatever. We went through tremendous sanction period. All kind of technology denial, even visa denial. We have a plenary talk. Last month we were refused to get the visa. All kind of things we went through, but we went through it. And things reversed over time, but things happened when things are planned. So particularly I am looking forward to the younger generation, PhD students, postdocs, young faculties, and you have a very bright future. Only one advice from my so many years of this involvement, when you talk to top scientists, even Nobel laureates all over the world, we are not much lower in our thinking, in our brain capability. Support systems are coming up, Indian economy is flourishing, so hopefully we'll be on the top. But we are not far behind if you look scientifically, even in Higgs boson or big fundamental science, even gravitational wave. If you count from top 20, there will be Indians. But anyway, Nobel Prize is given to 3. Sometimes we could not make it, but we are there. Our presence is there everywhere, all over the world. So that is the beauty of it. So when you go, you don't get surprised seeing something. Don't see the photo session or photograph. See behind it. See inside it. See how they have done it. And pick it up. Come back. Do it here. Even experiments where you put, don't think they can do it, we cannot do it. There are a lot of money invested. Even immediately after Second World War, if you see the sun, the scientists and politicians at that time, they sat together. If you see the bare land where this world's largest experimental facility grew, and even World Wide Web, all those things came from there, you will see that they work together. Any catastrophe, anything, scientists, academicians, and politicians work for future. What has happened, go future. So we look forward it. You people will help the country to build up this future accelerator, synchrotron, free electron lasers, and develop the facilities, experimental facilities. And we will collaborate. There will be two-way movement in future. In our accelerator, for ion beam, people are coming from abroad, putting their proposals and using the facility. So it will happen in photon field. Thank you.
Thank you, Professor Kanjilal, for your insightful talk. Next, we invite Dr. Poonam Yadav, scientist DST, to share her thoughts on DST support for synchrotron research.
Greetings from DST. So I must start with thanking the organizers, JNCA and IIT BHU, and especially Director IIT BHU. Thank you so much, sir, for hosting us. So these workshops had been having, we have been organizing them in the past, but in the recent review meeting of the Synchrotron, Secretary DST had observation and suggestion that we should host this time in this part of country. So we could not think anything better place than IIT BHU. And I am thankful to Dr. Sanjay and his team for having this on such a time when Mahakumbh is going on and everything. So we decided on many things, but finally we are here, and I'm thankful to everyone around. And thank you so much, sir, for coming and reviewing this particular part of science. Thank you, sir. So I think Professor Kulkarni and Kanjilal sir said everything I had to say. But the first thing I want to point out to the young users and potential users. So these workshops are always intent to attract new users towards these facilities. So if you can see the display, we have displayed 2 of the recent articles. These are in Current Science. So me and Kanishka have wrote one of these, and the other one is on RAL UK collaborative project. So we just want to percolate this information to as as much as possible to not only restricted to IISc as sir said. So please go through the DST and other government websites as and when possible. So all the information are always updated there. And when you read the articles, please go to the Current Science and other magazines, because generally we as the government departments publish in Current Science, and because these are not the science, these are the informative science articles. So about this particular project, so I am very happy and pleased to inform all of you that we have been able to facilitate 373 research from across 60 institutions, and we have more than 400 publications out of these experiments. The other thing which we are very, maybe proud of telling here is, on average, Indian users using 5 days of Beamline are able to publish one paper, which is global standard. So we are not just availing using these facilities, we are competing globally, and I must thank Kanishka for this. And the second, I want to point out the areas which we as the Department of Science and Technology largely bifurcate Petra to be used on are nanomaterials, energy materials, material for clean environment, quantum materials, and semiconductors. With the National Quantum Mission and Semiconductor Mission coming up in a huge way, so this is going to be another edge to the researchers, because already people are exposed to using these facilities. The other thing I want to again share very happily is that Department of Science and Technology have given extension for 2 years after the completion of this particular tenure of this project in September 19, and it was done in the presence of German Federal Minister and our SNT Minister, and it was again supported by 52 crores, which is over and above the sanction cost. It don't happen very easily in DST. So this is one of a kind, and this shows the importance of this program with the Government of India. And I must add here that we are all 3 synchrotrons, we are available for the users. We had our own mission as DST used to be to give access to large fraction of the beam time to the new users. So we were able to create more than 3 times new users in the area of material science for all these efforts. This I am talking about last 8 to 10 years. These are not efforts of 2 years or 3 years. It has been a long exercise. So now we have more than, as everybody said, more than 1,000 users and more than 700 publications, which have good impact factor, and some few of the publications have been published in Nature also. So now we have a good, I should say, spread across the country, sir. So we have 165 institutions participating in all these 3 projects, and we look forward to, and the workshop of these kinds are intended to ignite new minds, new MSc, PhD students and young faculty to design their research around these facilities. So I look forward to a wonderful workshop ahead, and thank you again to all the organizers. Thank you so much.
Thank you, ma'am, for this informative talk. It is now a privilege to invite our chief guest, Dr. Subhash Sarkar, to address the session.
Kalai Vanakkam, Shubhodayam, Shubhodaya, and Shubprabhatam, southern part of our India, and little bit which is other than Shubprabhat or Suprabhatam. This is Shubh Sabera from Punjab, Shubh Vakhair from Kashmir, and we should not forget our Manipur. This is Mangal Karak. This is our Ek Bharat, Shrestha Bharat, and you all scientists have come from our Ek Bharat, Shrestha Bharat. Ek Bharat, Shrestha Bharat नाम से तो ताली बजना चाहिए. Namaskar. On the dais
our Honorable Director, Professor Amit Patraji, Professor G.U. Kulkarni, Professor Kanishka Vishwas, Professor Chandan Upadhyay, and who is just like on the dining table like a salt. He is Professor Dr. Sanjay Singh. And there are so many scientists and other fellows. And little bit, there's a Dr. Kanjilal, Dr. Poonam Jadhav. Warm greetings to all. I am honored to be part of the Synchrotron X-ray User Outreach Workshop, a collaboration between DST India and DESY Germany, which is organized in IIT BHU and JNCASR with DST's Nano and Advanced Material Division, is a strategic initiative to enhance Indian scientists' access to Petra 3, one of the world's most advanced synchrotron X-ray sources. We must cherish the coming together of such great institutions for this innovative workshop and to achieve the remarkable developments in this field through collaborative research. Let me reiterate the importance of the collaborative research once again so that the future generation should act in collaboration rather than being merely competitive. I should tell one very small experience of mine. Nowadays, collaborative research has become mandatory. One of my teacher, there's a long back, he expressed his sorrowness when he was doing MS ophthalmology. At that time, his teacher did not allow them to use slit lamp. That was the culture previously among the scientists. One instrument have come in my department that will be handled by single or two persons. Now we are multiple users and multi-institutional users and taking the information from different sources and different scientists and different countries also we are doing together. First of all, collaborative research diversifies the expertise as it brings together experts from various fields as we see today happening. Please give a big round of applause for all organizers as they plan to come together and collaborate for this workshop. The collaborative research also results into enhanced problem solving and resource sharing in optimal manner. With the improved research quality, obviously the productivity is also enhanced and networking also results into better outcomes and outreach as well. Dear friends, coming back to the topic, the Petra 3 enables groundbreaking research in diffraction, scattering, spectroscopy, and imaging, allowing precise investigation of atomic and molecular structure. These capabilities drive innovation in quantum materials, battery technology, semiconductors, and energy conversion. Such advancements are crucial for India's scientific and industrial growth. And everybody will be happy that during COVID time, the use of this synchrotron X-ray was done very nicely. And that has also helped for derivation of our vaccine also. I will request everyone to read one book This book, name of the book is Go Viral. It will be useful for to get inspiration of a scientist. Go Viral book was written by Dr. Balaram Bhargav, the then ICMR director. It provides deep insights into the fundamental properties of materials, paving the way for the development of next generation electronics, quantum devices, efficient energy storage system, and novel materials for sustainable technologies and healthcare also. This is my field. Over the past two phases, more than 1,000 researchers have utilized DESY's facilities, resulting in numerous high-impact publications based on experiments conducted at Petra 3. As we move forward in the discussion related to X-ray users, I would like to talk about the diffraction grating experiment. This experiment has remained in my memory since high school days, as it need utmost attention and precision. One small mistake and then you need to wait patiently for the results. The experiment has demonstrated the wave nature of light by using a grating with thousands of parallel slits to produce an interference pattern. When light passes through, it diffracts at specific angles based on its wavelength, following the equation in lambda is d sine theta. This allows precise wavelength measurement, making the experiment essential in spectroscopy, optical instruments, and telecommunications. It offers higher accuracy than double slit experiments and is used in astronomy and to analyze star spectra. The experiment reinforces wave theory, adding advancement in physics and engineering through applications in spectrometers, sensors, and laser technology. Dear friends, I would also take a moment to share about our country's long, rich, and prosperous history of diverse traditions and institutions of knowledge. We should keep respect in our heart, in our memory also. The great legacy of this traditional encompasses the concepts, principles, and theories to guide people to having a meaningful and satisfying life. Yes, we have then so many institutions like Nalanda, Vikramshila, Takshashila, Vallavi, etc. I would like to share a small excerpt related to Swami Vivekananda. Swamiji was fascinated by the concept of creation given in Nashadiya Sutra, the only one that there was hammered itself to bring out the creation. From this, Swamiji developed the concept of prana and akasha coming out of the same substance, and these two being one in the dualoka, that is electric sphere. If we could remember that two philosophers was roaming in a ship in the midst of sea, and in the midst of sea, suddenly a storm came, and the water waves, and over the head, the sky. One of the philosophers is telling, Shunnam, 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 Shunnam. And another was telling, Purnam, Purnam. That gives us the idea to understand the matter and to understand the incidents, understand the dualaka, the electric sphere. The great scientist Nikola Tesla was fascinated by these ideas of Swamiji in 1896 and it would wait for another 10 years for Einstein to work out independently the equivalence of matter and energy in his now famous equation, that is E is equal to mc square. And every small particle have infinite energy. And it is nothing but what we tell, Sarvam Khalvidang Brahma. Moving forward, I would like to say the various schemes and initiatives by Department of Science and Technology, Madam has already expressed, which are creating huge impacts in the science and technology space, like National Mission on Interdisciplinary Cyber Physical System, that is NMICPS, National Quantum Mission, National Supercomputing Mission, climate change missions. We must take a moment to appreciate the monumental effort by our Honorable Prime Minister Sri Narendra Modi ji in the field of science and technology. His vision and furthered our cause of continuous innovation in this field. My dear friends, the Anushandhan National Research Foundation, that is ANRF, has been established with giving a definitive power, that is Anushandhan National Research Foundation ANRF 2023 Act. The NRF aims to seed, grow and promote research and development and foster a culture of research and innovation throughout India's universities, college, research institutions, and I will tell also schools and R&D laboratories. ANRF will act as an apex body to provide high-level strategic direction to scientific research in the country as per recommendation of the National Education Policy 2020. NRF will forge collaboration among the industry, academia and government departments and research institutions and create an interface mechanism for participation and contribution of industries and state governments in addition to the scientific and line ministries. I am reminded of a quote by 1944 born scientist Williams Brodie. What is the calculus of innovation? The calculus of innovation is really quite simple. Knowledge drives innovation. Innovation drives productivity, and productivity drives economic growth. Now our research in India has also streamlined. If I am not wrong, previously, about 2 decades back, there were competition, how many papers we could publish. And now, not only that, the paper publication and some research work, then how many patents have been done, and how many patents have been transferred to the technology, and how many that kind of technology transferred matter has come into utility of the society, and how many of that has come into the utility of the country's export ecosystem. My dear friends, the future of India, you all represented the future of scientific discovery, and we trust this workshop, which includes around 15 expert lectures, will be providing you a complete overview of the facility and how to use the state-of-the-art facilities to support your research. We hope this event fosters new ideas, encourages collaboration, and enhances our collaborative understanding of the vast opportunities offered by synchrotron X-ray facilities. We should also remind few scattered words sometimes have been given by our Honorable Prime Minister Narendra Modi on innovation and self-reliance. He told India has to trade forwards from here. We have to focus on developing indigenous technologies and products to make India self-reliant. In research ecosystem, he told, most highlighted that research output and patents had grown rapidly in the last decade, and India's ranking in the global innovation index rankings had moved from 81st to 39th. Investment of research, this is very important. That is, a research fund of rupees 1 trillion was created to strengthen India's research ecosystem. Focus on critical technologies. Today, India's focus on critical technologies like AI and semiconductor, India's AI mission would increase both research and skills in the field of AI. Before that, I should tell a story to you. The story is a very popular story, and it is a true incident. And I hope this story will give inspiration to the researchers. I am trying, failure. Then what to do? A businessman in America, he gathered a lot of money and he tried to be a popular and definitive, a very good businessman. But he tried and ultimately he failed. Repeatedly. He repeatedly failed, and then he decided that he will destroy his own life. Then all of money he gathered, and taking all these, that was not very much. He came out from his home to commit suicide. Then he came to an area where there was gambling. And the gambling was such that a manganese mining company, they were digging a big area, and they did not get manganese from that mining areas. And that's why they decided to sell out. And the Nilam, and he decided, I would like to commit suicide, let us participate in this. And he has not very big amount of money, very big land, but it is about 300 meters digging was done. Who will take this land? And what will be the utility? And he participated. And what happened? Fortunately, what amount of he offered, none came after him. And he got the land. And after that, at the time the digging was continuing, and all the laborers, they told, what I will do? Because land has become new owner. And yes, you have got your wages for this day, continue it. And after 3 feet digging, they got the manganese ore. And he became a very, very, very big businessman. And this story of that book is success, distance between success and failure is only 3 feet. So that's why I hope these incidents will give inspiration to all the scientists. I heartily welcome all participants and wish you the best throughout the workshop. As we say, necessity is the mother of invention. May you all keep inventing for the betterment of humankind. I hope this event will create new ideas for the synchrotron facilities. Thanking you, Bharat Mata Ki Jai.
Thank Thank you so much, sir, for your enlightening words. Next, I would like to conclude this inaugural session by inviting Professor Chandan Upadhyay, IIT BHU, to deliver the vote of thanks.
Thank you, Shivani. It's my privilege to offer a vote of thanks. It's very delighting to hear Dr. Subhash Sarkarji. I had a privilege to hear you on NEP issues and who, steer the whole program very effectively, and now we started seeing the fruits of that new education policy. Thank you, sir, from core of our heart that you spared some time and graced us at this occasion. I would also like to thank Professor Amit Patra ji, who is thriving and driving this institute to achieve excellence. Thank you, sir. I mean, we feel very motivated under his leadership. Thank you for sparing some time to come here. I would like to thank President JNC, who encouraged us to take up this workshop here. We get a very nice opportunity to see very familiar faces, Professor Chandran, Kanjilal sir, Kalobranji, and then very new researchers. And thank you very much for granting this. Thank you, Kaniska and Sanjay, for organizing this program very nicely and very effectively. I would like to thank our deans and head of the departments across the institute who spared some time. I know there's a lot of activities are going on. So thank you, sir, for gracing us at this occasion. Other faculty members from the institute, I see many familiar faces. Thank you very much for coming here. And volunteers, I must thank. I know that they have been working from last 1 month, from compiling the list, sending emails and everything. Without their, they are the backbone of this program. Without their immense contribution, we are here today. Thank you, and thank you, participants. I mean, you are the crux of this workshop. So thank you for showing your interest. Thank you for coming here. And do spare some time to visit different departments where you have some connection or where you find some interest. And interact with the fellow PhD student, because that's the connection which you will, carry on in the future. A lot of collaboration will be forged, out of these meetings. And finally, thank you, the representative of the DST, Dr. Yadav, and and personal thanks to the DST secretary, sir, for his very wonderful message and sponsoring this whole program. Thank you very much.
Thank you, sir, for the vote of thanks. That brings us to the end of this inauguration session. Thank you, everyone. Please join us for the photo session and then the high tea. We will start our talk session from 10:45, and I request everyone to see the poster of participants downstairs and interact with them during these breaks, since we don't have a specific time for the poster session because of time limitation. Thank you, everyone.
and he works on photoemission spectroscopy. And title of his talk is Depth Resolved Spectroscopy of Quantum Materials Using Higgs Space. Professor Maiti.
I have to go there or okay? No, but is it okay if I can?
Yeah,
hear
it's
me?
fine.
Yeah. I have to then stand there. I think. Okay, good morning. So it's really a pleasure for me to be here, such a beautiful campus, and I have been here several times and see many friends here, so the things are coming up very well. And I also thank the organizers for the invitation to this interesting workshop. So today I'll try to give a brief overview about the work that we have done in last 3-4 years. So using the Petra facility, basically. So today I'll try to highlight how one can get information about the electronic structure as a function of depth in various material, and how that helps to find out the underlying physics of the material properties. Okay, so photoelectron spectroscopy, for the students I prepared some of the introductory slides so that you can follow it up, but you please stop me if there are any issues in between. So photoelectron spectroscopy is basically based on photoelectric effect. So you shine light on material. I think this pointer doesn't work. Huh? Yeah, so okay, so what should I do? Huh? Okay, yeah. Ah, okay, okay. So basically standing here helps, okay? Yeah. Okay, so photoelectric effect basically means that you shine light, a shine sample with some light, and if the photon energy is high enough to knock out electrons from the material, so the electron will absorb that energy and it will come out of the material. So what you do is that in this experiment you put a detector here and find out the kinetic energy of the electron, the number of electrons coming out at a particular kinetic energy and its momentum, spin, and so on. So then you can use various conservation rules, because you know that electron excitation is a quantum mechanical process. So use conservation laws to find out what was the property of the electron when it was there inside the solid. So, you know, I mean, if I think of that, this is basically the schematic of the occupied part of the electronic structure, like these are core levels and this is the valence band. The highest occupied level is called the Fermi level. So now electrons which are there in this occupied part will absorb this energy that comes on the sample, and it will get excited to the final state. And these electrons which has energy higher than this vacuum level, which is by the work function away from the Fermi level, will come out of the sample and you detect this kinetic energy. Okay. So if if I know the number of electrons as intensity at a particular energy that you have detected, that would be related to this many factors. One is called the cross section, which is dependent on the transition of electron from this occupied part to the excited state. And then there are resolution functions, which are basically how accurately you can detect the electron kinetic energy. This is the lifetime of the electrons and holes that you create. And this one is another important factor, so which I'll basically focus on today. And then the other part that you really want to probe is called the density of states. So you are basically probing the density of states in the electronic structure by photoemission spectroscopy. but you have to actually worry about so many factors along with the density of states to understand the photoemission spectrum. I'm not getting into the other details of this. Okay. So the absorption kind of part that I have shown here, this e to the power minus x by lambda, I would just elaborate a little bit on that. So if lambda is called the mean free path, so assume that this is your sample, okay, and you are shining light on this. Now, you know the sample has a surface. Of course, there is no unique way to define how much would be the surface, how much would be the bulk. But if I assume that, say, for example, the top layer of the material is surface, or maybe top 1 or 2 layers, or 3 layers may be the surface, and the remaining behaves like a bulk. Now, if you shine light on this material, of course, the electron at different location will get excited, okay? Now, assume that the electron which are excited is at a depth x from the surface. And if your mean free path means that the electron comes out of the material without any other scattering loss. So the moment electron undergoes some scattering process, it will lose energy. Of course, then that will not be counted as signal. So the real signal is the one which are coming out without any energy loss, okay? So if the mean free path is lambda, then you know that the factor that comes as e to the power minus x by lambda, that's the fraction of electron that comes out and as a signal. Now if I plot lambda as a kinetic energy of the electrons that comes out, it looks like that, this various material. So this one is called universal curve. I am showing you a data which is many decades old. Okay, but if you really do experiments now also, I'll show you some example that it follows the same rule, okay? So now my aim is basically to make this technique depth resolved, in the sense that you want to know the electronic structure at different depth from the surface, how it is, okay? So how you can probe. So the one way is that you can change lambda, because you know this universal curve says that it's most surface sensitive when the kinetic energy is between 40 to say 100 electron volt or so. So you know that this is about 6 to 8 angstrom, okay? Means that you are probing only top 2 to 3 layers. Each layer, if it is say 2 angstrom, so you are basically probing 2 to 3 layers. So now you change the photon energy to high energy, and you can change the lambda significantly. Similarly, if you go to low energy, you can also increase the lambda. So that way, you can get a experimental spectrum at different depth, okay, effective depth, and use that to extract your surface and bulk electronic structure. Okay, this whole business basically to extracting of surface and bulk using this kind of technique, actually I started during my PhD with Professor D.D. Sharma. So basically, you can see that, and then of course it has been taken up by various groups, and so we continue to play the same game even now, and try to find new phenomena based on this, okay? So the first thing that I said is that you of course change the photon energy, so the lambda changes, and you can actually get spectrum at different surface sensitivity and extract the surface and bulk. But it's not so simple, because you know that you are exciting an electron from initial state to the final state, and this excitation cross section or the photoemission cross section, that depends on the kinetic energy of the electron, like the photon energy that you are probing. So if you are using say low energy like UV or so, you know the P states gets more enhanced because of the cross section compared to D states. But if you go to higher energy, then D states has a higher cross section. So there is a complication. But if you are probing a energy level like core level, where you have one kind of states there, so whether the cross section changes or not, it doesn't really matter, because you are actually looking at the same thing whichever you are exciting. So the analysis will not get affected, but of course the valence band has this problem. So the valence band spectra is not easy to identify using this changing photon energy, because those are hybridized states, okay? So now, if I assume the kinetic energy and their effective length that it probes, at 1.5 keV, lambda is about 20 angstrom. Now, hard X-ray, how it helps? Because if you go to hard X-ray, then around say 6 keV, which we mostly use, then the probing depth is 40 angstrom or so. So it probes about 20 layers. So you can assume that you are actually now bulk sensitive. Now, if I calculate, assuming that the surface is about 3 to 4 layers, approximately, it's material dependent, okay? Then at 1.5 keV, you are actually probing 74% of the bulk. And if you go to 6 and 8 keV, then it's 86 or 88. So it's mostly bulk kind of spectra if you are at a high energy. But if you are at low energy, of course, you have a large contribution from the surface, okay? And then you can calculate the surface and bulk intensity and extract the surface bulk. The other way that you can do is that you can change angle. So angle at which it comes out. So here, what we have shown here is that if the electron comes out normal, along the surface normal, of course the probing depth lambda will be associated with the depth it probes. But if it is coming out at a angle say theta, then the probing depth from the surface is this, but it has to travel this much length because of the angled emission. So the effective depth will be lambda cos theta, okay? So here, you are not really changing the photon energy, but change the angle, and then of course, you actually change the surface sensitivity. You can change it as you like, but here also, since the photon energy is fixed, of course, you are not changing the photo emission cross section. But one thing that changes is that when you are using synchrotron light, they are linearly polarized light. So the linear polarization vector makes an angle with respect to the sample, okay? So that way, if your states are polarization sensitive, then of course, they are not spherically symmetric states like SOFs and so on. So then of course, the photo emission cross section will change. So again, matrix element dependence will come. What I want to say that whether you change angle or change photon energy, everything has some other aspects that you need to worry. But all these doesn't matter when you are looking at core levels. Because core levels, they are all completely filled, whether you are looking at 2P or 3D. So the overall symmetry is like a spherical symmetry. It's like an atomic level, okay? So that way, those can be probed as a function of depth pretty easily. Valence band, you need to worry about a little bit like that. So the beamline that I used, actually I would like to thank the organizers because, you know, this is a great contract which are made at Petra because we, I think, paid for one beamline, which is P22, of course. That's the Indian beamline which was made. But anybody can apply for beam time in any of the beamline. And we get 1 year equivalent beam time, which is really great. So that way, I mean, the entire Petra facility can be utilized by the Indian users because of this contract. So I really thank the organizers for that. Professor Rao for really is the brilliant idea about this. So the beamline that I used initially some years back before the Indian beamline came up, we used P09, which was the hard X-ray beamline. And then we moved to P22, which is basically the Indian beamline. So the main issue is that, of course, we can go up to, say, 8 keV or so. I mean, pretty high energy. And Petra, the advantage is that you can actually make the resolution, like how accurately you can determine the energy very well. So the best resolution achieved so far is 150 milli-electron volt, which is not really achieved. So we mostly use 6 keV because that's the best condition that it gives. It's optimized at that. But of course, I mean, you can get 0.2 electron volt, like 200 MeV quite regularly at other energies also. The issue here is that, as I said, that photo emission intensity, it doesn't depend only on the instrument resolution, also it depends on the lifetime broadening. Now, if you are using a hard X-ray, of course, the kinetic energy will be very, very high. So the uncertainty, I mean, in energy, of course, you have to worry about. So the lifetime broadening also is significantly large. So even if you have high energy, it's not necessary that you will be able to probe the features which are extremely narrow. Okay, so it's like that. So one has to keep in mind those. So the kind of things that I have noted here, like Kondo peak, which comes nearly at the Fermi level of the order of 10 millivolt, superconducting gap, which is also of the order of 10 millivolt or lower, band gap in various topological insulators like Kondo insulators and so on. So these are very difficult to probe, even if you have a very, very high energy. However, I would suggest that always use the best energy resolution that is possible, because that's the way you can actually determine the features very well, okay? So now I'll talk about some of the interesting results that we have got. So the first I just show here that, this is summary of various class of superconductors that are discovered so far, okay? So, I mean, you may find it, I have made my own figure, but you may find similar figures in the net also. So the first superconductor which was discovered in, which got Nobel Prize to Kamal honors is this mercury. And then, of course, in the same class, various materials were discovered. The latest is MgB2 in 2000, okay, so which are known as conventional superconductors, means that the electron-electron phonon coupling as a reason for Cooper pairs is working in this kind of materials, okay? So people think that to get superconductivity, you need to have two electrons pairing together. Now, nobody knows how that pairing happens, okay? So one of the belief that is called BCS theory is that the electron-phonon interaction actually mediates this kind of coupling, where the phonon works like a glue to really stick two electrons together, otherwise they'll repel each other, okay? So these are called conventional superconductors. So these are these black ones, open circles. Everything else that you see, they cannot be explained by this electron-phonon coupling, okay? So these are called unconventional superconductors. All the high TC materials, they are all unconventional superconductors, including many low TC like heavy fermions and so on. So we have also worked some of the cuprates and so on, but here I'll show you one interesting result on iron-based superconductors, which we actually found out based on our experiment at Petra. Okay, this is very interesting observation. So this is calcium iron to arsenic 2. So the structure is like cuprate, so it's a layered structure. You have iron here and these are arsenics, okay? So these iron arsenic, they form a two-dimensional layer and they are separated by calcium. You can have strontium, europium, barium, anything that you want. And you can tune the properties. So calcium iron to arsenic 2, it doesn't really show superconductivity in normal condition. But if you apply pressure, it can show superconductivity at a reasonably high temperature. But if you substitute, say, iron by cobalt, then of course it becomes superconductor in ambient condition. The TC is about 15 Kelvin. So we looked at this one, taking this as a reference and find a very interesting scenario. You see that here I have shown a core level spectrum. This is arsenic 3D collected at 80 electron volt, which is the red one, and hard X-ray photoemission, that is 6 keV, the blue one, okay? You see the red one shows 4 distinct features, but the blue one only shows 2 peaks, okay? So now you can of course change photon energy and see the relative intensity of these features changes. So from this energy dependence, you can easily say that this one must be surface and this one must be bulk, because hard X-ray, just now I showed that it is essentially bulk sensitive. Almost 90% comes from the bulk, okay? So you can analyze and find out which one is surface, which one is bulk. From that you can find out the effective penetration depth, and you see that it follows the rule that I showed, the universal curve, okay? I think I'll go a little quickly. So you can also find out that why the surface would be different. So in one case, I show you a STM study. So, you know, whenever you cleave a sample, of course, yeah? There are 4 peaks. Yeah. 1, 2, 3, 4. Yeah. Only one which is maximum. That will be. No. This is arsenic 3D. So D has what is the L value? That is 2.
L equal to 2. So now if you knock out an electron which has a spin half, okay, so your total angular momentum can be L plus half or L minus half. So that means 2 plus half, that is 3d 5 by 2, or you can have L minus half, that is 3 by 2. So you have 2 peaks. So because of this total angular momentum, so the bulk will have 2 peaks and surface will have 2 peaks. So that way you have this one is surface and this one is the spin orbit split peak. This one is bulk and its spin orbit split peak. Okay? And then from the relative intensity, you can actually find out what is the effective depth. Okay? So now what I'm saying is that if you clip the sample surface, you of course know that there will be reconstruction, there will be defects and so on. That actually makes your surface electronic structure different from bulk. That we have identified from the STM study and so on. So that shows why it is different. Now let's look at the critical part that I want to show you. So here I am showing arsenic 3P here. Okay? So this is arsenic 3P for the superconducting material. And you see that I have done experiment at different temperatures. Okay? They look almost identical. So there is absolutely no change in arsenic. But calcium of course shows some change, but the spectral shape is identical because if you shift them, they look almost same. Okay? But if you look at iron 2P, it shows some interesting behavior. Okay? So that means that you have a peak here which is say around 210 Kelvin, and you cool down and you see that intensity goes up. And there is no way you can make them shift and so on, and you can make the same line shape. It's very, very different. This doesn't happen for calcium iron to arsenic. Like if you don't have the superconductivity, you don't see this. Okay? So this attracted our attention. So why the superconducting material shows a different behavior? So I'll tell you what is happening here basically. So assume that this is your lattice. Now if you knock out a electron, so from the core level, okay, so what happens is that you have created a hole here. So this one becomes positively charged because you have knocked out an electron. So instantaneously, so this positive charge can be screened by an electron transfer from the neighboring side to this. Okay? So if that happens, you call it a well-screened feature. Okay? And of course, it's a quantum mechanical state. You may have unscreened feature also. So whenever you look at photoemission spectrum, you always get these two contributions. So you are supposed to get say 3d 5 by 2 1 peak, but actually you get 2 peaks. One is well-screened, where the core hole is screened by charge transfer. And if you transfer a charge, of course, it becomes neutral. So the binding energy, of course, will be very different from the charge state, which is a +1 state. Okay? So it will come at a higher energy peak. So the poorly screened peak always comes at higher energy compared to this. So this is pretty much well known. Okay? But if you look at the spectrum,
you can use that stick.
Huh?
You can use that stick.
Okay, it's okay. Huh? Yeah. So now if you look at the cube rays, for example, you see that here you have a poorly screened peak, this is a well-screened peak. Okay? But if you do hard X-ray photoemission, what you do is that you see another peak comes out at a lower. I'll explain what is that. This is called Zhang-Rice singlet. So what is happening here is that basically you have transferred an electron from here to here, so you have created a hole. This hole can move around in the lattice, okay, so because it's a conduction band. So now if this hole has moved here, and you have a hole here, and it forms a singlet. Okay. Then because of this singlet formation, the total energy will be even lower. Okay. So you get a peak at a lower binding energy. That's for it. Now people believe that if you have this kind of singlet, so the system is more probable to form a Cooper pair. Because Cooper pair is nothing but 2 electrons, so they're forming a pair of opposites. Okay. So this one people thought that could be a signature of superconductivity. And so basically what we are trying to say is that this feature that comes out in iron-based system probably is something similar like Zhang-Rice singlet. And this is not found in non-superconducting material. Okay? So this actually re-emphasizes this theory. So this is the first observation in this material. So far, no other observation exists in iron-based system. Okay. So this is one. The second thing which I talk about, so we studied extensively this topological materials. Okay. So those who don't know topology, I'll just give a brief schematic overview. Topological insulators are insulators where you have this bulk valence band completely filled and completely empty conduction band which is separated by a gap. Now in these materials, the surface states, if they form a kind of a conduction band and if there is a time reversal symmetric protection, okay, then they are called topological materials. What do you mean by time reversal symmetric protection? So time reversal symmetry means you are reversing the time. So T becomes minus T. So that means your momentum, if it was moving in this direction, it will start moving in the opposite direction if you really change the momentum. Now spin also is a momentum. Okay. So that means that if your up spin is moving in this direction, the one which moves in this direction must be having down spin if there is a time reversal symmetry. This is basically the criteria compared to the normal materials. So what is the speciality? Like in these materials, if you have a impurity, for example, here, so the electron which was moving in this direction, it will try to get scattered. But it cannot get scattered because if it wants to move in this direction, it needs to have a down spin. So that means the spin flip is necessary and which costs energy. So that's the reason. If you have an electron which moves in this direction because of the symmetric protection, it will continue to move whatever you do. Okay, so that's the speciality. So all the quantum materials that people talk about are actually like that. So it's more like a one-way traffic in a traffic signals. Like if a car is moving in this way, you see always white light, and if it is moving the other way, it's a red light. As long as one-way traffic rule is maintained, I mean in India of course sometimes people brake, but if you are not braking, even if you have an accident somewhere, okay, it doesn't matter, the car will move in the same direction because the rule is maintained. Okay, so it's basically that. And in materials, what happens is that, so the normal insulators are like this. You have a valence band and conduction band. Now, if these two overlaps and it opens up a gap, you can see that the red and blue got mixed up. That's called band inversion. So normally, if you have a band inversion, you do see this kind of behavior. Okay. Anyway, the real materials are of course very, very complex. So you do see, okay, one thing is that in this system, the energy band structure shows this kind of dispersion, which is called Dirac cone. You know that the energy from the Einstein's equation, you can write down E square equal to P square C square plus M0 square C to the power 4. So now, if you put M0 as 0, then E becomes linearly proportional to P. So these are called Dirac fermions with rest mass 0. Okay, so that's the reason you get linear dispersion. So if you look at the real material, it shows of course the Dirac cone like this, but these have a much more complex shape. So this is one material which shows this BIPD. The structure is basically non-centrosymmetric structure. Okay, I'll tell you what is the importance of that. I'll just show you core level because I'm not talking about the valence band. So this is what you actually do. So this is the core level spectrum, and you see this is bismuth 5D. So this is D5/2, this is 3/2, and it shows two peaks. These are at low energies, and you change photon energy, you see the relative intensity changes. That's because the surface sensitivity changes. Okay, so that way you can extract surface and bulk and find out. So now, for example, 49 eV spectrum. Yeah, this one. If I compare with the hard X-ray spectrum, you see that the higher energy one is the bulk, because that one is the bulk one, and this is the surface. So from that you can actually find out how the effective lambda changes with energy, and it follows the reversal. The most interesting part that I want to show you here is that you know that this is bismuth 4A, okay? And if I find out the relative intensity of these two, okay, you know any peak, the intensity depends on its degeneration. So I have talked about the total angular momentum J, which can be L plus S or L minus S. So this is like this. Now this one intensity will be 2J plus 1. That's called the degeneracy of the state. So if I calculate for 4A, it should be 3:4. So this one
देखिए खराब हो जाएगा, हमको क्या है?
So this is a normal relation. You use the
कुछ नहीं होने वाला।
This is called branching ratio.
उससे कुछ नहीं होता।
But what we find that this intensity is much larger than this compared to 3:4, like 0.75. So if I calculate, it comes out to be 0.83. So what is happening? Why the branching ratio is so large compared to that? Palladium actually doesn't show this field. Palladium is actually following the loop. So palladium 3D, it should be 2:3, so that is 0.67, and it follows the same norm. So what happens is that we try to look at the spectrum. So this one you can see that the normal emission spectrum is the red one, and this one is angular emission spectrum. So you make it more surface sensitive. See that the intensity goes significantly. So what we feel is that this is something that whenever we describe this intensity of various peaks, we always think of atomic descriptions. So this degeneracy and so on. But the behavior would be very different in solid. Because whenever a material is there in solid, of course, there can be additional contributions. So, if you have a effective electric field gradient, you know that it can give you stronger spin orbit coupling. People have talked about Rasba splitting, Dresselhaus. How many minutes? Oh, okay. Dresselhaus effect and so on. So, since this is a non-centrosymmetric material, means that there is no center of symmetry. So, you have an effective electric field gradient inside. Okay, so this is something called Dresselhaus effect. That actually enhances its orbital moment. Okay, so that's the reason whichever is a heavier atom, it shows a stronger orbital moment in this material, and that actually enhances this the branching ratio. Okay, so these are the two things that I would. So the third thing I'll finish very quickly. Okay, so this is another material which we looked at. Okay, the interest is that just now I said that Dirac fermions are basically particles or fermions which has rest mass 0. So that means the band dispersion, it shows linear band dispersion. What we try to do is that you enhance electron correlation into the system, like Coulomb repulsion. So whenever you have Coulomb repulsion, the electrons will be less mobile because you try to enhance their effective mass. So they will become heavier and so on. So in this kind of system, if you enhance Coulomb repulsion, what happens? So this is an interesting material. These are cerium, and this is basically, it can be copper or nitrogen like antimony or arsenic. So they form the conduction band, and this cerium core hybridizes with these states, giving rise to Kondo effect. Kondo effect, the heavy fermion physics comes from that. Now this layer, which is also another antimony layer, this forms this square net kind of structure. And this actually hosts Dirac fermions. This is known. You can calculate and find out that their band structure shows Dirac force. So these electrons, they are in proximity to this cerium, so there will be hybridization. Okay? So we wanted to see what happens because of this hybridization, what happens to this electronic structure. So there are many things that we have studied, but here I'll talk about something very different. Okay, let's. I think because of the lack of time, I'm not getting into all this. Okay, what I wanted to say here, maybe quickly, I can say that the F levels, they are behaving like a core levels because the F orbital extension is much smaller compared to P or S. Okay, so that is they behave like a core. They don't really hybridize with the nearest neighbors and so on. So you can think of like atomic level, and then the conduction band disperses like this. This is momentum, this is energy. And now if they are hybridizing, it opens up a gap, which is like you have a F state and then D state and F state like this. Similarly, here it's E, F, D. Now if you think of parity, -1 whole to the power L. Okay. So for D state, the parity is even parity because L is 2. For F state, it is odd because L is 3. Okay. So here you And these actually kind of things gives rise to the Dirac states. So these are natural kind of systems which can show you the Dirac kind of fermions. So the surface you can actually see the Dirac cone. What we observe, I think, of course, I mean, if you do experiment, for example, with different photon energy, so this one is, for example, 2.5 keV, red is 6 keV, 8 is blue is 8 keV, and you see the intensity changes so much compared to this thing. So that actually clearly tells you that if you change the surface sensitivity, the electronic structure changes significantly. And you can, of course, extract surface and bulk. But I want to attract your attention maybe for a very other aspect quickly. Okay. So I'm actually looking at the core level spectrum of cerium-3. So there is a very, very interesting discovery, I can say, or whatever you can say. It's an interesting phenomenon. You see that cerium 3D core level, it shows many peaks. And I'll explain you what are those peaks. And there is one peak here. Normally, I mean, this kind of spectrum is captured by Gulnasham's number. Okay, so this one is the kinetic energy of conduction electron. This is electron energy. This one is the correlation electron-coulomb repulsion, between F state and core hole. And of course, this is the core hole energy. This one is hopping energy of conduction electron, and this is your electron-coulomb repulsion of valence. So you use this Hamiltonian. So to solve this, okay, you can actually take only 3 configurations to solve this very easily. You don't have to go to many complex things. What are those 3 states? One, we call it F0 state. It means that in cerium you have 1 electron in the 4f level. So this 4f level, it can stay in the 4f or it can hop to the conduction band. So if it hops to conduction band, you call it F0 state because there is nothing. If it remains in the 4f level, you call it F1. Now since you are doing core level photon emission, it can happen that the core level charge is screened by another electron. So then it becomes F2. So this is called well screen state, this is the poorly screen state, and this one, of course, there is no electron. So these 3 contributions you can use and explain the 4F spectrum, 3D spectrum very easily. Okay. So, and what people thought that this feature where the electron is not there in the F level actually has gone to the conduction band is assumed as a signature of Kondo peak. Okay. And this has been known even till today. What I will show you that we extracted the, I'm not getting into the details of this, I think I had too many slides. But anyway, so if you look at, so this is cerium copper arsenic 2, which is a Kondo material. Okay. Means that if you do resistivity, it shows a resistivity minima. And also it shows magnetism, it doesn't show magnetic order and so on. So this is a perfect Kondo material, but you see that you have a peak here, set of peak here, you have a set of peak here, but there is no F0 peak. So it means that this F0 peak, which was actually thought to be a signature of Kondo effect, may not be correct because most of the Kondo materials actually they don't show this F0 peak. Not only that, sometimes we have seen that if you have the surface peak, some of them they show this feature, but in the bulk it's not there. But the bulk Kondo effect is a bulk effect. So basically, what we are trying to say is that this description of F0 peak as a Kondo peak may need to be rethought. Okay. That's one thing. The second thing is that in these materials we see a new feature. This was not observed earlier. So we actually are able to find out this from the RX photon emission. So this one has a lower energy compared to the peaks that people have found. So that means that these materials actually has a completely new state at a much lower energy, which was not found. Okay. So basically this is the summary. So I have shown you 3 interesting results. One is the kind of a finding of Sangrai singlet in iron-based systems, which was not really found. That was possible because of this X-space studies. The second thing I have shown you that the description, atomic description doesn't work in solid because you have an enhancement of in-orbit coupling. But people traditionally used atomic description for O-level studies in all. So that needs to be looked at carefully. So the third thing is that the definition of the Kondo. So one has to really find out really Kondo theory works or not. If it works, which feature is basically representing the Kondo theory. There are a lot. I have actually done a lot of experiments. This year also I have a big time in May. So, so we get almost once in a year, and of course I agree that each big time produces a paper. So these are the group members I like to thank. These are basically the organizers also. These are papers published based on the review. Yeah, I didn't know that, so I just put it that way. So just thank you very much.
You did the depth resolved photoelectron spectra by changing photon energy, right? So, but you could have done also the second one you just talked, changing electron emission angle.
I have done it also. In one case I have shown for DIPD, where we have kept everything same but changed the angle from normal emission to 65-degree angled emission. And we saw, actually that's the way we found out that the spin-orbit coupling of the surface electronic structure even much stronger compared to bar.
So, they call it angle resolved
No, this is not. Angle resolved photonation is a very different thing. So there what happens is that you try to, this is depth resolved still. Angle resolved is that you associate the emission angle to the momentum, because the momentum is conserved for this. So you find out the momentum of the electron that comes out from the angle and the kinetic energy. Kinetic energy, you know, is 3 electron light, E square by 2m. So you know E, and if you know the angle, then you know the direction in which it comes out. So that way you know the momentum of the electron that comes out. From momentum conservation, you can associate this momentum to the momentum when it was there inside the cell. So like the crystal. Okay. So that way you know the momentum and corresponding binding energy. So that gives you energy as a function of K. So you do band matching. So that's the angle.
Also, sir, I have seen somewhere angle integrated.
Yeah.
What is frame? I guess.
Yeah. So these are all what I showed is basically angle integrated spectrum, because we are not resolving the momentum dispersion, okay? The momentum dependence. What we do is that we, you know, this in photo emission, like when you are detecting electrons, you are accepting electrons which are coming out in certain solid angle. Okay? So we try to accept all of them. If we are taking all of them, then you are integrating over all the angles. Okay, so that's called angle integrated kind of spectrum, and that relates to the density of space, because you are not really resolving the momentum, so you are not really doing the band match.
So basically, sir, we are seeing the average electronic density of states, right?
It is electron, when you are talking about density of states, you basically plot it as a function of energy. You have no K dependence. So it's always averaged over all the K. Yeah.
So you done all this experiment on bulk material, right? Like the bulk is in size bulk. So when you put it there, you make angles of spectroscopy. So how you know that, like if a sheet, how you know it at what angle the sheets are? Because you are studying it on the layered structure. You are, whatever the study you are doing theoretically is basically for a layered structure. But if you are essentially synthesizing bulk material, how the layers are exactly there, you don't know. So how you will study? You can say that the theoretical part is going to that one.
Okay. So the material that I have shown here, these are all single crystals. So you can do Lave and find out what is the surface normal, what are the axes, and so on. So that way you know the crystal information completely, and when you do the angle variation, you can actually find out which layer you are looking at. But this depth resolved spectrum, when I am talking about, it's not necessary that it has to be single crystal. So what you do is that you assume that the surface that is exposed to the light is your reference layer, because we are not doing K resolve, we are doing K integrated. So you basically integrate over all the K vectors. So you assume that, the top layer or top surface is your 0th level or surface layer, and then you are basically getting the density of states as a function of depth. Now the surface that you are doing, so we essentially prepare by scraping or maybe by cleaving and so on. So assume that it's a flat surface, because that's basically, that you have to consider. It's a flat surface, and you probe the depth from the surface, but it's K integrated.
Same can be done for thin films also.
Thin films, it works better, because, if you have a heterostructure, for example, so you know that how much thickness you have used, whether you are reaching that thickness or not, and you can vary various thicknesses. A lot of people do thin films, heterostructures, multi-layers, and so on, where, of course, you can get much more information. Yeah.
Okay, thanks Professor Maiti for this very fascinating talk. Let us thanks Professor Maiti. Our next speaker is Professor G.M. Kulkarni. He is from JNCS Bangalore. He is working on nanomaterials. Professor Kulkarni.
सब रिकॉर्ड कर रहे हैं क्या जो हम बना रहे हैं तो
Okay, so Chairman Saab, my time starts now, please. You said 30 minutes, right? Okay, let me try to stick to 30 minutes. So first, let me thank the conveners for the invitation. I'll be speaking something about my lab research. I want to tell you what came out of the lab and how we pursued taking the lab research to synchrotron and how we gained. Okay. I hope I'll be able to convey this message across. Before I do that, out of my curiosity, I'm asking you, how many of you are already users of synchrotron, some Excel synchrotron? How many of you, please? Oh, already quite a sizable number. All right, that's good. So this relates to growing gold crystallites and looking at their internal structure. Okay. So let's look at the very the 1 or 2 slides of tutorial. Metals, what kind of crystal structures they get in. We have body-centered cubic, face-centered, and hexagonal close packed. We know the packing fractions, coordination numbers, so on. So when we have these free electron systems with the metallic bond, the systems tend to get to as high symmetry as possible, okay, and that too with maximum number of coordinating atoms in the first sphere. That's how most metals actually crystallize in ambient conditions in face-centered cubic lattices, and some of them also go to HCP because packing fraction and coordination number remains the same. A few of them go to BCC with some compromise, but very few get to simple cubic. In fact, there is only one example, I believe, among elemental metals. Gold is popular. Conventionally, it is all in face-centered cubic, everyone knows. So are other noble metals, as listed out there. Now, if you look at possible phase transitions in these metals, what are conventionally occurring as face-centered cubic, for example, if you apply pressure, temperature, you can drive them to other crystal structures. This is a, few decades people did this kind of work quite some time ago. And you can see what literature says about, hello, G. Must be a VIP call. If you look at the literature, gold and platinum both require around 300 gigapascal, okay, pressure. It is listed out here, but I'll show you some data. Whereas other metals, they take lesser pressure to phase transform. So in spite of all these high pressures, these noble metals actually hesitate to go to any other crystal structure because of the favorable energetics associated with FCC. We will not get into those details, but let's look at one example. So here is the case of gold. This is an X-ray diffractogram, and what this paper shows is under 275 gigapascal at room temperature, you have still face-centered cubic lattice. Already 275 gigapascal, okay? Only when you heat it to under that pressure, similar pressure, to 860 K, that's about 500 degrees centigrade, you tend to see some emergence of these hexagonal close peaks here. Can you make out? HCP 100, HCP 101 start coming up. Otherwise, we have these popular peaks, FCC 111, FCC 002, and FCC 220. Okay? So these remain, very little intensity comes up related to HCP. So I'm talking about 500 degrees centigrade. You're almost halfway through gold melting temperature, and you have already applied around 250, 300 gigapascal. Such hesitance to go to hexagonal pack, which is not very different from FCC, by the way. You're not pushing it to BCO or something else. So it's not going to BCC or something. It's still HCP with very good energetics, but still gold likes to remain in FCC. To the extent that this report talks about, after removing the pressure and temperature, coming back to ambient, gold happily reverts back to FCC. So it's only indication of some phase, such HCP phase, at such elevated conditions. Otherwise, it just comes back to FCC. So we should conclude bulk gold is robust. Okay, so it is noble in many ways. It's also noble in terms of its physical crystalline structure. It is a different case when we come to nanocrystals. Ujjal here looks at high resolution TEM of microcrystals and grain boundaries and all that. So this report talks about very tiny crystal in TEM with 1 gigapascal. When the electron beam is shining, they're looking at the lattice structure and it is transforming to BCT. And it's only in very, very tiny region. Of course, things change very much when you're at the nanoscale because of confinement effects, because of the enhanced surface to volume ratio. Energetics would go very different. And so even gold also can get into other types of crystal structures, but again, momentarily. If you withdraw the pressure, it just gets back to FCC, even when it is a nanocrystal. So it is extremely robust, and it has been a challenge to put gold into some other crystal structure. We reviewed the literature related to nanocrystals and also to some extent microcrystals, looking at how these noble metal crystallites, what kind of metals exist in what kind of crystal structures. Are there non-traditional crystal structures associated with all the metals? I'm not going to really go through, but just it shows the richness of the arena of all these crystal structures of various metals. Metals happily get into other types of lattices if you put them into nano scale, and apply a little pressure or temperature, readily they get into. But as I said, gold does not. And I just showed you also the bulk gold result in the previous slide. Moving forward, let's look at how to grow crystals of gold. And does it give a clue in terms of can the root be changed when we are starting with individual nuclei, individual atoms, and we are making the nucleus grow into a bigger crystallite? Are there chances where we can actually take the root somewhere else and confuse and create different type of crystallites? Today I'm talking to you like this, but this was not the case. When we did the experiment in the lab, it was only serendipity. Okay, that helped us. But we had the outlook, what to look for. We were very clear about it. So conventionally, when you take gold, metal precursors, for example, and gold in this case, and when you try to grow by having them in reducing atmosphere, I'm talking about chemical process, they can get into tiny, tiny single crystals. Either all these shapes are shown there, polyhedral crystals, cuboctahedral, cube type of structures. These are most favored, but often one comes across also multiplied twinned lattices like this. 1980s, if you look at high resolution TM, it was full of these examples. Various types of twinning, what they see in these noble crystallites. And we pushed the boundary and made the single crystals grow further. And as you can see in the SEM pictures from the lab, we have grown gold cuboctahedron, which is typically, in this picture, it is of the order of around 8-10 micrometer wide. And this is the biggest crystal you can find in the world. Okay, so even cuboctahedrons do not grow indefinitely. They rather get into plates because of the energetics I have shown on the above. See, what happens in the case of gold is, if you look at the 111 facet, there are only 3 prominent facets, okay? 111, 100, and 110. If you look at 111, we are looking at now electron volt per angstrom square kind of surface energy. It is low, 0.0587 in relation to the surface energy with 100. and also 110 is much higher. So gold tries its best to exhibit everything with 111 because it wants to save the energy. This disparity is not much with respect to other metals. Okay, if you take silver, for example, the difference is not much. So silver doesn't mind actually going into exhibiting other types of facets. So here, if you look at cuboctahedron, you have 100s exhibited, 111s exhibited. You can simply go with the geometry of the facet and assign what kind of crystallites facets they are. One can also be doing Levet diffraction and all that. The other example is more difficult to get. This is the decahedron crystal. These are all 111 terminated. They're 5-fold symmetry. Very unusual because gold likes, by energetics, it likes to exhibit 111s. But if it packs itself with 111, then there are geometric considerations. Okay, if you pack pentafold 111s like this, you will be left with an angular disorder. And that tiny disorder, to the extent of around 2.5 degrees, is absorbed along the twin planes here between the 111s. Okay, so this slight disorder comes up here in between the twinned crystallites, the zones. Nonetheless, these can also be made to grow few microns wide. So that's the background, and let's move forward. As I said, silver doesn't mind at all. Silver can be made to grow into nanowires like this. It exhibits pentatwinned tips like this, and also extended facets of, say, 110, right? Along these lights can be turned off. Somebody can help me. They were off actually. I don't know why they came back. So you can see that silver doesn't mind exhibiting different types of facets because the energy differences are not too significantly different. And in fact, silver nanowires like this you can also order from Aldrich and other companies. You can get them in barrels now. People use them to work with flexible electronics and all that. So silver system can exist in each one is a sort of single crystal. I would say it is a pentatwinned single crystal it is. No, I think the switch is on the other side. Yeah, so we were messing around with the gold. Let's concentrate on the board, please. It's okay. So, yeah, we were trying to work with the gold for very many reasons. We also made lots of metal organic precursors based on this tetraoctyl ammonium bromide phase transfer reagent. These are well-known stuff in terms of nanomaterial synthesis. I don't want to get into detail. And we were playing around doing lots of different synthesis of nanomaterials and all that. In one instance, we realized that if we take gold complexed with this tetraoctyl ammonium bromide, it also bring in to some extent silver plus. Okay, then we have a mixture of this. This is a liquid crystalline state when you drive away the solvent, and this solution, if you take and drop cast on a glass plate and just heat it up on a hot plate in air, you end up with a sort of a little messy system. It needs ammonia wash. After that, what you see is simply unbelievable. It's actually consisting of gold in a different form altogether. So here goes the story. We actually aim to, through this chemical synthesis, we aim to produce these pentatwinned crystallites, Chota crystallites. The angular gap is shown there. And then when it is made to grow, most favored growth direction is 110. They grow into these kind of needle structures. And you can, through adjusting kinetics and concentration and all that, you can make them grow like this into needle type of structures like this. Okay, and this can be done even with pure gold precursor. But if you do have some amount of silver mixed with it, then the magic happens. See, this is very beautiful morphology actually. You can see the rugged facet here. These can be indexed as high index planes, which gold simply doesn't exhibit at all. But in this case, we are seeing there is a tiny baby decahedra sitting there, which couldn't grow for some reason. So you can see this pentatwinned arrangement of the needle structure. So what happens in this case, a simple story is that when you have a mix of Ag plus and Au Cl4 minus kind of anion, what happens is Ag tries to come on Au111. One gold gets reduced, forming nuclei, and it exhibits 3 coordination on 111 and 4 coordination on 100. And because of this competition, that to get on to, because Ag can happily have more coordination on on 100. And so it likes 100, but energetics associated with AU crystallite does not permit 100. And this is where some sort of energy barrier breaking happens. And we essentially have now pentatwin decahedrons lined up together to form a larger crystallite, which looks like this. This is a very simple version of the story. Let me get along with it. And you don't have in 1 or 2 or something. You have in millions, actually. And you can prepare them as long as each around 10 micron, width of around half a micron or so. You can almost pick them up on a pip and also mount it wherever and study them. We looked at the powder diffraction, high resolution powder diffraction in the lab. And what you readily see is a crystallite made into pure FCC without the interference of silver plus, okay, at lower temperature. You can see here it gets into pure FCC. Whereas that with elevated temperature, not too much, 220, but that's enough to confuse the kinetics. Then you also have Ag plus to play around there. And then you see the emergence of other peaks coming up here. These can be indexed. We took around 8 months to actually figure out the space groups and all that. Nothing in the literature was helpful. Nothing is there for that matter. And we could actually finally come up with how the peaks can be fitted and all that. Chairman Saab is looking at the watch. How I am doing? I have not gotten to the synchrotron yet. Okay. Opening 2 batsmen are doing bad actually. Yeah, so I will tell you one thing. Having made new crystallites, it's like finding a new element in the periodic table. That was the excitement in the lab. And look at the optical property. These are anisotropic crystals, how the plasmons behave. And we did very many studies actually. How the plasmon shifts with respect to the length of the crystal, so on and so forth. So, yeah, I mean, one can go on like this. Even, we did many studies. I will not get into those details. Yes, this one I should spend some time. These are very different type of crystals. In the sense, it is not an extension of what we have with face-centered gold. Okay, these are altogether different. So, what are the real litmus tests for gold? So to say, one is amalgam formation, another is aqua regia treatment. These are age-old tests for gold, right? I mean, people also use them for extraction of gold in certain places. So if you make mercury interact with the gold, you can see here, this is a very controlled experiment. So we have put some cuboctahedrons here coming from FCC family. And this is one non-FCC, we call it as rice actually, because it has the shape of rice. And you can see amalgam has taken away the FCC entity and left behind non-FCC. It didn't touch at all. We have argued out this in this Anglicam paper. We also have a theory to support that, how the surface cell of non-FCC does not permit the 5D10 system of mercury to get into surface diffusion, penetrate and destroy the gold. Amalgam formation is prevented. We have talked about it. We also looked at aqua regia, where these harsh acids concentrated HNO3 HCl in right mixture can kill this platelet. You can see the FCCI. We can actually make single crystalline gold plates. If somebody wants to learn the game, I'll teach you. You can make almost half single crystal, atomically flat gold crystals. You can use them for device making and all that. So that's the control there. And we have 2 of these rice which are non-FCC, and they are standing there. Nothing happens with aqua regia under the conditions what I've shown. I'm going to use it for a different game later on. So there is some tendency to eat away and all after a while, but I'll come to that later. So chemical stability is very different. What I want to carry across is a chemical recipe took it to altogether different level where physics had failed, okay, for decades. So this chemical trick worked, and I must admit that it was only serendipity. Yes, having done all this, then we were frantically looking for collaboration to dig deeper because our understanding wasn't very clear. We even desperately tried picking up the longest crystal grown in the lab, non-FCC, and mounting it on a glass capillary pip and on a single crystal diffractometer and tried to see whether we are able to get any diffraction pattern at all with the X-ray power running to the highest intensity, whatever. Nothing was seen because volume is so small and a lot of confusion the way, because you have to do the centering and all, goniometer centering. It was not easy at all. Then Meanwhile, we were talking to collaborators. Chandrabas took some of these samples and went to France, Soleil Synchrotron, and he's a high pressure man. He applied high pressure, working with colleagues there. He looked at under high pressure how the crystallites transform. If I remember correctly, chemistry of materials paper, 40 gigapascal it went, and it phase transformed to some extent. But when you withdraw the pressure again, it came back to non-FCC. Again, very robust non-FCC phases. That's the message. That was quite a nice interaction. So we were actually on the lookout. When we, using powder diffraction, what we had learned was we can push the non-FCC content in these crystallites to the extent of around 90-92%. But somehow the last 8-10%, the crystallite was not giving up at all. That was still FCC. So what's going on? Where is what phase? We wanted to understand microscopically what happens. Desperately, we even cut with FIB, made a thin slice of the crystallite and took it to again TM grid and all that TM, but it was total mess. FIB had destroyed the crystallite itself. So nothing was coming to help. Finally, Petra 3, P06 beamline helped us. And this is Chetali who did really the hard work. And that is we're standing on top of the synchrotron beamline. You can see the arrangements there. I'll not get into those details, but I'll tell you, when you take a slide from the lab, this is a very important thing I'm telling you for new users. Carlo also talked about, you have to make it suitable for the experimentation on that particular beamline. That's quite a struggle actually. Though you get 5 days, 6 days there, maximum of beam time, it is 24/7 by the way, not 7, 24/5, whatever. So you have to be having a good team to sit there and work around the clock, collect meaningful data. And before that, you have months of preparation for actually getting the sample ready. So this took us actually, I was there 1 week before to make sure with my own money, by the way, stay and all that, because project doesn't fund that long. To actually, how do we locate this tiny crystallite on the beamline, okay? So we grow them on glass slides, or if you want on silicon or something like that. And the beam scientist told us, gave us a sort of a substrate there on which we can actually grow. We did all that. But on the beamline, we are talking about now a beamline which is 50 nanometer in diameter, okay? We went all the way because we want intense beam, which is very, very narrow, and we can scan the beam across the crystallite and look at which phase is hiding where, right? Because we could be having orthorhombic, tetragonal, and a tiny bit of FCC also left over. Where is what? What is causing the pentatwin structure and all that? So to locate that itself, we had to work around with some magic, like for example, creating some markers. And this particular marker is made of platinum. And these are the tiny crystallites, if you can see on the screen. We were aiming for those, and you can see here, this L is written with platinum ink using an electron beam technique. And this is something which we could lay our hands on, and next to it our crystal, so something like this crystal we made use of, the tiny crystal there. The whole thing was mounted on the diffractometer, and it's all blind game now. You can't see X-rays, it's in the hull, from how do you make out? Well, what the beam scientists have done is they have X-ray fluorescence detector there, which keeps monitoring the L emission from the X-ray crystallite, the microcrystallite, and this is a gold L. And when you scan the beam across, you are also getting fluorescence from that. So wherever you see a fluorescence image appearing, like the one shown here, this is a fluorescence image, and this is SEM image. If I match, you can see that there's a perfect match there. I know the SEM image. When I get the fluorescence image on stage at the beam line, I know I hit the crystal there. And now what you have to do is, across the crystal, you have to plan to collect in terms of pixelite, spending time there. At each pixelite, you show the beam, collect the spots. Show the beam, collect the spot. Much like the Lave pattern coming from a nano volume, 50 nanometer in diameter, the beam, whatever it can penetrate. From there alone, you are producing the data. So you know how is the spatial distribution of various phases. And they all appear on this big screen. And this is something, such a pleasure to watch this. For example, on this big screen, you can see here a lot of these spots coming up. Leave out these white aberrations there. They are artifacts, and there are some stains here. In this kind of experiments, lots of stray radiation will be there. First, you need to calibrate and know what's the background and all that. And then you know these are the genuine spots coming up there. They are no longer sharp. One would expect them to be very sharp if you do have a single crystal, but they are not. You can see they are spread out like this. You can actually take the closer look at them. They're all spread out like this. You can see that, right? And what do we do with them? You see, when we have different types of crystals stuck in twinned fashion, you can expect such profiles for the spots, and you can go to K-space and look at what's happening. All the spots are supposed to be, if you were to be dealing with the FCC, which is a single crystal, you could be having sharp spots like this across this inner dark circle, okay? You could be having like that. If you do have other type of crystal lattices, then you could be having something like this, which is a red circle on top. I've drawn it schematically. This for a tetragonal phase you could be expecting, because in tetragonal we are seeing A equal to B, but its C is somewhat less than that of the FCC. Okay, so what happens in the K space is the circle becomes larger, right? And you may have mosaicity as well, because you're dealing with now pentatwinned crystallite, and there will be intensity spread also like this. This spread can become a measure of the mosaicity itself. And with a lot of discussion, again, one thing about synchrotron is it just throws out lots of data. It's like a James Webb telescope, You set it out and you have lots of data, you don't know what to do with it, you have to analyze. Like this, in 5 days, we collected around 2 terabytes of data. And after that, it takes weeks and months together to analyze what is what. Well, we had good help from the scientists across. This is where the India-German collaboration comes in. And a lot of online meetings, a lot of discussions through which we could actually figure out what's happening. So we could index them to what are genuinely coming from that 8-10% of FCC, and what could be the other lattice, like orthorhombic or tetragonal, what kind of lattices are involved there. And we could also draw a supercell. When we have a crystallite like this, FCC may be oriented in some fashion, whereas the orthorhombic phase may be oriented in a different fashion, right? So you need to create a supercell geometry and look at how the 2 unit cells are oriented with respect to each other. And we found that the angle between the 2 core unit cells are around 45 degrees. And they're all based on symmetric considerations, okay? And now you are scanning the beam across the crystallite. See, this is the fluorescence emission coming from there. I know the beam is there, and for that I'm getting a spot like this, okay, spread out like this. Q max, Q min, I'm drawing those circles based on what is, from powder diffraction we know what the orthorhombic lattice would exhibit in terms of the Q max for that particular reflection. This is the FCC 111. And what's the Q min coming from FCC itself. And when we scan, you can see the spot is moving down here, we are still watching on the same, I think I'm done with half an hour. Yeah, I'll take 5 more minutes, I'll just find it. So you have to be keeping a tag on an individual reflection, and where all it occurs as you rotate the crystal. We have only limited rotation because it's not on a paper or something, it's on a substrate, so you could rotate only up to 45 degrees. So this is in the other direction, and we are looking essentially at a combination of 0, -1, 1 of orthorhombic mixed with 1, -1, 1 of cubic, okay, at this particular spot, right? So these are, as I showed in the larger drawing, they're all symmetry related, and you can keep track of them. And also you can go on drawing some schematics to show you how the mirror reflections come about and all. Well, we are addressing a crystallite like this, so you can expect lots of surprises there. And here is the glossary. We have collected from this entire angle is up the order of around 40 degrees or so, and spots appear, disappear, again come back, because there is a logic there, because you have now these crystallites organized into pentatwin structure. So if one twin gets exposed and then its Bragg angle satisfaction, it satisfies to some extent, then it vanishes, and when the next twin appears at the same favorable angle, again the spot appears. So this we kept track of, and we had to correlate when a spot is absent, when it comes back again. By the angular gap here, you can see that I have written the 38 degrees, various spots coming and going. The summary is this, that the reappearance of reflections after 36 degrees, it amounts to nearly perfect pentatwin geometry, but we are seeing in a spread of 33 to 40 degrees. That talks about the disorder itself, which is shown here. Okay, so cross-sectionally, you can also make out from the microscopy that you expect such a spread from the tips. All right, I think I should be just closing now. Yeah, these are details. Let me summarize here that what we learned from this P06 interaction, okay, with the DESY work. We have, if you take this crystal, whatever crystal I'm talking about, I think most of them behave the same way. We have around 6-degree twist from one tip to the other. Okay, we have the tips which are pentatwin, but as one tip to the other, they are not well aligned. There's a twist of around 6 degrees. Okay, and then the crystal growth directions we could calculate. And what little FCC we found near the tip. Where is that? I thought I had that image. So the tip is made up of richly strained FCC. Strain is shown there. It's under compression of -6% and expansion of +4%. Okay, it's not a normal FCC, but it's strained FCC. And just beyond the tip, if you go into the core, you come across a lot of non-FCC content. And we have done some work on tachography as well. It's the next level experimentation. There's a lot to learn for me. I'm interacting with them, and this is progressing well. And perhaps in maybe in a couple of months we should be able to send out a decent publication out of this. These are the conclusions. This here is the image I was looking for actually. This is what the picture we came up with finally. See, the FCC is here at the tip, and entire internal core is made up of non-FCC. Okay, this, when I say FCC, this is also quite strained FCC. It's not the regular, happily grown single crystal FCC. It is not. It's grown under a lot of constraints, and it's distorted, under strain FCC, I must say. And in the core, the strain further increases, and that's the reason it phase transforms to other orthorhombic or tetragonal phases. And the rest of the things I talked to you. If I can get one more minute, I want to just show you. I had shown you aqua regia, right? Now that we have understood that the tips are made up of strained FCC, why it is not giving up in aqua regia? It should give up, right? So on extended treatment, what we see is the tips are chopped off. Only the core remains now, right? You can see here, a lot of these crystallites have lost their head and tail both. Only the body remains. And this body is now 100% non-cubic. So we could finally synthesize entirely gold in entirely non-cubic phase. Well, having done that, a lot of chemistry can be done. I should be winding up now. You have FCC and non-FCC in the middle. You can bring other type of metals. This is all chemistry, okay? You can bring in platinum, copper, and you can create dumbbell shapes and all that. See, that's the fun, actually. So I must thank my colleagues, my students, and other colleagues around. And Vimesh Wagmare, Shobana did a bit of theory. Chandravas, as I said, he helped along with Ajay Shukla. Milan has been in the background all the time with us, in discussion, writing proposals for Synchrotron. And getting a proposal through is not that easy. I must say that, okay? So whichever comes accepted, we happily fund it. But till that stage, it is tough. Kanishka also knows. The first review takes place at, correct me if I'm wrong, first review takes place at the DESY itself, okay? And they send out that this project proposal is acceptable. Then the Indian review team takes up. Am I right, sir? I'm asking Professor Kanjilal. Yeah. So it's quite a rigorous process. And with that, once approved, it comes to JNC administration, and we fund the project. Here, I thank my students, and it's sad to mention that we lost Gangaya in an accident. Yeah. Thank you very much.
We'll make a few questions.
This structure is very fascinating, but did you try to look at the properties like how does the color look? Gold color,
Yeah.
change with the structure?
The conventional gold is yellowish, right?
Yeah.
This is a bit oranges.
I see. So the non-FCC, I see. Okay.
Yeah.
But is there any other property that you looked at?
I must tell you a story behind this orange color. If students have questions, they can ask, but otherwise, yeah, these gold companies called me because it became national news, international news, and all that. No? New scientist interviewed me. Gold, come on. So, Titan company, they called us, and we had a day-long meeting. Then finally asked how much you can produce. I told 18 milligram. They thought they will appoint somebody to work with me, and all. They tried actually 6 months. But scaling up, there are lots of challenges.
Yeah. But did you try, like, say, for example, transport or any other property, how they behave?
Yeah, we tried simple making connections and looking at the transport with temperature and all. Free electrons are still free. Yeah. But one has to look at it carefully. They're all. Yeah, we have, we routinely, in fact, I'm a device man, so we keep doing, yes. It's not, these are big 10 micron length, so it's not very good. Questions from students here?
Generally, it is perceived that.
Very good.
So generally, it is perceived that the strain is higher towards the tip side and then less strain towards the core. In your case, it is other way around.
General means in which case you are talking?
In most of the cases, if we are talking about nanomaterial or nanostructures, the core is generally less strain in comparison with the surface.
I'm not too sure of that, but I can explain to you what's happening here.
Yeah.
See, the pentatwinned, whatever tip we have, they are small by size, and they are towards the end, they can relax. Whereas the ones which are caught up in the middle, they are twisted, they are big, okay? We have talked about the growth itself in great detail. Because of that, they hide a lot of strain inside. And when they cannot take it, 220 degrees I told you, the 10-degree temperature window and 30% silver is important to push it to 92% of monoxide. They are all playing the role there to create enough strain in the growing crystalline that it faces to monoxide. So it is in the body itself, not at the tip. Tip can relax. There is nothing to prevent it.
Any theoretical calculation must have been done.
As I said, Umesh has done, that's a part of the JAX paper, and Shobana did one in nano research, and Anguchem also we had some colleagues from US. But the students are not, I'm sorry, students are fresh, new participants. All known faces are asking. Which will go ahead till they make up their mind. Yeah. This is a wonderful question. You see, when you have small crystal, there is not enough strain to push it to go to other crystal forms. It will become more and more strained FCC, but it will not face also. We have the data, we have published also. The unit cell goes on drifting with all the strain built in, but still the symmetry is the FCC.
Sir, it is what multiple layers stacked together in the middle, right?
We don't have evidence of that.
Can you try to do FIB, like you said, try to cut it in thin films from the middle. And so what was that? Like it was layered or something? Like
No, we wanted to slice it. So we want to prepare the sample for high resolution T. But the FIB caused sort of melting, you can say, melting of the phases.
So we don't know what in the middle, how they are stacked. It is basically multi-layer, like many layers stacked in the middle, or somehow it's going
the geometrical aspect of how they are stacked in the body of the crystal.
in the middle. Well,
that's why we are on to now typography. Okay, that will throw the actual individual orientations and all much more clearly. It's the imaging technique, direct imaging technique it is. So we are looking at that. It's like TM, so to say, but at that level. Typography is used in medical imaging and lots of fields. So here it is nanotype, working with X-ray beamline. And now we don't, based on this study, we don't have that. All that we know is to what extent other than FCC crystal phase exists, and what are the unit cell parameters and other type of strain parameters.
Okay, if there is no more questions, let us thank Professor Kulgeet for giving me questions.
Now I request Professor Chatterjee to present a memento to Professor Kulgeet.
Our next speaker, Professor Utpal Kumar Gautam from Aizawl Mohali. He will deliver on NAD materials for clean hydrogen products.
Okay, I think anyway we're running short of time, so I can just do the first formalities. Let me thank you for the introduction, and also many thanks to Kanishka and Sanjay for this wonderful invitation. And I think we already had two very interesting talks so far. So even I was not very sure what kind of talk I should be preparing. So I prepared a very heavy talk. But it so turned out that the first talk is related to XPS. So my first part essentially goes away. And then second part is also about nanocrystals. Professor Kulgeet talked about it. So I'm going to get rid of it. So I'm going to basically talk about oxides, which has not been talked in detail. I'm going to discuss about high pressure studies. But if it comes immediately, I'm going to summarize in 2 minutes the first topic. So, all right, so I talked about materials, so it's going to be just one material. First, let me formally thank India-DESY cooperation, because not only me, but my students are immensely benefited by this project. Also thanks to DST for this wonderful initiative. Thanks Aisar Mohali and my students and my collaborators and funding agencies. So the first paper I wanted to discuss, which I'm not going to discuss it because this is my first experience with beamline, where we did XPS studies with high energy beam. And the second work, again, which I'm not going to discuss, is about exact beamline, which we actively use, because we make electrocatalyst and we want to study them different aspects, including in situ studies. But I'm going to talk about piezo-catalytic hydrogen generation today, where we have used the high pressure beamline. So very briefly about the first work, we have already seen works on nanocrystals, and this is about, again, about 2 nanocrystals, which looks pretty ordinary, about 4 nanometer in size. They are made by the same method, but the only difference in this case is that we use PVP as a capping agent, because when you want to make small nanocrystals, you have to put a shard on top of it. You have to cap it with something. So in this case, it is PVP. Now they have similar size, but they have very, very different properties. I'm not going to discuss in terms of catalysis. These are phenomenal numbers, and so we have patented this, and this is across various reactions. So we have two catalysts. One is very good, the other one is not very good. Whereas they look same if you do all different characterizations. For example, XPS, lab scale XPS, XRD, electron microscopy, and the only difference is PVB. So it gives us an idea that the way PVB is sitting on the surface is playing some game. Now, when we talk about catalysis, what is generally talked about is the electronic structure and how the electrons get transferred from a catalyst to the reactant. Because that is how a catalyst, a particle takes part in catalysis. It has to transfer electrons. Very briefly, we thought that this is not the only thing which takes place. We must take into account the diffusion across. If you look at this nanoparticle, for example, this is a theoretical study. You can see there is a ligand cell. We wanted to find out how the reactants diffuse. So it is something like traffic jam. So you might have a very good hall, or you might have a very good catalyst. If the reactants do not reach the catalyst surface, the reaction is going to be slow. But we wanted to find this one. There are two constraints. One is that the two particles must be similar. The only difference must be on the cell. And they must have similar size already. And then they must have similar charge transfers. Okay? Then only we can figure out that the difference is only coming from diffusion. So, and which nobody has looked at that point of time. We kind of figured out that in one case where you have a long PVB, there is at an average one PVB molecule attached to one particle. In the other case, there are 4 PVB molecules attached to one particle. But if you look at the carbon numbers, we have palladium roughly about 10,000 and carbon atoms roughly about 3,000. So they are more or less very similar. So we developed, we use impedance spectroscopy to find out the diffusion coefficients across these ligand layers. Usually, sometimes you can do it using NMR spectroscopy, but it has two constraints. One is the concentrations has to be high, and they do not like a lot of metals, because if you have a lot of metals, the NMR fails. So, if you see here, they have the same charge transfer abilities. Okay? But if you look at the impedance spectra, we'll skip it, but you can eventually calculate the diffusion coefficients, and we estimated the diffusion coefficients, and it shows that more or less the reactivity scales with the diffusion coefficient, these ligand cells. So one of the very critical questions the reviewer asked is that you must use different energy radiations to find out XPS, and you have to show that particles are exactly same, and which we used the DESY beamline, and you could show that if you use either lab scale laboratory XPS or if you use high energy XPS, you get the same XPS spectra. That was one of the questions. All right. We saw some nanowires and safe controls. So we make safe control nanostructures, palladium nanostructure again, and we want to use them for electrocatalysis. It's a very interesting and funny example. If you look at why catalyst goes bad, there are particularly about 2 or 3 reasons. And if you look at this schematic, you can see here, if we look at here, some atoms are going away. It is called leaching. Leaching is the first mechanism through which a catalyst goes bad. Because this catalyst, which is on the surface, is highly active. It is exposed. The second mechanism is called particle fallout. Because when this is an electrode, okay, and these are the catalyst particles. So when current passes from electrode to the catalyst, electrodes are normally carbon. So you have Joule heating because these contacts are not perfect. So when you have heating, you have water, carbon, carbon dioxide. So carbon corrosion happens. So when carbon corrosion happens, this particle is not very tightly attached to the electrode surface, then it falls off. The third is what is called electromigration. When the electrode gets heated up, these particles move and they agglomerate. So we designed this kind of wires, the wire-looking particles. The idea is something very similar to what you see here and which we often encounter in bathrooms. If we have long wires which interdigitate, we have multiple benefits. The first benefit is that if you have particles, if you put them together, they will all agglomerate. And then many of the particles will be actually hidden behind and are not exposed to the electrolyte. If you have this kind of nanowires, whenever they interdigitate, they will have always 4 to 5 nanometer sizes of holes through which particles can, liquid can always go inside, electrolyte can go inside. So nearly entire interface is exposed to the surface, to the electrolyte. The second advantage is that because they are like this, they are very robust, they are very strong. The third advantage is that even if in one place the particle comes up, it must be connected to several places. Okay, it's a very conducting network. So even if one side comes up, it is still conducting and it will still contribute to electrocatalytic activity. So these are the nanowires. We have done exact studies because there is one very critical question is that when you do these electrocatalytic reactions, one of the species, this is very critical, is oxide species, surface oxide species. So we figured out how to find a surface oxide species when the reaction is going on. I'm not going to explain it. We have used it for different parts of the fuel cell, okay, for the cathodic reaction as well as for the anodic reactions with some fantastic activity plus fantastic stability. Then we have moved on. We are trying to make a electrochemical fuel cells, the real fuel cells. Now this game is going on for about last 20 years. But if you look at the literature, last 3 to 4 years, what has emerged is that this catalyst, when you put on a fuel cell, its efficiency goes down by about 95%. And there are various reasons why it goes down. I'm not going to discuss because the reaction conditions are very, very different in laboratory scale when you use an electrochemical workstation versus when you make a device. One difference is the temperature. Because when you want to do a fuel cell reaction, you produce water and you have to make sure that the water evaporates. So the reaction normally happens about 70 to 80 degrees centigrade in fuel cell. But normal electrochemical characterization you do at room temperature. Now if you look at chemistry principles, you understand that when you increase the temperature in an isothermal condition, the reaction rate must increase. So we can safely assume that catalyst must be performing better when you go to high temperature. But in reality, these reactions are not a single step reaction. There are at least 6 to 7 intermediates. Okay, there are multiple reactions. And let me stop there. We have started working at variable temperature electrochemistry. This kind of study doesn't exist at this moment. But the results are fantastic. One of the very interesting results we figured out is that when you use platinum, it becomes increasingly poisoned by OH groups when you go to higher temperature. But if you use palladium, the reverse thing happens. For example, I'm not going to explain this, but you see that this trans becomes opposite. As a consequence, So, and we figured out why this happens. was if you use palladium instead of platinum, actually in fuel cell it is much better, whereas palladium, platinum is the commercial catalyst. It is about the fundamental property of palladium versus platinum at higher temperatures, something we discovered and found to be very, very interesting. So now we want to do in situ studies and see this how catalyst surface get covered by OS groups. So, all right. So how much time I have? 10, 15 minutes? All right. So, there is another emerging area that we have started working. It's called piezo-catalytic hydrogen generation. So, in this part, I'm going to show you that we introduced a new family of compounds for green hydrogen generation. And then there is something very unique because of which we need to use high pressure cells. Now, what is piezo-catalytic hydrogen generation is something very simple. All of us, we have used sonicators, Bach sonicators. Now, if you take oxides, most of the oxides, you need to use an oxide which is non-centrosymmetric. And if you start sonicating in water, you start getting hydrogen. It's a lot of hydrogen. Now this has many advantages because you can use oxides. If you do photocatalysis, you cannot use oxides because oxides do not absorb light. They absorb in the UV range, not in the visible range. If you use electrochemistry, you're going to use something like platinum or palladium, which is very expensive. But oxides are very robust, they are inexpensive. And this process is very simple. We do not need any special setup. So I think we kind of understand what is piezoelectric materials. They have the ability to convert mechanical energy to chemical energy or vice versa. So they have to have a non-centrosymmetric crystal structure because when you put mechanical force, when you compress them or when you expand them, they have polarizations which do not cancel out within the unit cell, and that is why it gives rise to surface charges, positive charge versus negative charges. So, for example, you can look at this. Assume this is a crystal. And if you look at a crystal, and this is a non-polar crystal, if I start putting pressure, this will develop positive charges and negative charges on the two opposite sides of a crystal. And when you have excess charges, these charges are stable for several microseconds. They are able to do catalytic reactions. And for example, if you have electrons and you have a proton, it is going to give hydrogen, and that hydrogen comes out as hydrogen molecules. Now we are left with one problem, that we have to apply pressure. So this is where ultrasound comes into play, ultrasonic baths. If you see the mechanism through which ultrasonic bath works, it forms cavitation bubbles. Okay? The ultrasound is something like this. You have expansion, you have rarefication and expansion. This is how sound moves. Now, when you have rarefication, you can assume that it is something like forming a bubble because you have very few molecules in that region where you have rarefication. When this process continues, these bubbles gradually grow until a point comes when the bubble bursts. You can see here, when you put ultrasound in water, these bubbles grow with time, but at some point of time, this bubble breaks. Now, when this bubble breaks, you have vacuum inside, kind of vacuum inside. This molecule very forcibly comes inside. So the kinetic energy of the molecules are very, very high. And kinetic energy, in some sense, represents temperature. So the effective temperature when the bubble bursts is very, very high. In addition, because these molecules come very fast, if there is a catalyst particle there, it's going to exert pressure on this catalyst particle. Okay? You know pressure, the force is not mass, but this particles are also very small. So force per unit area, the pressure is extremely high. And this gives rise to piezoelectric properties, this charge generation on catalyst surface and hydrogen generation happens. Now, why is it renewable? There are two ways this can be made renewable. One is that if you simply connect it to a solar cell. The second is that these ultrasonic waves are widely available in sea source. If you look at the sea source, we always hear this sound, hiss sound when you go to a sea beach. But if you see the fraction of sound that you do not listen, or you do not have the ability to listen, it has large amounts of this ultrasonic waves. You can also create it. If you have a stream, if you put some metal masses, which can create these bubbles, okay? When these bubbles break, it also creates, this has been experimentally demonstrated that you can create ultrasonic waves like this. When a stream flows and you put particular kind of mass to obstruct. So, so it can be made renewable. So for example, if you go to seashore and if you start splitting water, you do not need any other source. And it can work at night, unlike photocatalytic approaches. Now, let us briefly look at how it works. Okay, this is a very, very primitive, simple schematic. So we have conduction band and valence band. These are oxide materials. Most of them are oxide materials. Now, these developed charges, as you can see here. Now, if you see here, these charges, we have positive charge and negative charge. Now, because there is a charge generation, what happens is that within that crystal, when the electrons are close to the negative charges, their energy becomes high. Okay? And when they are close to the positive charges, their energy becomes low. So essentially what you feel is that when you have a catalyst, within the catalyst, the band bends. Okay? On one side it has high energy, on the other side it is lower energy. So with pressure it is something, without pressure it is something like this, with pressure it is something. If this one sufficiently bends, okay, these valence electrons become sufficiently high in energy that it can start giving electrons to the proton, which can happen. Proton reduction potential is 0 volt. So if it is more than 0 volt, it can start giving electrons. Now so it involves only valence band electrons. Okay, it involves band bending. Okay, so it is something like electrocatalysis, because in electrocatalysis also you use only valence bands. But the advantage is that you can use insulating materials. Now look at these oxides. You know, they are typically semiconductors. Okay, so proton reduction happens somewhere here, and their valence band is somewhere here. So typically this band has to bend by about 3 electron volts, 2.5 to 3 electron volts. Why I'm telling you is that I'm trying to connect it to the pressure that we can get in beam line. Okay, so this is a relation through which you can figure out the voltage it develops on the catalyst surface to the thickness of the catalyst and the piezoelectric coefficient and the pressure. Okay. Now, if you want to get something like 3 volt band bending, okay, most of the piezoelectric coefficients are of the order of 10 to 75 picometer per volt. So if you plug in all these values in this equation, you see that you need roughly pressure of about 0.1 to 10 gigapascal, which is not possible to get in laboratory. So we have to use, if you want to study the material at higher pressure, you need to use synchrotron. So, how much time I have? 8 minutes, all right. So, I am going to skip this. So, we introduced a new family of compounds for piezoelectric CO2 splitting. It's called cylinder-revealous phases. It's a fantastic material because if you look at its formula, you can see that you can have many different kinds of cylindroblast phases. So you have a lot of flexibility. So it's a combination of two phases. One is the silane phase, the other is the aeroblast phase. Okay. All right. So just to mention that this is something called PFM, and if you do, it is a technique, derivative technique of AFM from piezo force microscopy. From here, you can see when you apply pressure, you can directly see the displacement. Okay, that is, if you put pressure, it shrinks. Okay, and from there, sorry, when you put voltage, not pressure. Sorry, when you put voltage, it shrinks. Or if you shrink, the voltage generates. They are both connected. From there, you can directly calculate the piezoelectric coefficient, which is called D30. And it's very simple. You know what is the displacement, you know what is the voltage. So displacement versus voltage. And you get picometer versus volt. Okay? And this is, for example, 50. So the range is about 10 to 75. All right. So this is how we make the cylindroblast phases. You can see here. So we did some control experiment. We started using the materials which we use to make the piezoelectric. BiOCl is one of them. And quite surprisingly, BiOCl gives very high amount of hydrogen. It is even better than the catalyst we actually reported. And then you can look at the PFM data. It clearly shows that it is again piezoelectric material. Because this is unexpected, because BiOCl is a tetrahedral structure and it is non-centrosymmetric. It is not supposed to give this. So here is the crystal structure. It is a layered structure. Okay. Sorry, it is a tetragonal structure. It is a P4 by NMM. It is space group. So if you look at the crystal structure, you can see two layers. Okay, two layers, and two layers. In each layer, bismuth is connected to 4 oxygen atoms and 4 bromine atoms. So 4 oxygen in the top, 4 oxygen in the bottom, but they are twisted. And in the bottom layers also it is similar. So if you look at independent layers, they are centrosymmetric. But if you look at the unit cell, you have to have two layers. So the so it becomes centrosymmetric because polarization cancels out in the unit cell. So there are two. The first thing that came to our mind, probably when you go to high pressure, because we have to have high pressure in piezoelectric conditions, there might be a phase transition. However, at that time, in literature, high pressure phase is not known. So, we went to the beamline because we wanted to say what happens at high pressure. So, as I was explaining, this is how it looks. It's called diamond angle cell. The rest of the things are similar, not same. It is somewhat similar, but it uses the same diffraction law, n lambda is equal to 2d sin theta. This scale is different because wavelength is different, but otherwise, if you have experience with single pressure order XRD, it is something very similar. The advantage here is that you put your sample somewhere here. When you put your, and this is actually looking very big. In reality, if you look into this, this is extremely small. It is about, say, 10 micron. And you know that pressure is force per unit area. Because this area is very small, the pressure becomes very, very high. It can generate very high pressure. But the problem that you cannot do this experiment in normal laboratory setups is because if such a small sample, okay, you can put very little amount of sample, which you cannot put by your naked eye. You have to use a microscope. Now, when you use a microscope, such small amount, you do not get sufficient intensity that you can measure. So you need a very, very high intensity, and which you can access in beamline. So we have to do these experiments in beamline. So these are the experimental patterns. You see that the pattern do not change. There are two peaks here which are merged, along the A-axis and along the C-axis. Because it is layered material, the C-axis it compresses more compared to A-axis. These two peaks split, but there are no different, no extra peaks, except something. You see a few peaks which comes because of the pressure transmitting medium, which is neon in this case, which crystallizes at high pressure. It seems to get stuck sometimes. So, however, so you have this XRD pattern. From XRD pattern, you can derive information about A, B, C parameters. So, here is a plot. You can see the C parameter and A parameter are plotted against pressure. So you see that this parameter changes and you expect that they are going to decrease because you are putting pressure. They do decrease. And this is the C by A ratios. Now what is interesting is there in about 15, 16 gigapascal, okay, the way this value changes, okay, first it looks like something exponential. It's not exponential, but to naked eyes it looks like exponential. After that it looks like it is straight. So if you see something like this, it is in literature called isostructural phase transition, okay? Because their compressibility changes, their properties changes, okay? So this is, so in the other sense, we have a high pressure phase and we have a low pressure phase. For example, if you extrapolate it to zero pressure, it is going to show a different phase compared to if you extrapolate here. So there is a high pressure phase and there is a low pressure phase. What happens is that by the time you reach a high pressure phase, okay, you can look at the crystal. These bonds, which are not bound initially because it's a layer material, they start forming robust bonds, okay, and there you cannot compress them anymore, okay, they become robust, and that's why the compressibility changes around 15, 16 gigapascal. Okay, I'll skip the details, but essentially our pressure in piezokinetic conditions is somewhere here. But this is stuck. Okay. Yeah, it's one slide is just one. So I'll skip the details of theoretical calculations, how the structure changes when the phase goes from low pressure phase to the high pressure phase. It has many advantages. It becomes more stable at high pressure. One of the reasons is that, you know, we have conduction bands and valence bands, and these conduction and valence bands are contributed by different orbitals. Okay. Now, valence band in this case is primarily contributed by chlorine and bismuth. Now, what happens is that when you go to higher pressure, it predominantly becomes oxygen-based, and oxygen is very stable compared to chlorine because chlorine leaching is possible, but it is easy, but oxygen leaching is more difficult. So the structure becomes stable. We'll skip such discussions. So this compound is well known for having defects. Okay, PiCl is a very good photocatalyst, for example. Everybody knows, but it is very bad because it has lots and lots of defects. Chlorine very easily comes out, oxygen easily comes out, and then you have problems. Now, there's a very interesting paper come at some point of time when you're looking into this, that in Syria, okay, which is again a centrosemitic system, when you have oxygen vacancies, it's piezoelectric properties shoots up like anything. So we started, then we got many papers, we started looking at defects. Okay? This is an XPS spectra, and first we discussed XPS spectra for oxygen. And if you look at this, if you see 3 oxygen peaks, okay? This is the lattice oxygen. This is the oxygen surrounding an oxygen vacancy. And this is absorbed moisture. So this clearly shows, okay, that we have oxygen vacancies. Okay. Now, when you have oxygen vacancy in lattice, okay, that oxygen must have been previously bound to a metal. When that is gone, the metal gets distorted. It goes away from its original site. So that particular unit cell becomes no more centrosymmetric. It becomes non-centrosymmetric. Okay, and these are theoretical calculations. You can basically see an additional charge is coming up, polarization coming up in the center because we have put a vacancy in the center. And if you look at the dipole moments, so at all pressures, okay, at all pressures, we start seeing dipole moments in the centrosymmetric crystal. So we kind of know now it is coming because of oxides, but we still have the job to prove it. So there are 3 different samples with 3 different oxygen levels. Okay, you can see here XPS spectra. We have more oxygen, medium oxygen vacancy, and very little oxygen vacancy. When we have very little oxygen vacancy, okay, hydrogen coming out is also very less. When you have medium, it increases, and when we have lot of oxygen vacancies, we have more oxygen coming. There are other ways you can check, for example, repair spectroscopy, positron annihilation spectroscopy. By different ways you can confirm. And the same things can also be checked with taking, for example, BiOCl, that was behavior. So essentially what we showed is that this beamline studies on high pressures was extremely important to decipher essentially what is happening. Otherwise we would have never resolved this problem. Why? Whether it is because of vacancies or it is because of some crystal structure change. So we have many new similar structures, and we hope to use beamlines in the future. So thank you. Yes. Yes, a few of them I have checked. It's a very interesting point. For example, just again analyzing the structure itself, if we use the Birch-Morgan equation and find out the properties. For example, compressibility is very, very different in both cases. So you can see here, okay? And the V0, the value, expected value at 0 pressure are also very different. So compressibility is different. I'm sure that, for example, different conductivity along the x-axis and y-axis, the ratio at high pressure and low pressure is also going to be very, very interesting.
How good is the simulation of implosion and doing hydrostatic pressure experiment?
They are very good actually. I have it next slide. So you can see here. Almost matching 1-to-1.
Thank you, sir, for such a nice talk. My question is that can we combine it with the photocatalysis and electrocatalysis?
Yes, yes, we can.
Second question is that what about the mechanical stability?
What is?
Mechanical stability.
Yeah, very interesting questions. So So we just published one paper, our recent paper in chemistry materials, you can see, and we have shown that typically people show it for 8 hours, 12 hours, or maximum 16 hours. So we have a paper, we have shown up to 160 hours, and there is absolutely no change. It remains the same. And the first point is again something very interesting, because when you use photo and piezo, you get something very high synergy, extremely high synergy, something that you really cannot expect. And again, we have one paper where we have explained the origin of synergy in such systems.
Thank you.
Okay, if there is no more question, let us thank Professor Gautam.
It is one more question.
Yeah, I'll just ask you during the tea time.
Yes, go ahead.
Oh, okay. So I was actually asking about how to handle the diamond angle cell. I mean, how are you so sure that the X-ray, which are incident X-ray, are not coming from the cell rather than from the sample? How can you say that?
Very good question. But that is very simple, because you know your X-ray structure of your sample. There are a couple of things. There is a tiny hole. If you look at the cell, okay, it is much smaller than the ring that you put here. It is smaller than that. But if you look at the microscope, there is a hole through which there is also a ruby crystal. When you put your sample, you have to put a ruby crystal, because the ruby crystal's spectra, okay, photoluminescent spectra changes with pressure. The pressure that you apply is not the actual pressure it experiences. Okay, so to recalibrate, you have to put a ruby crystal in it. So its fluorescence changes. Now, when it fluorescence changes, you need a way to measure the fluorescence. Okay, there is a spectrometer. To see the spectrometer, if you look at the crystal, there is a tiny hole. It is not a hole. It is covered, but one part of the diamond is uncovered, which is very, very small, but with microscope you can see, through which you can see your crystal sample.
I want one comment on that. What is the kinetics of the production kinetics of hydrogen? If we talk about HER,
Yes.
you are saying this acts as a somewhat electrocatalyst. Then what is that kinetics?
Okay, very quickly, because I have experience with all three of them. So, because all three we do in our lab. In terms of photocatalysis, it is at par or slightly higher. But it is, they are not comparable, because you are not putting the same amount of energy. It is energy input versus output. Okay, the Barsonicator that we use are not optimized. It is not customized for this purpose.
What is the method of that? In this case, how we can measure? Actually, we are not measuring anything.
It's like
there is a production of hydrogen.
You take this one and you put it here, the catalyst. Then you have to, of course, connect it to a GC to check the amount of hydrogen.
Now I request Professor Chatterjee to present a momentum to Professor Gautam.
Last speaker of the session is Professor Sanjay Singh. He is from IIT-DESY, reviewers on quantum material. His topic is application of synchrotron techniques in information technology.
organizer, I should thank first to DST to provide fund so that we could organize, and GNCSR. So earlier I was thinking that I am convener, I to give talk, but I don't know you have to give. So thanks to all. So today, this is the topic of my talk. So today I will be basically introducing a problem and will show some of the example that how we solve this problem using the synchrotron technique. Okay? So basically its application for the incommensurate phase transition. So I will go. And as there may be questions, so in our lab we are working in different fields. Different fields. So this slide I have put basically that all the students and PhD and postdocs, they can see that we are using the synchrotron technique in all these fields. So it's not in a particular topic of the field related, because morning many students were telling, sir, हम तो chemistry से हैं, so हमारे लिए useful नहीं है, इसलिए हम नाश्ता कर रहे हैं. So it's not like that. Okay. So please. So they thought that this is mainly for physics. So we are working in different fields, and so you can see here almost 70% publications in our lab comes from the synchrotron. And we are working and in different fields, you can see. Okay, so this is the outline, so some basics for the students mainly, and then I will show some results and then conclude. So 3 important points I will mention here. So let's start. So we have a diffraction pattern. This is mainly for students. Any of you can tell what is the difference between these 3 diffraction patterns? No? Okay. So let's hope after my talk we will be able to answer this. Okay. So let's come for the fundamentals. So the crystal definition. If anyone asks what is crystal, what we say, if you see, so anyone? Crystal, what is crystal? From back side. Huh? Periodic? Arranged molecule, highly arranged molecule in space. Okay. So if you see the famous book of this condensed matter physicality in 1959, a solid composed of atoms arranged in a pattern periodic in 3 dimensions. This is the textbook example what we read in DSC, MSc or BTech. Okay? And then Barrett. Then, but something happened in 1982 and the definition in the Charles Kittle book itself changed. Okay? So now the book says the crystal what? So we can make a crystal from molecule which individually have 5-fold rotation axis, but we should not expect the lattice to have a 5-fold rotation axis. Did anybody get something? Anything? Okay. But book, if you see the definition, it's kind of 3 idiots the machine definition. I could not understand from this line. Okay. So there was a confusion that time because of the invention of quasi-crystal in 1982. And then the International Union of Crystallography gave a new definition of the crystal, that by crystal we mean any solid having essentially discrete diffraction diagram, and by aperiodic crystal. So now periodic and aperiodic crystal, the whole things change. That aperiodic crystal we mean any crystal in which 3-dimensional lattice periodicity can be considered to be absent. Okay? So periodicity is not necessary. And today I will be talking about incommensurate modulated crystals, which comes under the category of aperiodic crystal. Okay. Okay. So just for the students, mainly my introduction is mainly for the PhD and postdoc. So modulated crystal, what means? So normally, if you see that if you have a normal crystal, it's periodic. So I have given example of 2 dimensional. So it's periodic. You have lattice parameter A1, B, A2, and then you have a unit cell rectangular. You repeat this unit cell, you get the crystal. But if because of external stimuli, these atoms may change their position. So there is the first example. The right side, if you see, the atoms move slightly left and right. But still, if you follow properly, we can have a unit cell which is 2 times of original unit cell. But still you have the periodicity. So this is called commensurate modulated crystal. But if you see the downside and you try to find a unit cell, it's impossible to try to find a unit cell. So there is no periodicity. Okay? And these kind of crystals are known as, normally it's incommensurate modulation, and if it gives the split diffraction pattern, we call incommensurate modulated crystal. But this is the definition. We all know the XRD, X-ray diffraction pattern. So it's normal 2-dimensional XRD, 1-dimensional pattern, what we see. In normal crystal, we have well-defined, very bright diffraction pattern. But in case of modulated, we have very tiny additional peaks. Okay? And I will show you how synchrotron is important to understand the structure. But this is the real space. What is happening in the reciprocal space? So in the reciprocal space, I have compared crystal and modulated. So what you see, with black, very bright spot, equal intensity, you have other spots in between these two, and their intensity may vary, and their space between these spots may also vary. So if space is equal, then it is periodic or commensurate modulation. If it is unequal, then it is aperiodic. Okay? But now, if the crystal is aperiodic, then we cannot understand based on the normal 3-dimensional crystallography approach. You need to move to the higher dimensional crystallography approach. That was done for the quasi-crystal. So normally what we have? We have reciprocal lattice vector. We give HA star, KB star, LC star. It's normal. We have HKL, we all know from our fundamental knowledge. But in case of modulated crystal, you need additional vector which is called wave vector, and then you have this M, which is MQ, H plus MQ, H for 3-dimension and then MQ is 4-dimension. And if you see the diffraction pattern, then M is telling about the degree of, basically order of satellite reflection. And if all are rational, Q1, Q2, Q3 of this Q value, then it is commensurate. If at least one is rational, then it is commensurate. Okay? And then you also get the position which is modulated by a periodic function. Now this was the basics. Now coming into the system magnetic state memory. So it comes from the standard state memory effect. The state memory means in general, we might have encountered issue that if you have anybody is having heart attack, okay, then what are the 2 possibilities of with the doctor? What are the possibilities? How doctor treat the heart attack patient? Bypass surgery? Stunt, yeah. So that's angioplasticity. Okay, so the stunt is your shape memory alloy, and the effect is called shape memory. So it's remember is shape with respect to temperature and with respect to pressure or stress. That with respect to stress, it is called superelasticity. That is used in the stunt. But this is with respect to temperature and pressure. But now, if your system is magnetic in the low temperature phase, the low temperature phase is basically the Martensite phase. I will not go into much detail, but remember, if you might have seen the war movies, Hollywood war movies, and then what soldier used to do, they take their sword, red, they put for the red hot, and then quench in the water. It gives the hardness to the shot, and that hardness comes from the Martensite. Okay, so it's from very beginning it's important. And the steel industry is completely depends on the Martensite phase transition. But suppose your material is magnetic, then the magnetostructure comes, the coupling comes through. So you have this small spin domains, and then these yellow and red, they are the Martensite domains. So suppose you have weak magnetostructure coupling and you apply magnetic field, this H, then what happens? The magnetic moment will try to align in the direction of the field, but nothing will happen with the structural domain. But if you have strong structural and magnetic degree of freedom coupling between structure and magnetic degree of freedom, then if you apply field, your structural domain also try to align in the direction of the field, and you have large strain. And this strain, so if you see normally magnetic actuators which are used, the strain is 0.1%. But these materials give strain up to 10%. It's very huge. So they are very important. So now coming to the our materials, it is Ni2MnGa. So just the take-home message that it's very famous system which gives the 10% magnetic field in your strain, and it shows the phase transition. So one magnetic phase transition, other is Martensite. Together with this, it also shows another interesting effect, which is called pre-Martensite phase transition. So Martensite is structural phase transition, or pre-Martensite or precursor effect is important because from, you can say, last 4 or 5 decades, it is told that it is a structural phase transition, but cubic symmetry is maintained, which is fundamental mystery. Okay? And I will show that we have solved this fundamental mystery also after 60, 70 years. So we have different phases, and these are the open questions in this system. First, the low temperature Martensite phase, whether it is periodic crystal or aperiodic crystal, in a broad sense. Second is controversy about the physics of the modulation, which is whether it is governed by adaptive modulation, means adaptive, if people are working with the metallurgists, whether it is related with the stacking fault, means there is no fundamental micro level physics is involved, or it is related with the soft phenomenon mode, where you have change in the band structure and electronic structure. Okay? And another mystery is about the pre-Martensite phase transition. As literature says that it is precursor effect, but cubic symmetry is maintained. So something is confusing. We try to solve this. And we have solved all these problems using synchrotron X-ray diffraction technique. Just to take home message that why, again, modulation. Modulation is important in this system because it has been observed that if no modulation, no reversible magnetic field is restrained. So that's why understanding modulation is important. Okay. So now we are coming to our result. So first, so we have prepared the sample. We saw we have phase transition, all 3 phase transitions we observed, and then went to the synchrotron. So you see, if you see the normal exciting pattern, you will look very large peak, okay, sample, our sample is cubic. But if you zoom, what you observe in the second right panel, the second figure, is smaller intensity. And it is a very special case. If you just compare the top one, 300 K temperature, and this 30 K temperature, the main peak looks exactly same. There is no change in the intensity. There is no splitting of the this break peak. Means structure must be same. Because we know from our fundamental knowledge, cubic है तो A equal to B equal to C. If it is going tetragonal, then A equal to B not equal to C. So you must see, if the symmetry is lowering, you must see the splitting of the peak. But here we don't see anything. Okay? That's the fundamental thing. And if you go to Martensite, you have clear phase transition. So we observed all the phase transition. But now, what is the structure, commensurate or incommensurate? So we try to people might be working with the sample preparation. So first thing what we do the XRD and try to fit with the level, integral, something. But if we try to fit with the level, what you say? If I show just the big curve, okay, and report in the paper, our sample is single phase and everything is fine, referee will be happy. But if you zoom it, you see very small intensity peak, there is clear mismatch between observed and calculated. Okay? And whatever you do, you will not able to fit. This indicates that the standard 3-dimensional crystallography is not going to work. and we need to move to the superspace functional, means the modulation wave vector change. And here I have compared. So in this case, you can use the modulation wave vector, rational or irrational number. So if you see, if you use the 3/7, you still have this mismatch, and when you vary the modulation wave vector and it comes to a value which is kind of irrational, then observed and calculated peak profile are matching. Means it is incommensurate. And so this is the first answer we got, that it is incommensurate. But what times, 7 times or 6 times? This we can get from the reciprocal space. Like we have fundamental spots, red color, and in between these, how many numbers of spots you are getting? Depending on that, if you are getting 6, means it is 7 times multiplied for the modulation. If it is just 5, then it is 6, something like that. And between distance, if it is uneven distance, then it is incommensurate, and even then commensurate. So we have done for our system also, and we have observed for the pre-Martin site also. But by the way, if you take the same sample in your lab XRD, you will never get these peaks, which I am showing the mismatch. You will get the main peak, but this mismatch, you will not able to observe in these peaks. So then you will miss your fundamental science particularly. Okay? So this is, we have shown that pre-Martin site phase is also incommensurate, but 3 times modulated. Means unit cell parameters are multiplied by 3. So basically now here I have compared. You see the 2 phase diagram. First phase diagram, the black left hand side, black side. You see there is no information about this pink which I have inserted. Okay? But right hand side, when we use the synchrotron, you can clearly see that we have observed all the changes, whatever happening in the magnetization is. Okay? So basically we observe the precursor effect using the synchrotron. Then comment on the origin of modulation or physics of the modulation. As I told, the adaptive model which is proposed in PRL 2010, that is based on the staking point. Okay? So you have the unit cell and something like this. In this case, what happened? All the atoms move, the upper part moves equal, lower part moves equal. Means the amplitude, whatever atoms are fluctuating, must be same. On the other hand, if it is soft phonon mode model or electronic origin, then you have different intensity of the atoms movement. And what we got from our result? You see, you have green balls, okay, gray balls, and this magnesium balls. All have different amplitude of modulation. This clearly says that the fundamental origin is related with the soft phonon. Now, so the next question we ask ourselves, is magnetic shape memory and large distance related with nature and physics of modulation? Because Ni2MNGA is large, and we have shown it is incommensurate, and the physics is related with the short phonon. But this is with the one system. But if it is really connected, then we must look at another system where these things are missing. So we have asked for another, we have prepared another system which doesn't show reversible phase transition. Okay? Means you cannot use for magnetic actuator application. And here, just I will show that we have applied the synchrotron technique, and this slide. So here, left hand side XRD is fitting very good. You may be happy, but if you see the atomic displacement, the right hand side figure, what you see? The red curve you see. Red curve is going, this is interatomic distance in the 4th dimension. The red curve, the down point is around 2.3 angstrom. Okay? So we have nickel, manganese, indium atoms. So the interatomic distance, if you measure, okay, it must be greater than 2.5 at least. Okay? So this 2.3 angstrom means atoms एक दूसरे में घुस गए, which is impossible in the case of normal metal. Okay? Means something is wrong in our analysis. So we have discarded it, and then we took the equal displacement of the atom. Then fitting looks same, but physics is proper. Okay? The fundamental science tells us that okay, you are doing the correct. So the same time for the students mainly is from our experience, my experience only, that you never look just if everything is fine fitting. Whatever analysis you do, it must be connected with the fundamental science, because fundamental science can never be wrong. Okay, your analysis can be wrong. Thank you. So now I will go for the pre-Martensite phase. What we have done, and again this is because of thanks to the Petra 3 data and the initiatives for that. So I will go to the Martensite transition. So the metallurgy we see, okay, it has become harder. But the first histographic model was given by the Bain, and what Bain model tells us that during the Martensite transformation, symmetry is breaking. Symmetry breaking means if you see the X-ray diffraction pattern, you must see the peak is breaking. Okay? And this distortion is called Bain distortion. Okay? So what we see, so pre-Martensite phase was observed in 1956 in gold cadmium system and then nickel titanium system. Many systems after that it has been observed. But what literature says that in the precursor phase, pre-Martensite phase, cubic symmetry is maintained. Even you get extra peaks. Okay? But this is puzzling. Okay? You get the extra peak, but cubic symmetry is maintained. Even if you see the recent articles, this computational materials in NPJ, I think I have written down. This is 2015. What it says, the spontaneous strain of pre-Martensite phase is small as compared with the transformation strain of the Martensite phase, and the pre-Martensitic phase remains quasi-cubic. So from cubic to quasi-cubic, but still they are thinking that it is cubic. Okay? Now, what is the difference between quasi-cubic? So this is what I have done. So this is for Ni2M LGA. The right hand side, these are the satellite peaks. What you see, with incommensurate, fitting better, that's fine. Okay? No issue, and it's kind of cubic like. Because the left hand side, the main reflection, you don't see any splitting. But what difference we got when we put the platinum? And platinum we put because of the reason, because earlier we have done some work on the platinum and we got theoretically the larger strain, reversible strain, all those positive things. So we prepared the sample with series. But if you compare the SC susceptibility of two samples, then one kink is observed at 235K, which we generally neglect. Okay? But if you use the synchrotron, you will not able to neglect if you do XRD synchrotron. So these are the temperature dependent pattern covering all temperatures. And what we observed, 4 important points. Above 260K, some XRD pattern, between 260 to 235, then 235 to 220, and then below 2. And we try to analyze all this. So above 260 it's fine, below also fine. Okay? But something interesting is between 235 to 220. So this is the XRD pattern. Now if you try to analyze using the cubic symmetry, a clear mismatch in the first top graph you can see. So this say, if you see it, you see a shoulder kind of thing in that XRD pattern. So we did not neglected it, and we tried to understand, and finally we tried a different models, and finally what we found, then you use the super space group model, and we found that we can fit it only if you reduce the symmetry. So this is a simple thing that it reduces the symmetry, but it answered a long awaiting question that yes, the pre-Martensite phase is a thermodynamic special phase. It's not a precursor phase. Here you have the Bain distortion. And then we saw this, and this was the phase diagram we made. It has 2 kinds of precursor effect. Then, okay, so it is somehow the last part. The question is, till now the pre-Martensite is precursor because it comes only in a narrow temperature range. Then we thought that whether we can stabilize pre-Martensite phase in wide temperature window so that we can understand its physics properly. So we prepared this system, and here you see the lower panel, the magnetization data. We have only one kink. There is no sharp drop in the magnetization, which indicated that we have the pre-Martensite phase in the But of course, behind this, there is a long history of sample preparation and all those things, that many samples we prepared and after that we got. And this is the middle panel, shows the lab XRD. We don't see any change between 300 till 13 Kelvin. That sample is cubic. But if you go to the synchrotron, you see tiny things. It tells you that you have the phase transition. And you can clearly see, actually, if you see the magnetization, below the magnetic phase transition, the magnetization is decreasing. But standard, if you follow the rule, and if you decrease the temperature, the magnetization must be increasing. It's a standard rule. But here it's decreasing, means something is happening. And what is happening? That we got from the synchrotron that there is a phase transition. And finally, I would like to conclude that using the synchrotron technique, we have answered many for the many unresolved issues from last even 60, 70 years. So I must thank the faculty.
Thanks, Sanjay, for finishing in just 27 minutes. Yes. Okay, questions?
Excuse me, sir. Sir, here. Sir, the three diffraction pattern you not showed.
Yes. So I was waiting for that. At least I wanted to see, and someone is interested. See that. So this is the crystal, the first one. The second one, what we have shown you, the incommensurate modulated crystal, and third one is famous. I have done my job. Basically, we vary this from DFT, how the field will be changing. In the phase transition, like if you get the imaginary part of this phonon, this person from phase transition, you get from DFT. Composition is of course, but theoretically you can. No, but in composition something is happening which we can take into account in the theory. The same here. In all these nickel, manganese, gallium, slight deviation change. Okay, so I will not be in between you and your lunch.
Yes, all of having it. Okay. So, Sanjay, thank you very much for this fascinating talk.
Now I thank you, Chatterjee sir, for this enlightening session, and I request Professor Sanjay Singh to present a memento to Professor Chatterjee.
I will give to him.
We will now have a lunch break and we will meet at 2:15 for the next session. Thank you everyone.
So we will wait for another 5 minutes and then we will start this.
जी सर जी सर सर कल वो आके बना के गए थे टेम्प्रोरी व्यवस्था की है सर हाँ हाँ वहाँ एक हाँ सर है सर वहाँ नल भी लगाना है सर सर वो अच्छा तो फिर बाद में आके लगाए होंगे सर कल शाम को नहीं सर हम इनका नंबर सर दे दीजिए मुझे मैं बात कर ले रहा हूँ 7860 हाँ सर बताइए
Good afternoon, everyone.
Hello.
Welcome back. It's an honor to be here with all of you today to host the post-lunch session. Myself, Aishwarya Bastia, Research Scholar, School of Mental Science and Technology, we extend you a very warm welcome to this user outreach program. Then, as we dive into the next session, we have Professor Akhilesh Kumar Singh, School of Mental Science and Technology, to chair this wonderful session. Sir, over to you.
4-3
Please have a huge round of applause.
अरविंद जी हम फोन कर रहे हैं आपको ठीक है
So thank you, Asher. So welcome you all in the afternoon session. So we have 3 speakers. Time allotted is 30 minutes for each in presentation and 10 minutes for discussion. So I will request the speakers to stick with the time. So the first speaker is Professor Somrat Acharya from School of Applied and International Sciences, Indian Association for the Cultivation of Science, Kolkata. So he will talk about in situ fabrication of non-covalent two-dimensional molecular crystals for solid state luminescence. So I request Professor Acharya to start the presentation.
Thank you, Chairperson, for your kind introduction. And I'd like to thank the organizer, particularly Konishko and Sanjay, for their invitation and to share some of my recent results on the molecular crystal. Sanjay was telling that some people are from the chemistry background. So I'd like to draw a bridge between the chemistry and physics with these molecular crystals here. Okay? So, let me start from the very fundamental things. So light. Have you seen light to work in the liquid state? Whatever light it is. If it is detector, it is pointer, it is household light. Have you ever seen the light to work in the liquid state? Anybody? No. Because light works in the solid state. But the problem is, if you want to design light with the molecules, molecules are extremely luminescent in the liquid state. But if you take them in the solid state, they lose their luminescence. So this is basically called concentration cost quenching. This implies that if you are bringing the molecules in the solid state, they will lose their luminescence. That means you cannot design light in the solid state. So this is a very detrimental phenomenon, right? On the other hand, there are some other molecules, like this hexaphenyl silyl. Look at the molecule. They have got the phenyl rings and a silyl stator here. So these phenyl rings can rotate against the silyl stator. So once you make a solution of these things, these molecules, they are non-luminescent in nature. But if you make aggregate of these molecules, they become highly luminescent in nature, right? So this is exactly the opposite phenomena of what we have seen before in case of, say, this beryllium derivative. So this pyridine derivative was highly luminescent in the solution form, but if you make the aggregate of this pyridine derivative, they lost their luminescence completely. So that is detrimental for the solid state lighting there. But this kind of molecules is suitable for the solid state lighting. So why it is happening? For this kind of pyridine molecule, these are the planar molecule, so they can form pi-pi stacking between them. So if you have the pi-pi stacking between them, there is a chance of the excimer formation. So if you have excimer formation, then you will lose their luminescence. On the other hand, because these hexaphenyl silol in solution phase, their phenyl rings are allowed to rotate in the solution phase because of the degree of freedom to rotate, there will be non-radiative pathways. But if you stop the rotation of these phenyl rings by making some kind of aggregations, then you will have the radiative pathways, and ultimately you will get high luminescence out of these molecules there. So why is this happening? Tentatively there are two reasons given, but there is no firm solid evidence that why this kind of anomalous behavior is appearing from these molecules there, right? So one is the restricted intermolecular rotation, other is the restricted intermolecular rotation. That means if you stop the vibration and rotation of the molecules, then you will be able to create the radiative pathways by stopping the non-radiative pathways there, and eventually these molecules will be luminescent. So this implies that you need to freeze the molecules. So by doing that, people have tried to put them in different kind of application. People have tried to put anti-solvent within the solution phase so that this molecule will form the aggregates. They have tried to make a small crystalline structure of these molecules. Also tried to put in the biological cells, tried to put the layered materials, tried to blend with the polymers. The ultimate target is to make the aggregates of these AIE molecules. Okay? But think about that. All these processes, what I have shown, they will not allow you to form a control state of aggregate. And if you won't form the control state of aggregate, your ultimate photophysical pathways will remain uncontrolled. So what is the need? The need is to form the controlled aggregate or making controlled molecular crystals of these molecules so that eventually you can control the luminescence pathways there, and if you can increase the luminescence in the solid state, it's a jackpot, right? So in order to form the molecular crystal, one has to take care of two parameters which are extremely important here, right? One is the crystal packing, another is the intermolecular interaction. So what is crystal packing? This is defined by the Z, V0 by V, okay? So here, Z is the number of molecules within your unit cell, V is the volume of the unit cell, both you can measure by means of crystallography there, and V0 is the volume of the molecule, which you can determine from the geometry of the molecules, right? And talking about the intermolecular forces, there are different kind of intermolecular forces, short-range interaction, which actually varies exponentially with the distance between the molecules. And then you have the long-range interaction, which varies inversely proportional between the distance of the molecules. And then you have the bond formation. What are the bond formation? You have hydrogen bond formation or halogen bond formation. Why these bonds are important? Because these are non-covalent bond. Additionally, they are imposing kind of directionality so that you can really fabricate a molecular crystals. So thinking about hydrogen bond, you can broadly categorize them in three different categories, right? So one is weak hydrogen bond, which remains below 4 kilocalorie per mole. If you think the hydrogen bonding is 0.5 kilocalorie per mole, is very weak bonding there. And then you have the intermediate hydrogen bonding, which goes 4 to 15 kilocalorie per mole. And then you have the strong hydrogen bonding there, which can run up to 40 kilocalorie per mole. This implies that you can really reach to the covalent limit there. That means you can have the strong hydrogen bonding there, which can really mimic the covalent bonding, which plays role in fabrication of the inorganic crystals. Then talking about the halogen bonding, it also can give the directionality, okay? Depending on the iodine, bromine, chlorine, or bromine, you can have also the bond energies up to the 40 kilocalorie per mole, which is pretty high here. So depending on the nature of this halogen bonding, you can broadly categorize them in two different categories. One is symmetric, where you have two bond angles are similar. That means theta 1 and theta 2 is similar here. And then asymmetric, where you have different values of theta 1 and theta 2. So if you have the symmetric hydrogen bonding, they can grow in a linear manner like that. Or they can have a situation where you have little bit of change in the angle and the crystal can grow. On the other hand, if you have theta and theta 2 are completely unequal, then you have a growth like this way, zigzag, zigzag, zigzag growth. So this implies that using this halogen bonding, you can also grow your molecular crystals there. So in a whole, what is happening there? You think about a complete molecule, which is basically called tacton, and the binder group, which is binding non-covalently, that is called synthon. So as in interaction of tacton and synthon, you will have the growth of the molecular crystals, but if you look at the reality, the shape and sizes of the molecular crystals are not really controlled. You don't have any control over the growth of the molecular crystal. You don't have the control over the shape and sizes of the molecular crystals there. Okay? So what's the need? The need is, what is the ordering of the molecules within these molecular crystals there? What is the conformation of molecules? How the molecule is sitting with this molecular crystal? Can you control the conformation so that you can have a controlled growth over the molecular crystal, right? What is the direction of the growth of the molecular crystal? What is the dimension and shape of your resultant molecular crystals? Okay, so these are the challenging points that one needs to address. So here comes our journey. We have been using a different technique. This technique is very elegant, discovered in around 1930, and both of them, Irving Landmüller and Kathleen Bloget, they got a Nobel Prize for this discovery. This is called the Landmüller technique. It's nothing that you spread the molecules at the air-water interface, and then you compress this by means of some mechanically controlled barriers so that you can bring the molecules in the closer proximity there. And if you can bring the molecule into closer proximity, then you will have a chance of the control of the conformation of the molecules, because you are spreading the molecule at the air-water interface. Okay? But the problem is, we all know that all the molecules are not compatible at the air-water interface. Only those are amphiphilic molecules, so those are very compatible at the air-water interface, right? Why? Because the polar head group will interact with the water molecules, whereas non-polar part will remain away from the water there. Okay, so this is very compatible for the amphiphilic molecules, but what molecules will show now, those are not really amphiphilic in nature, but they are hydrophobic in nature there. Okay, so these are the classes of the molecules. But why these molecules will form a layer at the air-water interface? Because of different kind of dipolar as well as hydrogen bonding interaction. Okay, those can interact with the water molecule to form this kind of dipolar or hydrogen bonding interaction there. Okay, and once you have this kind of interaction, you'll have a film of the molecules at the air-water interface, and you can lift the film on top of solid support by dipping any kind of solid substrate. Okay, and you can transfer the molecules onto the solid substrate there. So this is called Landmüller-Bloget tree. So we started our journey with a simple molecule, iridium derivative here. This is monocyclomethylated iridium derivative. We call it phenylpyridine. So it's split at the air-water interface from the chloroform solution. Okay, and we started to lift up at defined compression. That means at different surface pressure. So immediately after lifting at low surface pressure, what we have observed that we already obtained the two-dimensional molecular crystals. And the width of the molecular crystals is at around 80 nanometer, length is exceeding microns, they have got very good rectangular shape, and the thickness is only 4.8 nanometer. Then we started to compress that uniaction to see what is happening there. So see, these are the atomic force microscopic images taken at the different surface pressure there. So what we can see from these images? First it shows that we are getting larger packing density there. If you compress them, then we can get larger packing density. What else we can see? For each and every case, you have directionality is increasing with respect to the surface pressure. If you compare this figure and if you compare this figure, see this is more directional oriented. That means you can align all these two-dimensional crystals in a single dimension there. What else can you see from here? If you measure the height at each and every stage, the height remains the same at around say 4.8. This implies what? We can readily form two-dimensional molecular crystals, strictly two-dimensional molecular crystals at the air-water interface, which has got wide rectangular area as well as very small thickness of 4.8 nanometer there. Okay, so this is the beauty. So once we have fabricated these two-dimensional molecular crystals, then we started to look at the spectroscopy, what is happening there. So we first compared the solution photoluminescence spectrum. So this is the solution photoluminescence spectrum here. So this is giving very weak photoluminescence in the solution phase. Like if you measure the photoluminescence quantum yield with a measure of the degree of your photoluminescence, so it is coming to be 1% here in case of solution phase. Now if you compare with the two-dimensional molecular crystals, you can readily see a jump, enhancement in the photoluminescence quantum yield, and it can readily go up to 39%. So what happens? In solution phase, they are almost non-emissive in nature, but if you are forming two-dimensional molecular crystal, immediately they are becoming top luminescence, right? And as a result of that, you can recognize very intense green fluorescence in the solid state. What else? Then we have measured the lifetime, fluorescence lifetime. What it gives? It gives that how long the charge carriers are staying in the excited state. So in solution phase, it is giving only of the order of nanosecond, but if you make two-dimensional crystals, it is going up to order of microsecond, 1,000 times higher than the solution phase there. Okay, these are the distinction. Then we were very optimized. Okay, we have fabricated two-dimensional molecular crystals. Now we have a chance, if you deposit more number of layers, then we will be able to increase the photoluminescence for them all. So we started to deposit more number of layers. So these are the more number of layers you have. Up to 29 layers we have lifted on top of solid support. What we can see from here, if we compare with the monolayer film consisting of only one layer of two-dimensional crystals with the multiple layers, there is not a big difference in the photoluminescence quantum yield. Then we are very surprised. What is happening? Why it is not the luminescence is not enhancing upon increasing the number of layers? So this is very surprising. Then we have introduced another technique that we have correlated the photoluminescence intensity with the surface coverage obtained from the atomic force microscopic images. Okay. So what happened? If we compress, then we are increasing the surface coverage there. But if you compare the photoluminescence quantum yield with the atomic force microscopic images showing the surface coverage here, they are not following the same trend. Additionally, where the molecules are most compressed, the photoluminescence quantum is not the maximum. So this implies that the number of molecules which are remaining under the beam, they are not determining the intensity of the photoluminescence there. Rather, the conformation and packing of the molecules are playing the major role here. Okay. So then we have compared the frozen form of these molecules with the 2D crystals. Why frozen form? This is called ethanol glass. Because if you remember that people have started to see that if I freeze the rotation and vibration of these molecules, they are giving high luminescence there. So if you make the ethanol glass, automatically the rotation and vibration of the molecules will be stopped. So that was the motivation. So we have started that one. And then we have compared that with the two-dimensional crystals at room temperature. Remarkably, see the intensity of the photoluminescence is of the same order here. Okay. So this implies that usually ethanol glass or glassy form of these molecules are made at low temperature of 77 K. Fine. And two-dimensional crystals are made at room temperature. And if you are making a glassy form at 77 K, then you have a chance of the phosphorescence there. So question comes, is it a process of phosphorescence? So, but see, let us see the basic photophysical processes here. What happens? If you excite the molecules, so it goes from the ground state to the excited state. Okay, this is called the process of absorption. Then it will come down again immediately to the ground state to recombine to give you the luminescence. It is called the prompt luminescence there. But if you have the triplet state, which is situated nearby to the singlet state there, so there is a chance of the intersystem crossing from the singlet to the triplet state. So if there is a chance of the intersystem crossing, then from the triplet it can come to the ground state to give you the phosphorescence. On the other hand, if you have small singlet triplet splitting, there is a chance that it will go back again to the singlet state and come down to the ground state and recombine to give you the delayed fluorescence. The difference between the delayed fluorescence and phosphorescence is that the delayed fluorescence occurs at the same wavelength of the prompt fluorescence and phosphorescence occurs at the longer wavelength there. So this is the basic difference. But if you look and compare these photoluminescence spectra, so the peak positions appears in the same position for each and every case there, right? So this is in dialogue. Whether this is a process of delayed fluorescence, whether this is a process of phosphorescence, and we need to probe that one. Furthermore, why are we getting the strong intense luminescence from these two-dimensional crystals? That we need to answer. And why are we getting longer fluorescence lifetime from these two-dimensional crystals? All questions have to be answered now. So this is the entry where we have started doing the synchrotron there, right? And for molecular system, there are very few reports, particularly on the two-dimensional crystals, which have really used the synchrotron technique there. So this is basically a very critical experiment that you need to have similar kind of setup where you can spread the molecules at the air-water interface. Simultaneously, you can compress the molecules and measure the synchrotron measurement there. So we have done that in, of course, DESY, in Photon Factory, also in Soleil, but also DESY helped us a lot here. So we impinge the beam at the grazing incident there. So there are two ways you can collect the diffracted beam. One is in the in-plane diffraction, which is called QXY. Another is little bit of out of plane, which is out of plane diffraction. So that is called QC. So two ways you can collect the beam here. So first we have collected the beam in the in-plane condition. So all these curves are showing you the in-plane diffraction condition. What we observed, that just upon spreading, readily we can see the diffraction peaks here. Three different diffraction peaks. One is 1, 1, another is 2, 0, and another is 0, 2 there. Okay? Now we started to compress the monolayer. So what happens here, the 1, 1 peak remains the same, the peak intensity and position remains the same, while the positions of the other two peaks are remaining the same, the intensities are going down. So this implies what? That basically your crystals are aligned along 1, 1 direction, sacrificing 2, 0 and 0, 2 direction. Then we started to check the out of plane diffraction. So what happens here? You see, the 2, 0 peak intensity remains the same, while the other 2, 0, 2 and 1, 1 peak intensities are going down. So this implies that your beam is impinging on your crystals along the long axis, which is basically along the 2, 0 direction. Fine? So once you have this diffraction pattern, you can find out the thickness in situ condition at the air-water interface there. So we have found out the thickness there, and from this diffraction measurement, we can readily determine that at each and every stage, the thickness remains at around 4.8 nanometer, which magnificently tallies with the AFM thickness measurements there. Okay. So once you have the diffraction peak, now you are in a position to find out the unit cell there. So we have found the unit cell. So here it is the centered rectangular unit cell there with the space group of C2MM. And if you look at the structure of the molecules within the unit cell, you can readily find out that there is no planar interaction. The molecules are tilted. That means we don't have any pi-pi interaction there. Rather, we have only the CH-pi interactions there. Okay, so this is beauty, and only synchrotron can do it. So then we have extracted the theoretical profiles by using the Fourier transformation of the resultant lattice and counting the form factor and tally that with the in-plane diffraction, and that really gives you a very close matching with the experimentally measured data, suggesting that what unit cell we have proposed, that is actually correct. Okay. Now repetition of the unit cell and 2-0 and 0-2 direction will form the crystals there. So you can form the two-dimensional crystals there, right? Now what is the conformation of the molecules within this two-dimensional crystal? Are they tightly packed or loosely packed? Now we want to probe that one. So in order to probe that, we have taken the solid state FTIR measurement there, and if you compare that with the powder form or solution form, you can readily see the sharpness in the peak. So this sharpness in the peak readily tells you, no, my molecules are very tightly oriented within these two-dimensional crystals there. Once you know the unit cell, now you are in a much better position. You can take the theoretical help to calculate their energetic positions there. So we have done that using the same conformation of the crystals here, and you can readily find out the energetic positions of the singlet and triplet here. So this is the comparison for the monomer. Monomer means with only molecule, and now I'll go to the higher order molecules in the next slide. So if you see, first what we can observe. There are some triplet states which are located nearby to the singlet state. That means the singlet triplet splitting is very small here. So if your singlet triplet splitting is small, so there will be chance of the intersystem crossing from the singlet to the triplet. But that is not enough to go a charge carrier from the singlet to the triplet state. You need a strong spin orbit coupling between the states. So we have calculated these spin orbit couplings also. So there are few states which are really strongly coupled together. Then we have increased the molecule to find out that what happens for the higher order molecules, dimer, trimer, tetramer. So readily what we can observe, if you increase the number of the molecules, the number of singlet and triplet states are increasing. And also you have many number of states which are basically locating very nearby. That means you have now chance of more intersystem crossing from singlet to triplet. But if you look at the lowest triplet position, see for the monomer and higher order of molecules, the lowest triplet position remains at the same, it is not changing. If you are increasing the order, the energetic position of the lowest triplet is not changing at all, right? And it is locating at somewhere at around 2.67 electron volt there. So now let us see what is happening here. So we have the singlet here, and then we have the lowest triplet, and there is a energy gap of 2.67 electron volt between the lowest triplet and ground state there. So if you convert this electron volt into wavelength, this appears to be 664 nanometer, which really matches well with the luminescence peak which you are seeing here. So this really tells that whatever you are observing, that is from the triplet to singlet transition, that means it is phosphorescence, it is not electrofluorescence. Okay, this is remarkable. That phosphorescence usually people have seen at low temperature, not at room temperature. Another thing, if you count the energetic position of the lowest triplet with the lowest singlet, this appears to be 0.54 electron volt there. So this is a big gap. This implies that the charge cannot go back from the lowest triplet to the singlet state, the lowest singlet state there. This means this is basically suppressing the chance of the electrons. So again, it is supporting, it is actually room temperature phosphorescence, what we are seeing here. Now, well, these are the theoretical calculations one can ask. You can have your own molecular conformation, you can match. So we have done the experiments now. We have taken the temperature dependent photoluminescence there, starting from 20K to higher than the room temperature. Why? Because if you are increasing thermal energy to your system, so that molecule will get the energy and will have a chance to come back to the singlet state to give rise to the delayed fluorescence. But if you look at that whenever we are increasing the temperature, actually the intensity of luminescence is going down. So this implies that there is no intersystem crossing from the triplet to the singlet, right? So what is happening, that is from the triplet to the ground state of the singlet there. And also the lifetime remains in the same range. Lifetime remains in the same range there, right? So this implies that whatever we are observing, that is actually from the room temperature phosphorescence here. Now if you make the two-dimensional crystal, infinite two-dimensional crystal, and you check the density of states, again you can find out there are many number of states appearing for the infinite crystals there. This implies that those states are taking place for the luminescence, whatever you are observing. So that gives you that why the intensity of the luminescence is too high there. Now if you calculate the natural transition orbital and if you compare that, you will see that in the unoccupied states, those are more delocalized in nature. So this gives you that the chance that the charge carrier will stay longer in the excited state. This gives you that why these two-dimensional crystals are giving longer lifetime of the order of microsecond there. Okay? Now we have changed the molecule, little bit changed the molecule. We started with the phenylpyridine, then we have added this fluorine groups to have the difluorophylline there, and see what happens. Whenever we have spread the air-water interface, readily you can form a two-dimensional molecular tape. The length of the tape is exceeding micron, width is more than 250 nanometer, and thickness, if you count the thickness, is only 2.5 nanometer there. Okay? The beauty is, now if you are compressing those uniaxially, what you will see, there is a lateral fusing of these two-dimensional sheets. And once there will be lateral fusing of this two-dimensional sheet, you can make a big molecular two-dimensional sheets with large plenary area. So we have done that, right? And then we have again taken the help of the synchrotron there. We measured the diffraction in the in situ condition, and now we tally with the ex situ condition there. We have lifted those beam on top of transmission electron microscopy grid, and see this is the transmission electron microscopic images of these two-dimensional sheets there. So this is readily showing lengths over microns, width over microns, and thickness of only 2.5 nanometer there. And readily then we were able to create the diffraction pattern. This diffraction pattern is under the electron beam, not under the X-ray, right? So this is another critical experiment, and it is more than 1 year to take this one, because it is a molecular system, soft system. So this is the selected area electron diffraction pattern for these two-dimensional molecular crystals. And from this selected area electron diffraction pattern, you can extract the line profile and compare with the synchrotron GIST data there. So these, the peak position in both cases are readily matching, suggesting you that the in situ structure remains the same in the ex situ condition. Okay? So this is the beauty thing. Think about that. I have started from that point that I want to fabricate a non-covalent crystal. That means I won't have any covalent bond. So if I am claiming that, I have to quantify the non-covalent bonding there. So here we have taken the Hirschfeld analysis. So we found that the CH5 interaction is at around, say, 23%, and CHF interaction is around 9%, and rest of the hydrogen bonding interaction working in this molecular crystals there. Also now we have found the unit cell here. So this is oblique rectangular unit cells with space group P2, and again you can see that only non-covalent interactions are dominating in these two-dimensional crystals there. Again, we have checked different spectroscopic. I'm not going into the detail for the sake of the time, but you can see they are giving a very long luminescence lifetime, as well as they are giving luminescence, strong luminescence in the solid state. And more excitingly, we have taken the photoluminescence excitations with them. What it does, it tells you that whether the peaks, what you are seeing in the photoluminescence, are from same origin or not. So appearance of the peak in any different PL excitation in the same position, this suggests to you that we have got the same origin of the luminescence there. It is not from the different states, okay? This I will skip, the spin orbit coupling, etc., whatever we have. This slide I will keep. Now question comes whether I can enhance the luminescence furthermore. So we injected metal salt, heavy metal salt within the water surface, with that thought that there will be metal-metal interaction, because those molecules have the iridium. And if you have heavy metal interaction, then we can enhance the luminescence there. So you can readily see what happens. That first thing is that the thickness is increasing. You can see from here, initially we had the 2.5 nanometer, now it is increasing to more than 7 nanometer there. But more interestingly, the photoluminescence is not increasing consistently with increasing the dose of the metal salt. It is restricted at 10 to the minus 4 molar. Why it is restricted at 10 to the minus 4 molar? So for that we have taken the help of the secondary ion mass spectroscopy. So secondary ionomer spectroscopy suggests that this two-dimensional crystal can really hold or absorb only up to 10 to the power minus 4 molar, and if you increase that one, it is unable to absorb that. So because of that, the optimized condition by which you can enhance the luminescence is up to 10 to the power minus 4 molar there. Also, we have taken the thickness, and it is also matching with the whatever we are seeing from the XT to AFM measurement. It is the GIXZ measurement also is giving a thickness of 7.2 nanometer, which is very close. Now we have changed the different family of molecules. It's not a big change, it's a positional change of phenyl ring. So this is a case for the benzoquinone ring. So we spread that again at the water interface, and you can see the formation of the two-dimensional crystals. And if you are compressing that inertially, then these small crystals can align over a large area here. Okay, so this implies that this technique is very universal. It works for the different kind of molecules. Then we have changed the functional group. Now your benzene ring is here. So this is the alpha natural derivative. You can see the formation of the circular crystals. So in each and every case, you are able to form two-dimensional crystals of different shape. And now if you are compressing these crystals, they can laterally fuse to give a big crystal, big molecular crystal with large molecular area here. And this is the case for the other derivative. This is beta naphthol. Again, there is not big change in the structure, so they are forming the circular crystals here, and you can laterally fuse these crystals to form a very large area crystals there. This technique, in fact, is very versatile. So you have used this technique for different molecules. Okay. So this is for one dipeptide molecule there, diphenylalanine. So you can see there is a big challenge that usually this kind of molecules remain in the beta helix structure. And there are processes to change it into complete alpha helix structure, but there is no one-step process exists. So if you spread that at the air-water interface and if you compress that, you can readily make 100% change in the structure towards the alpha helix structure. So this gives you the morphological evidences how it happens, that at the initial stage there is a formation of thumb dome structure with small dots inside. Now if you are compressing that, you can readily see the twisted structure, twisted fibers of these molecules. So this gives you to the alpha helix structure there. Then we have some linear kind of molecule which is called pyridinacine. So pyridinacine is linear molecule. So one can form the Archimedean spiral. These are the Archimedean spiral. So see, these are the spiral here. So linear molecule can form the Archimedean spirals by means of this technique. And you can really determine the crystal structure there using the synchrotron technique. Okay. So this is the last slide that I'm showing. This is another structure which is called sexyphenyl. So here it is again very linear in structure. And look how many reflections can you see from the synchrotron measurement. 1, 2, 3, 4, 7 reflections. In lab scale, you cannot see this one. So these 7 reflection means this is very periodic in structure, right? So we can determine up to 12 layers of periodicity of these molecules here. So this is a schematic structure derived from this real experiment there. So once you have this kind of linear structure, automatically question comes that how are they polarized? Okay, so we have checked the polarization here using linear dichroism. You can see the degree of polarization is increasing with respect to ordering of these molecules here. So these are this is some applications which we used for the using this high luminescence from these two-dimensional crystals. They are making different kind of light emitting diodes of different colors. So these I'll just skip here. Okay. So in summary, what I have shown. In summary, I have shown that how to fabricate two-dimensional molecular crystals, which are pretty different from the three-dimensional regular crystals or inorganic crystals or covalent crystals. These are made out of the non-covalent interactions there, right? And if you make this kind of two-dimensional molecular crystals, you are able to get very high degree of luminescence from these two-dimensional crystals. Okay, and we showed that what are the inherent spectroscopic pathways that are really taking part for enhancing this luminescence from these two-dimensional crystals there. So I am not showing the publications this is coming, this is for the references using different sources. And I must thank the Department of Science and Technology for generous funding, and ACRB and DESY, of course, and Solen and Proton Factory, particularly DESY. Thank you very much. And wait, I cannot conclude before acknowledging my collaborator. So here I got support from Professor Shanal with the measurement with the synchrotron at different places. Of course, the students who are responsible for the measurement, spectroscopic measurements were carried out in Professor Shubigor's lab in JNC, and theoretical calculations are done by Bidisha Das and Noen Dotto from ICS. And thank you very much for your kind attention.
Thank you, Professor Acharya, for a very nice presentation and innovative experimental materials design ideas. There must be some questions.
The very first case where you were showing the pressure easily goes up. We also see that the crystals was also going down.
Down.
Decreasing. When you have almost applied very little pressure, the density was less, but the molecular crystal was much longer.
No. Actually, whatever you are seeing that one, the density was less, and then once these crystals are fabricated at the wide interface, you won't have control other than fusing them laterally above surface pressure. That's because of the scale, AFM scale. Perhaps it is not covering the entire crystal, that's why. But once they are fabricated at the lower surface pressure, just above spreading at the wide interface, you have only chance to compress them, and once you are compressing them, you have chance for the lateral fusing of these two-dimensional crystals. And once you have the lateral fusing, you have a large plane area with small thickness. So now, see, one thing is that, as I have told, that this technique was broadly used for the amphiphilic molecules. So amphiphilic molecules, what it does, it has got polar and non-polar. So there will be polar-polar interaction, non-polar interaction. As a result of there will be different kind of assemblies. But they are not prone to fuse. In order to fuse in that, you need to induce this kind of CH-AF-CH by interaction that will give you the directionality, as well as bring the molecule into more closer proximity, avoiding those polar-polar, non-polar interaction. In the protein form. It is forming in the protein form, and then after formation of these crystals, we're transferring them onto solid stuff. All will take place. So there is a way to find out this thermodynamic parameter. You have the water surface there. So you start heating that water surface at different temperature. Find out the gives free energy. Okay? So that will give you that at what condition, how the free energy is varying.
Sir, so Shoma from the, can I just?
Yeah, sure.
So why do you expect the quantum yield to go up just because you increase the number of atoms in the non-crystalline phase? I mean, like non-crystalline 2D phase.
Actually,
so, you said that you went from a smaller concentration to heavier concentration. I would expect the quantum yield to go down if at all anything, right?
No. That's the example I have shown for two different classes of molecules. One class is called ACQ, aggregation caused quenching. Another classes of molecules is called aggregation enhanced emission, AIE. So these two classes of molecules are showing two complementary observations. In one case, if you increase the concentration, the quantum yield or intensity of the luminescence is going down. In another case, if you are increasing the concentration or if you are controlling the conformation of the molecule, your luminescence is going up. So that's the
only if they talk to each other.
Yeah, sure, but I can explain a little bit. So that was the motivation to start this work. Okay. Yeah, please.
My first question is, how did you determine that how many layers are there in the molecule? How many layers are forming?
You see this card. This is synchrotron X-ray measurement. So see how many peaks you can get? 1, 2, 3, 4, 5. So these two setup. So from here you can calculate the D and correlate with the molecular length to see how many layers are there. So this is a direct measurement, right? And of course you can also have geometric measurement. You know the length of the molecule. Now you calculate the thickness from any measurement, AFM or any measurement. Now you can estimate that how many layers of molecules are there, because you know the length of the molecule, you know the total thickness of the crystal.
My second question is that you are able to find out the crystal structure, crystal parameter for your molecule by using synchrotron.
Yes.
So is there any software like OLEDs and all, or is
Yeah,
there any other method to do this?
there are some kind of softwares where you can find out, but the limitation, you know what? That the conformation of the molecule, that how the molecule is oriented there, you don't have any idea. But your measurement is giving directly information about the conformation and packing of the molecule. Right?
The last question.
Yeah, please.
How did you able to compress this molecule and convert it into a sheet?
How did I compress the molecule?
Yes, and in 2D crystal.
Okay, so you see you have a bed of water, sea of water. Now if you can have some kind of control system set by two hands and molecules are inside, so I can compress the molecules like this way. So there are hands, but it's made out of some hydrophobic material so that it don't have kind of interaction with the molecule. So you can compress very slowly, maybe 1 millimeter in 5 minutes. And you will be able to bring these molecules into closer proximity without applying much force there.
Thank you, sir. Thank you very much for nice work, sir. Sir, I have a question. Do you need any stimulation for your luminescence? Or if you use the stimulator, what is the wavelength of the stimulator? Which stimulator do you use? And regarding the application part, where we can use this hydrophobic and...
See, there are two parts. That use of the stimulator for the luminescence. First thing is that I have shown a comparison with the ethylene glass, where those molecules were kept in the glassy format 70-70. And then we compared that with our two-dimensional crystals, which were obtained at the room temperature. So they are giving at the same wavelength. There is no change in the wavelength. So stimulator means if you use different kind of wavelength excitation, the position of the luminescence is not there. That's first thing. Coming back into your second question, so far we have shown a kind of application that is in the form of the lighting, right, or different color equivalents. So actually these have got broad variety of application because of their large planetarium. So we just started this once 3-4 years back. So avenue is there.
Light emission, I think, is at very low temperature range. If it is in Kelvin range, 10, 20, 40 Kelvin, that is not at a high temperature. Even at 30, below 30 degrees, it will show the light. 30 degrees centigrade.
I mean, we have shown the luminescence from 20K to 460K.
Yes.
So that's a very broad range, right?
Sir, I have two questions. First one is, you have done it by using water, on water surface. So how you have transferred it so that you can do atom? You cannot do atom on water surface, no? So you have transferred from something. So how you did that? How what you did for that? And second is, sir, in same thing, when you compress it, you're saying two rods are coming closer to each other. Sir, if two crystals are there and they are coming close to each other, like say it's any material, so they must make some type of bonding if they want to fuse each other. If they are not bonding with each other, whenever you will remove the compression, they will again separate back. So how you are going to control that?
Very nice question. So you remember that I shown the bond energies for the hydrogen bonding as well as for the halogen bonding. So I have shown that even in some cases, it can go up to the covalent limit there, right? 40 kilocalorie per mole. It depends that how the moieties are interacting. It's not compression. The role of the compression is only to bring the moieties into closer proximity. Then they will interact. Fine. So once you have this kind of strong bonding, you have two possibilities. One is the directionality, which is basically growing the crystal. And then the stability, what you were pointing out. So that's your second question. It won't break. Once, see, you are transferring them, that is your first question I'm coming. You are transferring them on different kind of solid substrate. Still you are seeing that. The ATM has shown that one.
So that due to be the interaction with substrate also, no? You transfer it as a with the substrate. That interaction substrate.
The transfer. Yeah, so we can talk. We can talk because of time I couldn't answer your last question.
Now we request Professor Achilles Kumar Singh to present a memento to Professor Acharya. Please give a big round of applause.
So next speaker is Professor Simon Vidde from IISc Bombay. So he will talk about investigating emergent electronic phases in oxide heterostructure by hard X-ray photoemission spectroscopy. So welcome, sir.
Thank you. First of all, let me thank Kanishka and Sanjay for organizing this meeting and also inviting me. So today I'm going to talk about the use of mainly hard X-ray photoemission spectroscopy in oxide heterostructures. So our first speaker, Professor Kalavar Maiti, already talked in detail about photoemission. So I'm not going to repeat the same thing. So rather I will spend some time about how we make oxide heterostructures and how we study them. And then I will discuss about the photoemission results. So let me thank by acknowledging the work of my students who have done actually the work, and I am presenting on behalf of them. And also that very important part is funding. Funding comes from different sources, from ISC, DST, ACRD, MOE, and also from Infosys Foundation, Quantum Research Park, and also for the synchrotron based measurement, different programs of DST, like DST-DESY program, and also DST KEK program, DST vector program, and also we have done lots of experiments in advanced program source in USA, but I am not going to show those results. But we learn the physics as a whole by using many techniques. Okay. So apart from photoemission, I will also show you complementary experiments by which we learn the new physics of these systems. So basically, I will be talking about mainly perovskite, the formula oxide perovskite, the AbO3. So A is all these elements, but is marked here. B are basically the transition metals, and O is oxide. Why is it so? Because you can name of any electronic and magnetic phenomena, and you will find that there is a perovskite, starting from superconductivity, topological Hall effect, metal insulator transition, and so on. So these are all in bulk form, but in recent times, because of now advancement in thin film technology, you can make interface between these perovskites. So this is one of the schematic of interface between two perovskites, AbO3 and A dash B dash H. Now you can see that across the interface, unfortunately I cannot show my cursor here. So across the interface you can see there are mismatches in various things. The lattice parameter can be different. The symmetry, like one may be cubic, another may be orthogonal. The symmetry is different. The charge state can be different. Spins, orbitals are different. And also across the interface, the interactions are modified. As a result, in the oxide heterostructures, you get to see many emergent electronic and magnetic phenomena. And that's what we investigate in our group. So these oxide heterostructures we grow by pulse laser deposition, or which is known as PLD. So by this, basically, you have a very high energy laser, and you can grow thin film. And we use a simultaneously technique called reflection high energy electron diffraction, by which actually you can monitor the growth, that how it is progressing. So initial phase of work involved lot of optimization and characterization involving read, lab-based XRD, X-ray diffraction, X-ray reflectivity, AFM, and then we basically try to have a very sharp interface. So you can see in the right hand side, I have shown an STM image which clearly shows that there is a sharp interface between the two perovskites. So it needs a lot of work to go to that phase. So now once we have a very sharp interface, we basically measure the electronic properties. And if we see something interesting in the electronic properties, then we start applying for synchrotron beamline. Okay. So basically we use different types of synchrotrons and technique, starting from X-ray diffraction, X-ray absorption spectroscopy, resonant X-ray scattering, and hard X-ray photoemission spectroscopy. So today I will be focusing mainly on this hard X-ray photoemission spectroscopy, and which have been carried out in this P22 beamline of spectra set. Kaloda has already given a nice introduction about photoemission, so I am not just for simplicity, I am just telling that basically what we are shining a light X-ray and we are detecting the electron. So if the energy of the photon is h nu, then the information is coming say within a length of lambda 1. Now if you increase the photon energy of the photon, then basically you go deeper into the field, and you are basically proving deeper states. And that's the basically basic principle of hard X-ray photoemission spectroscopy in a couple of sentences. And now basically I will show you some results. Okay, that why we are using this technique. So all of you are familiar with ferroelectric material, like we have a switchable polarization. So there are also some kind of materials like calcium titanate, strontium titanate, potassium tantalite. They are called incipient ferroelectric. So basically they are on the verge of ferroelectricity, but they are not ferroelectric. Okay. So but these materials are highly susceptible to ferroelectricity. Like if you give some perturbation, like in terms of doping, pressure and strain, they can easily become ferroelectric. Okay. So now if you create a defect in this kind of systems, it becomes very interesting. So normally in any solid, if you create a defect, around the defect your structure changes. Yeah? And that is generally confined within one unit cell. But in this case of incipient ferroelectric, they are directly constant in very large. And as a result, you have these nanopolar regions. So you have polar regions, but which are over few units. And depending on the concentration of this nanopolar region, and also as a function of your temperature, you can actually also get ferroelectric phase. And also most important is something called dipolar glass phase. Okay. And this is again in the insulating form of the samples. So what we are trying to do in our group, like in both of the phase diagram, if we add another axis, now if you put a carriers, then how the system is going to behave. Okay. And this carrier doping we are doing in a couple of ways. One is of course chemical doping, another is interfacial doping, and another also electrostatic gating experiment. Okay. So let me start with the first with the chemical doping. So this is some of the so one is chemical doping and another is heterostructures, but there is a common theme that both of them actually shows glassy dynamics. Now generally when you talk about a metal like a copper, gold, then you have a definitive Fermi surface. That means your electron at the Fermi energy have a definitive energy. On the other hand, when you talk about a glass, like structural glass or spin glass, you have a rough energy landscape where you have a metastable state. So generally, none of your metals are actually shows glassy dynamics, okay? Because these two doesn't go with each other. But we have found out some new results, and that's what I'm going to talk about. So now, the first part is basically this glassy electrodynamics in potassium tantalite. Okay. So potassium tantalite is incipient ferroelectric. When the first part is about just about the bulk surface. Okay, we are not going to grow film yet. I will come to the film later. So now, what happens? Like if you take a potassium tantalate and if you anneal it in a reduced atmosphere, like you put in a quartz tube with titanium oil, you anneal it, it will become metal. And that's what you will see the resistance as a function of temperature. The left graph, it's a metal. And also if you measure magnetoresistance, you can see switching of the Hus oscillations. That is, you have a very high mobility electrons. Okay. And also you can calculate electron mean free path, and basically that you can from that you can find out, and it is actually basically a good metal. Now, so once we have a metallic system, we just thought, okay, let us do photoemission and see how the states near the Fermi energy looks like. So now, if you take a normal metal like gold, that's what you will see, like a here, near Fermi energy, you will have finite density of states. So similarly for this oxygen deficient potassium tantalate, this is the photoemission spectra. You can see there is some finite weight at the Fermi level that tells us metal, but you can see that around to 1.5 degree deeper, there is some very broad states, and those are actually some defect states arises because of oxygen vacancy clustering. And we have found, we have done DFT calculations from there. We know that this is the reason of these things. So from this data, actually thought of doing design some experiments. So what we did, we tried to measure that. Our idea was that we will put some light on the samples, and basically we will excite some of the electrons from the defect state to the conduction band, and we will keep measuring the resistance. What happens? So basically we are measuring photoresistance. We are measuring the change in the resistance in presence of the light, and after that we are removing the light and see how the resistance comes back. And but in the results, what we found is very much surprising things. So what we found that in the middle panel, that when you put the light, you see the resistance drops down. Okay, because you are putting some carriers into the Fermi level. But once you remove the light, you can see the resistance doesn't go back. Okay, this is the data for 1.5 hours. We have done experiment even up to 48 hours. The resistance does not come to the new level, though you have removed the light. Okay, and these dynamics, the recovery dynamics, after you turn off the light, that's actually is a behave like a glass. So there are lots of experiments that we have done. I am not going to the details. Those are not synchrotron based experiments. So from all those experiments, we know that the recovery dynamics is a glass. Okay. So basically by this, we have found out that this, even in a good metallic regime, you can find some glassy dynamics of electrons. And this was published last year in this paper. So now I will come back to the much more interface. So basically, if you grow alumina, gamma alumina on top of strontium titanate, we found that it becomes a metal. Okay, two insulator and you get a metal. But these metallic electrons also show some glassy dynamics. So that's so strontium titanate at room temperature, it is a cubic. Okay, but if you cool it at 105 Kelvin, it undergoes a ferroelectric transition, ferroglastic transition. So you have basically three domains, and there are also domain walls. And in recent times, what other groups have demonstrated, that these domain walls, they have very different types of phases. Like you have a domain liquid phase, you have a pinned phase, and you also have a quantum domain glass phase and quantum domain solid phase. So what we are interested that now, if you put some electrons in the systems, does the electron feels their domain walls and whether they become glass? Okay, that was the questions we had, and that's what we have grown this gamma alumina top of strontium titanate. Gamma alumina is a band insulator. It has a band gap more than 7 milli, and strontium titanate has a band gap of 3.2 milli. Okay, so now if you grow gamma alumina on top of strontium titanate, you can see that there is a resistance as a function of temperature, that it becomes metal. So you are getting an emergent metallic phase at the interface. Okay, so what is the origin of this metallicity? And also we have done photoemission, and Didi has written two beautiful articles on photoemission spectroscopy on this kind of system. I think he will probably talk about it a little bit. Yeah, about gamma alumina or lanthanum alumina and strontium titanate. So we followed the techniques what he has elaborated in those two papers and done these experiments. And what we found when we do photoemission, so we can see that this is basically the titanium core level. Okay, so there are two main strong features, and those are basically corresponds to titanium 4 clusters. But if you can see in the lower binding energy, you see additional weak solvers, and that weak solvers actually tells you you have electron, you have titanium with lower oxidation states. So in this case, we have to fit with a combination of another titanium 3 plus and a titanium 2 plus cases. So that means you have doped some electron into the titanium. And also what we found that if you take this substance and if you anneal it in oxygen, then it becomes an insulator. So this top graph. So that tells us that this metallicity is coming because of oxygen vacancy, because you are annealing and it is becoming insulator. And but this oxygen vacancy is created within the strontium titanate, and that's why it is metal. And from there, we have done a lot of transport measurements, and from there what we found that when this domain wall, what I was talking about for pristine strontium titanate, those are glass. Even in this case, metallic case, the electron feels that, and electrons also behaves like a glass. There are lots of experiments like RAM rate dependence, memory effect, and it also basically shows glassy dynamics. So now I will come to the another examples. here we are basically doping electron in calcium titanate. Okay. So in calcium titanate in the bulk form is another incipient ferroelectric. So if you measure dielectric constant, you can see that at low temperature, dielectric constant is actually independent of the temperature. And if you measure Raman spectroscopy, you see the Raman mode frequency that also saturates below certain temperature. Okay, and that is the temperature where it becomes the incipient ferroelectric. Okay, that's the temperature scale. So now there are theoretical prediction and also experimental results that if you grow thin film of calcium titanate, by due to epitaxial strength, it will become ferroelectric. So this is one of the examples. The right graph is basically the polarization as a function of field. You can see that you have a polarization which is also switchable. So that tells you that calcium titanate thin film is actually has become ferroelectric. In the bulk it was not, but now it has become ferroelectric. So now what we are thinking that if you dope electron into the systems, what will happen? Will the polar distortions also survive? That was our questions what we are asking. Okay. So for that we have done basically calcium titanate thin film blown under high vacuum conditions, and this is, you can see the STM image. So you can see very sharp interface between the film and the substrates without any defects. You cannot see anything. And also if you do synchrotron X-ray diffraction, you can see very beautiful film, lot of thickness fringes that testifies the high quality of the films. Okay, and from the reciprocal space map also we know that the film is epitaxial strength. Okay, so now we come to the electronic properties. That what happens to the electronic part. So you can see we have grown a set of samples by varying the growth conditions. So what we found that if you grow this film in vacuum or if you anneal in vacuum, you can see that it becomes more and more metallic. Like if you anneal it in oxygen, the S0 samples, then it is completely insulated. You will not be able to measure any measurable resistance. So S1 you can see the green curve, it has an insulating behavior. S2 you can see that it is a metallic down to 125 Kelvin and then there is after. If you even further anneal in vacuum, you can see the metallicity enhances. So basically what you are doing, you are introducing more and more oxygen vacancy into the systems. So these S2 samples, we have investigated using hard X-ray photoemission spectroscopy. So we have done this photoemission at room temperature, 300 Kelvin, and in that setup, you can go only down to 40 Kelvin. So we have done the experiments also at the 40 Kelvin. So 40 Kelvin is actually below this after. Okay. So there is a question that below the after at 125 Kelvin, whether the sample is metallic or insulating. Okay. So these are the two questions what we wanted to investigate using hard X-ray photoemission spectroscopy. So these are some experimental results that a parameter like our film thickness is of the order of 12 nanometer. Okay. And we are using a photon energy of 4.6 keV. So the inelastic mean triple, the lambda, that is a 6.2 nanometer. Okay. But you know the lambda is in the exponential term. So effectively, you are probing like around 17-18 nanometers. So basically, you are covering the entire film by choosing this photon energy. So this is again the photoemission spectra of titanium. So in this case, you can see that there is a features at lower binding energy, and you can fit it with just with the titanium 3+ features. So you have primarily titanium 4+ as expected for calcium titanate, and then you have additional titanium 3+. And you can also calculate the ratio. Okay. So in this case, the ratio of the titanium 3+ or percentage of titanium 3+ is of the order of 6.5%. Since you know the lattice constant, you know the volume, so you can also calculate that what will be the expected carrier density if you have this much of titanium 3+. And that number is actually 1 into 10 to the power 21 per centimeter cube. So we measured Hall effect, and from Hall, what you know that the carrier density is actually 1 order of magnitude lower. Okay, so that means suppose you are giving 100 electrons into the systems, but only 10 electrons are conducting. Then where are the 90 electrons where they are going? So in order to prove that, we basically investigate the states near the Fermi level. Okay, so the 0 represents the Fermi's level. So if you zoom that part, so there is a very weak feature. If you zoom it, then you can see there are some very tiny features there. Okay, and those features actually you can even consider. You can subtract a background, and then you see that there are two features. One is called Ig, is an in-gap states coming from defect, and then you have the conduction band because it's a metal. And also from the ratio of the area under these two curves, you can also get an estimate that how much electrons are conducting and how much electrons are localized. So this also matches with what we got from core level photo emission and Hall effect. So it really matches everything. Okay. And we also now done the same experiment, the valence band at room low temperature also at 40 Kelvin. You remember at 40 Kelvin there was afternoon at 125 Kelvin. So we are at 40 Kelvin in lower than that. But in this case also you can see that there are also finite states at the Fermi level, the red curve in the left graph. So you can see though there is a afternoon, but this is not a gapped system. Okay. We have done other analysis also from the transport. From that also we can tell that it is not a gap system, though there is after. So that means it still is a metal. Okay, though there is after. Now the question, what is our original question, that what happens to the polar regions? Okay, polarity. So for that we again done STM experiment in collaboration with a group in Southern University of Southern California, and also from the STM and ILS they could figure it out what is the, if there is any polarity in the systems. Okay, so these are done at room temperature. You can see there are basically some nanopolar regions at room temperature. Okay, so in the neodymium calcium titanate thin film undergoes a ferroelectric transitions at 125 Kelvin. Okay, but in this case, even at 300 Kelvin, we can see that there are some regions with polarity. Now what happens at the low temperature? We cannot do microscopy at low temperature. So for that we use another technique called second harmonic generation, which is again which tells you, which measures the degree of inversion symmetry breaking in your sample. So you can see for all of the samples what we found that there is some finite SAC even at room temperature, which is consistent with the STM measurement. But as we are lowering the temperature, you can see that there is basically this, especially after 125 Kelvin, you can see that there is an enhancement in the second harmonic generation signal. So that tells us that basically the polar distortion survives even in the metallic samples. And also you can fit all these plots by a point group MM2, which is basically a non-centrosymmetric point group. So this tells you that even in case of metallic samples, the polarity survives in the samples. Okay. So now in the second part, in the last, another example, now we are talking about like if you grow gamma alumina on top of potassium tantalate, what is going to happen? I was talking earlier, gamma alumina on top of strontium permanganate. So now in this case, what we found that it also becomes a metal. Okay. So gamma alumina is insulator, potassium tantalate is also insulator, but in this case also you can see that you find a metallic sample. So again it is a two-dimensional, or it's a emergent electron metallic systems. Now we wanted to investigate, and so these are some whole number, that what is the thickness of these metallic layers. Okay, so for that we have done photo emission in detail. So basically we have done this experiment with varying photon energy, basically by going deeper and deeper into the samples. So you can see from 2.4 keV to 5.8 keV, and these are the sink you can see in the top, the panel B. So you can see you have main titanium 5 plus feature, and then there are some additional, tantalum 5 plus feature, and there are also some tantalum 4 plus features. Okay, and we have done detailed analysis. We have also found out basically the ratio of tantalum 4 plus and 5 plus as a function of this photon energy that we are using in the experiment. And then we have fitted this graph using this formula, which basically tells you, gives you an estimate that what is the depth of this metallic layer. Okay, so as we are talking about that it is coming near the interface, but is it only at the interface or much deeper? How is it? So from this analysis, what we found that the thickness of this metallic layer is actually around 1.98 nanometer. So in the Z direction is basically within 5 unit cell the metallic layers are confined. Okay, and also the number of basically ratio of tantalum 5 plus is around 13%. So we have also done some STM experiment to verify some of these numbers, but I am not going to talk about this thing due to lack of time. So also we have done some other core levels, and we also found out what is the band gap in these systems. So say how much time? So another 5 minutes. Okay. So the next part I will talk about some recent results. What is something known as high entropy oxides? I think some of you may work on this field. Okay. So most of the high entropy oxides are insulating in nature. Okay, and it has very highly insulating, either they are basically they are gap systems. You won't find some metallic high entropy oxide. But we have some metallic high entropy oxide, and that's what I am going to talk about. So basically, you know that conventionally, when you grow a thin film, so you have various control knobs to tune the property. One is epitaxial strain, quantum confinement, interfacial doping, and many other geometrical lattice engineering and all these stuff. But in recent times, there is a new control knob in this family. And what is basically is called compositional complexity. So this started in 2015 by this seminal paper. Like now, you have multiple cations in the same crystallographic site. So you have a compositional disorder in the systems. And as a result of this compositional complexity, many new things happen in the system. Like you have local chemical inhomogeneity, you have local lattice distortion, you have a highly disorder in the spins and orbital, and as a result, you can get some new property in the systems. So keeping in these minds, we are trying to have some high entropy composition of this rare earth nickelates, ReNiO3. So ReNiO3 has some interesting phase diagram. It undergoes a metal insulator transition as a function of temperature. Okay. And now what we are doing, we are combining 5 different members of this rare earth nicolate series and to form a high entropy composition. You can understand that growing a thin film of these compounds will be extremely challenging. But we have been able to do it. We can grow very high quality film using pulse laser deposition. These are some much more growth details about the read, X-ray diffraction. This really tells you that the films are very good. And also we have done electron microscopy. It tells us that there are very sharp interface between the film and the substance. But when we did STELs, actually what we find something interesting. That though, like chemically, you can see from the H-DAC image that you have a very sharp interface. But when you look at the composition, you can see there are some nanoscale inhomogeneity in few nanometer regions. Okay. And also from angular bright field imaging, I am not going to the detail, we have also mapped what is the bond angle in different parts of the samples. Okay. And this is in this right graph, we have plotted the bond angles at different parts of the samples. You can see if it is a more yellow or more red or orange, it is like closer to 180 degree. If it is more blue, it is like 150 degree. Okay. So you can see there are patches where the angles are less distorted. So that means there are some nanoscale chemical inhomogeneous systems. So basically the situation is something like this. Like you have some parts where the distortions are much more and some parts where the distortions are much less. And the most importantly, what we found that this high entropy oxides actually undergoes a metal insulator transition. Okay. And most important, another important interesting thing is that, sorry, this cursor is not visible, so it's very inconvenient. But you can see that if you look at the metallic part of the samples, the metallic part, you can see the resistance changes, resistance increases if you actually increase the chemical disorder. So that means what is happening at the room, in this metallic phase, you have these nanoscopic insulating patches, and as a result, the results that your resistance increases. We have also measured X-ray absorption spectroscopy of these samples at room temperature, and what we see that we can try to fit these X-rays by combining a metallic part and an insulating part. Okay, it doesn't match perfectly with the metallic part, but like 10 to 20 to 30% of it are basically coming as insulated. So it really tells us that there is a nanoscopic phase separation or electronic phase separation in the nanoscale. Now what happened if you now apply compressive strain? Okay. So previously whatever I have discussed, this is on a tensile strain. Basically you are growing film, you are basically putting strain in the in-plane. Now we are growing in under compressive strain. So remember that in thin film, 1% of tensile strain is equivalent to 1 gigapascal of pressure. Okay. So if you grow this film on this substrate called SR-LaAlO4, so it has you give a compression like 2%. Okay. And now you can see that your resistance is completely metal. The resistance as a function of temperature, you can see that is completely metal. So it's a very rare example where you have a high entropy oxides which is completely metallic. And if you do a photometer valence band, also you can see there are finite density of states at the Fermi level. So then we wanted to investigate that why it is becoming metallic. Okay, what electronic structure parameter is changing when you are going into the compressive states. And for this, I will refer to DT's paper again. So DD and Sudipto, they have a paper around 30 years ago, but they tried to understand why lanthanum nickel it is metallic and neodymium nickel it is insulating at low temperature from nickel pore level spectroscopy. And what they found that when you go to the neodymium nickelate, you can see that satellite peak actually shifts, and from the cluster calculation they showed that this is related to the hybridization. So similar experiment we have done, and I will plot in the same way as we did, and we can see that it has a similar trend. That when it is metallic, basically this gap increases. So basically it tells us that covalency increases, and as a result it doesn't undergo metal to insulator transition. It remains metallic throughout the temperature. Okay, this is, and finally, so we have also done other work. You add DESY using exhausts, but today I am not going to talk. Maybe in the next DESY workshop, this is something what I am going to present. So with this, let me conclude that I have showed you several examples where we have used hard X-ray photoemission spectroscopy for understanding different electronic phases. And finally, thank you all for your kind attention.
So thank you, Professor Mehta, for a nice presentation. Questions? Yes, your presentation was nice. Regarding you have used the calcium titrate.
Yeah.
How did you convert that calcium titrate to metallic form? And again, second thing you have said that you are converting that into the ferromagnetic state.
No, ferroelectric. Okay. So calcium titrate in the bulk form is incipient ferroelectric. It doesn't become ferroelectric. So firstly, there are already literature that if you grow under tensile strain, then it will become ferroelectric. Okay, because the ferroelectric phase and paraelectric phase, they are very close in energy. With strain, basically, you can switch to the ferroelectric phase. Okay, so that means it becomes ferroelectric, and then on top of that, we are now introducing some oxygen vacancy. So oxygen vacancy basically it gives you some electron, very low concentration of electron that we are introducing in the system. It's become metallic, but till the polar distortion survives. Okay, probably if we can increase the electron concentration more and more, this will vanish. But at this stage, whatever we are doping very low amount, polar distortion is still surviving. We cannot call it a ferroelectric because it's a metal, but what we can say that the distortion is still polar.
And then whether it is possibility to make it some semiconductor material, it is also possible.
So initial phase was insulating. Now it is completely metallic. So there is one graph, and it depends on how we will define. So if you see, you can see the green curve. So that has not become metal. When you have very small amount of oxygen vacancy, you can see you have some measurable conductivity, but it is semi-conducting. In the pristine form, you will not be able to measure it, because the resistance is greater than 1 kilo ohm. Okay, so in that range, probably it's a semiconductor.
Any other question?
Yeah. No, we know from the X-rays that nickel is in 3+. If there is oxygen vacancy, then nickel will become nickel 2+. So yeah. So for this thing, we have done this thing. I have not shown those results. If we change the growth conditions, okay, you will have a lot of nickel 2+. So we have spent a lot of optimization and find out a very narrow growth window. Okay, where it really nickel stays in nickel 3+. Yeah, we have done a lot of X-rays measurements as a function of growth pressure, and we have done this exercise, and then we came to this conclusion that it is nickel is really nickel 3+.
Any other question? Yeah. So did you characterize the oxygen vacancies concentration?
Yeah. So
just to correlate the contribution
yeah. So you can see from here. So for in this case, see titanium 3+ is 6.6%. So each oxygen vacancy is giving to 2 electrons. So if you take it as a 6%, then your oxygen vacancy concentration will be 3%. Okay, because each oxygen vacancy is giving 2 electrons. So your formula will be CaTiO 2.97.
So any other characterization, just to get some idea about oxygen vacancies?
For this, no, we have not done other. Okay, from the transport and half space only we are talking about it.
So the interface character and the growth characteristics that will decide how much vacancy you are getting into. And did you characterize this polar nano regions by some visual force microscopy?
No, that we have not done. That we have not done. No, we have not done. We have from this microscope you are seeing directly, so we have not gone beyond because that is one of the more direct evidence. We can see nanopolar regions.
Okay, so thank you, Professor Vidya.
Now I request Professor Aklisma Singh to present a memento to Professor Mehta. Please give everyone a big round of applause.
So now we have the last speaker of this session, Professor Rajini Krishna from JNCSR, Bangalore. So she will talk about study of doping in quantum dots using exams as a probe. So welcome, madam.
Thank you, Shravan, for the introduction, and at the outset, let me thank Kanishka and Sanjay for inviting me here for this very interesting workshop. So today I'm going to talk to you about how to use exafs in nanomaterials, specifically nanomaterials and a few examples of those nanomaterials. So before I get started, let me just acknowledge the people involved in this work. Most of this work has been done by my students, Dr. Avijit, who is just going to join in IIT Bhilai soon, and Dr. Pradeep, Dr. Saptarshi, all of them are my ex-students. And various collaborators, as you will see in the rest of the talk, this is not just, exafs is not a tool which will stand up on its own. You need to have corroborative evidences, as Sanjay was also mentioning, that it needs to make sense. Just fitting doesn't help. So we have done a lot of other experiments and of course the funding agencies. Before I get started, I would just like to give an overview of our lab. So this is, in our lab we have been majorly working in areas of nanomaterials, electronic structure, bulk surface electronic structure, the perovskite chemistry, defects chemistry, and magnetism in quantum dots. And more recently we have actually started working on magneto-optics in the last couple of years. So with this, let me get started with exafs. Since morning, since there has been no introduction specifically about exafs, although there might be some in the later sessions, I just thought a brief overview for the students that it is a very robust technique that you can get for local environment of the central atom, and basically the ripples that are present after the immediate element edge is what characterizes the exafs, and you can see what is the nature of the surrounding atoms, and it contains critical information about bond lengths, coordination, central, etc., which we will go and see as we go along. Okay, so most often when we talk about exafs, at least people in exafs community who have been working extensively on bulk systems think about it in a very different form as compared to these nanomaterials, not from the basics perspective but from what you can achieve. So you have a wave function, a wave vector here, and you have the energy space. This is how you will get an exafs data, and if you Fourier transform it, you can get the K space, and then you do the transformation, you will get the R space. And this R space is what can, trying to figure out what is there. For example, this would be most closest to the nearest neighbor distance. So this is how exams would work, and in bulk systems, normally it has been extensively used to study local magnetic moments, spin state, origin of the color in solid solutions, impurity location, so on and so on, which I am not going to discuss here. And what allows you to do that is because you can actually fit exactly these exams to a theoretical model, and you would be able to model this structure. For example, in these cases, you can see that you can actually detect 0.01 or 0.1 difference in oxidation state. So in nanomaterials, when it comes for these things, you see that the challenges are much more. The best case scenario is this one, wherein the probable pathways are large and largely unknown. So fitting becomes irrelevant if there is no mechanistic paths possible, and you can also see that the fitting error, like this is the difference in the bond length, is as huge as 0.667, and which is, why is it happening and is it acceptable, etc., is what we are looking at. And with all this so much of a difference, can we really get some information about the exams, from the exams of nanomaterials? Because 25 years ago when I was first doing PhD, during that time people thought, okay, nothing can be obtained from nanomaterials. But over a period of time, we have seen that even from getting this information, you can actually determine quite a few things. For example, several years ago, we did work on, look at the exams to prove that there is a ferromagnetic, antiferromagnetic interaction, which we just basically showed that that there is actually a antiferromagnetic layer of FES, which was not otherwise visible. Of course, Didi will come and tell me that you can do VUV, or Pralay will tell me that, but this is a more indirect way of doing the same. So we could establish these things. So basically, exams in nanomaterials is possible, and you can get some useful information about it. So now, before I get into actually what is a difficult part, let me clear this thing and tell you what is the easy part, what is the most direct, perfect exams fits. For that, I'll take an example of mixed halide perovskites, which we did very recently. And you see that when you have a mixed halide perovskite, you have CS, PBBRCl. So the question was, is it when you have PBBRCl, is it this octahedra is getting replaced, or is it some of the octahedra is getting replaced, like you have clustering, or whether it is random, one atom here, one atom there. So what we did was we looked at various length scales at unit, one at the unit cell level, another at the octahedral level, and finally at the bond length level. So that is, this is at the final, if you are just looking at the basic fluorescence data, you see that it is perfectly changing as a function of, it's perfectly changing as a function of increasing bromine content. It makes us feel that it is a perfect alloy. But there are these problems about ion migration. It's very unstable, and also there is a phase transformation. So you can, very small energies can give rise to phase transformation. This led us to see what is basically the issue. So the first thing we did was, of course, like everyone else, we did the XRD. And when you look at the XRD, you can see here the expanded scale, that basically it is shifting systematically, and this is as a percentage of bromine concentration, how much is the peak position shifting, suggesting that it's following Vegard's law, that at a macroscopic scale, you have a perfect crystal, perfect alloy. Then we said, okay, let us look at XRD at low temperature, because most often when we are trying to look at octahedra and other cases, we had to go down to low temperature because of thermal vibration. So we wanted to make sure that there is no phase transition. So this then we went ahead and said, let us look at the exhausts. Before we get started with the exhausts, we looked at the Zanas, and therein we found that this is a very perfect fit. That is what I was talking about when I say perfect exhausts in nanomaterials. When you look at this, and if I were to expand this, you can see here that all of these has isobestic points, which means when you have isobestic points like these in exhausts, what it means is there are exactly two paths. Only two paths. If it is 3, then you won't get these isobestic points. So what we did was, okay, we have a PBCl and a PBBr. So when you have these kind of isobestic points, we went ahead and did a linear fit of this Zana spectra. And sure enough, we see that this red line here is what we got for the chlorine and bromine variation. And this black line is the stoichiometric addition of chlorine to bromine, which given the fact that it is a stoichiometric addition, it's a very good example of how much chlorine to bromine ratio we have. And this is also one of the only ways where you can find out the chlorine to bromine ratio from what is incorporated into the solid. Okay, so then we know that there is only PBCl and PBBr path. So we go ahead and do the fitting. You can see here nicely that there is it fits pretty nicely, at least the first order peak. But you can see here that these are the higher order peaks which we cannot fit in nanomaterials. This is the best case scenario that we are getting. So I have one path which is a 2.25, another one which is a 2.69, the one associated with the PBCl and the other one associated with the PBBr. So what we see is when we look at the local environment, irrespective of how much chlorine or how much bromine is there, the PBCl, there is no intermediate path length. There is either PBCl length or PBBr length. This is also same as what some earlier work by Professor Sharma and his group had shown that the bond lengths cannot vary. It is the second and the third and fourth higher order this thing that will change. So we also found the same thing, that bond length is very similar. So now where is this, at what length is this octahedra shifting, or whether it is one single octahedra or you have few chlorines and few bromines in the octahedra, and that is where the question came. And this is when we collaborated with Professor Chandrabas to do some Raman results to look at the octahedra. And in this case also we see that this is the PBCl bond and this is the PBBr octahedra. This is, when I say P0, that means I have 0% bromine. When I say P100, I have 100% bromine. So this is PBCl3, CSPBCl3, and this is CSPBR3. So we see very well defined lead halide octahedra modes, and this peak here was assigned to cesium motion, and that is a very interesting peak, as you will see from the other peaks here. You can see that when I go to P20, which is like 20% bromine, I have interest, it's closely related to P0, but it's shifted a little. And more interestingly, this peak, the cesium motion peak, is actually shifting. And when I go to P40 and P60, you see that it is very broad, and this is where we figured out that this we cannot do it at room temperature because there is a very broad peak here, and we do need to go down to lower temperature to understand what is happening there. And so Priyanka had actually, she went down to 77 Kelvin to decouple these peaks, and we see finally that the homogeneous, there is a homogeneous mixed halide variant. There is no microscopic domain, and it is very interesting to see that there is a solid solution behavior and adjusting at the local PBX and XN and X6 minus N kind of this thing. But what changes is the cesium motion. The cesium motion peak gradually changes from PBBr, cesium lead bromide, all the way up to cesium lead fluoride, very systematically. So basically this is what we proposed in the end, that there is a change, there is a tilting of these octahedra, and these octahedra can then have a bromine or a fluorine, and this hole in between, the cesium, is what changes, the size of this hole changes, and that is why the cesium motion becomes more or less easier. Okay, so basically this, with this we could solve this problem, along with examples we had to use other techniques such as XRD as well as Raman to understand this systematically. Okay, so now that I have shown you what is a very good system, let me now graduate and say what is a tougher system. Because I promised you that we would be going into doped systems. With the doped systems, the problem is a large part of the dopants are typically on the surface, so it is difficult to model. And also when they replace the host atom, it's not like all of them gets replaced, only one of them. It modifies the unit cell parameter for very small things, and refining them becomes extremely difficult. So my student Saptashi, who came up with this idea that when I am refining it, let me go through this iteration. So what he said is, I will put the ideal R, the bond length scenario for the host lattice, but the bond length of the dopant anion replaced instead of the cation-anion distance. And then I am going to use that as a starting value and obtain the lattice parameters, and then of course do it iteratively until I get a very good fit. And this is how we went along and did various models. These models are similar to the bulk with lattice substitution model, but you have a foreign unit cell in that system. He went ahead and did the iteration for all the dopants in this cadmium sulfide system. He could achieve very nicely manganese, iron, cobalt, nickel and copper. But in most cases, as you can see here, he could not fit them with one single peak. There were two peaks, and then the first peak could usually be associated with the MS path, which is basically the metal sulfide path. But the earlier peak, the one at the low R distances, this is what we assign to the Z low. We call it Z low because it is not as a particular atom that we can introduce. We just put it, these are the surface atoms which can be nitrogen, oxygen, any of the low Z elements. It is impossible to figure out what it is, but we can say that these are on the surface. So basically the relative intensity of this red peak compared to this black one, it determines how much percentage of these dopant ions are on the surface and how much of them are in the lattice. So with that said, so this is what he went ahead and did that, and he could actually get, so basically you can see that all the bond lengths of R is very similar to what he found in literature. It matched very well, and so the fitting was quite interesting. So basically with this, what I am going to now talk about, I have already talked about, the first three parts are the various other things that you can do, like crystal facet engineering, etc., and then use of exaps to determine exchange coupling, which I briefly talked about. I also briefly talked about location of the dopant position by looking at these relative intensities of these peaks. We just now discussed extensively on the structure property correlation in our so-called perfect exaps fitting. Now we will briefly discuss about two things, internal structure of these nanomaterials and the oxidation state of the dopant ions. How am I doing on time? Yeah. So chairman says I have to finish very quickly, so I will skip this part wherein where we talk about the internal dopant location, and I will just go directly to the next part, which is how do I use this? Now that I have determined a path to find out, how do I use it? So one other way of finding out how many atoms are actually on the surface is by looking at basically the magnetism. If you have a very good magnetism in these dilute doped semiconductors, that means there's a good SPD exchange interaction suggesting that it has gone inside. So this is a magnetism curve here, and you can see here that it is very, these are the various dopants for the very same ones that Saptarshi did exact analysis on, and we see that it is not dopant clustering. So how do we go about with SPD exchange interaction? So when we did look at this, and we said, what I did say is that let me take the ratio of the first shell with that of the surface atoms, and this is what we looked at, whatever part of them is on the surface, and we could really very well map the two based on the magnetism as well as the so we could normalize the areas and you could see that the diffusivity trend of these dopants within the nanocrystal match with that of the magnetism as well as the exact measurement. So basically the atoms on the surface we cannot be responsible for magnetism was very evident. The other thing that we could look at is the periodic trend. So dopant oxidation state is expected to play a very crucial role, and when we looked at atomic radius plus electronegativity, we get the ionic radius. So we see that it is very nicely falling in this one. The line is not an average. We knew the oxidation state of iron 2+ through various methods, and we also knew the oxidation state of copper through other methods. So we just drew a line through the iron and copper. And we see that this manganese is actually oscillating between 2+ and 3+, and so is cobalt and cobalt with 2+ and 3+. Nickel and nickel falls very nicely closer to the 2+ line. So we see that through exams also we did this. Since I am running out of time, I am going to hurry through this, and you can see that when you do these nice fittings, we see that basically so there is no except in the case of manganese and cobalt, there is no intermediate states, but in the case of manganese and cobalt, we could see the intermediate states, and we could actually confirm this switching upon external perturbation through specific measurements like time resolved spectroscopy, wherein we see that manganese and cobalt actually, if I were to do a fitting, since this is not really correlated to the exhaust, we can see that with nickel and copper we could fit it to one single feature. With iron, it's well known to quench it very fast, and with manganese and copper we needed two time scales to fit it, and this suggested that ultra fast capture actually goes through to Mn2+ and 3+. Okay, with this I would conclude this talk, and I believe that EXAFS is a powerful tool to look at nanomaterials, but in a new fresh light compared to that of bulk materials. Thank you.
So thank you, Professor Vishwanath, for nice presentation.
Questions? Ma'am, nice presentation. So in bulk material, what info can be obtained by EXAFS?
So in bulk material also you can get the bond length, you can get the oxidation state, you can get second nearest neighbors, if you can fit the second nearest neighbor, third nearest neighbor, because in bulk what happens is you have a very systematic crystal structure. In nanomaterials, as long as the crystal structure is systematic, but the bond size is so small that when you convert it to K-space, it becomes not very basic.
So basically we are getting local structure, right?
Yes.
Very, very local structure.
Local, it is local to that atom, but if there are many, that atom in the crystal, if they have many different structures, then you will get an average of all of that. I cannot say that manganese here and manganese there.
Yes.
If all of them have the same structure, I will get, which happens in bulk, but in nanomaterials it doesn't happen, and that's why the
And you also
I mean, you do see these peaks there, but they're not actually peaks. If I were to show you some actual conversion, Fourier transform, you can see that even noise will convert to those.
Right, obviously. So what is the solution there?
No, it's not about solution. They are not in solution. They are all in solid state. We do exerts in solid state.
Any other question?
Yes. Exams is a surface sensitive technique.
Exerts is per se not surface sensitive. I mean, it is, you can look at the bulk as well as surface. I
Yes,
would
yes.
say it's only on the surface.
What is the penetration depth of this
This
filament?
is just the KH, so I don't, I'm not very aware, but I don't think
Thank you.
Any other question? I just have a question. In perovskite halide system, did you perform ritual structure analysis to compare the bond length with your graph result?
So we did do a refill analysis just to make sure that the structure is not changing at low temperature. To compare it with exhaust, since my this thing is broadened, we did do it. I mean, bond length matched very well with the literature value, but it's also broadened because it's an nanometer.
So when you are changing the composition, you can basically determine how much
You
bond
can
length.
determine the, according to Weger's law, if you were to just calculate the average lattice parameter.
I'm using ritual structure.
Yes, using Weger's law, using you get an average lattice constant. I did using refill parameter refinement. Using that lattice constant, we will get that. But it's an average structure, not local structure.
Now I request Professor Akhilesh Kumar Singh to present a memento to Madam. Everyone please give a big round of applause. This was indeed a wonderful session, sir. Now we have a memento for you. So I request Professor Kanishka Vishwas, sir, to give a memento.
Yeah, so we had very nice session. I am sure that the participants has benefited a lot from the three presentations. I would like to add up that at our school we have created a very good diffraction facility where you can characterize the X-ray diffraction experiments from 4 Kelvin to 1500 degrees centigrade as a function of temperature, as well as for thin film measurements. So you all are welcome. If you require, you can always contact us for the characterization. So thank you. This session closes now.
Just a short announcement. Now this is the end of this session. After this we have next and final session at 4:40. So please come back here, and there is a tea outside of this hall only. You can take your refreshment there. All people can go there. Thank you. Just outside the hall the refreshment is there. Please everyone come back in time. and Technology who will chair this session. Sir, please.
Good evening, everyone. So we are going to have one special lecture in this beautiful evening. It's a special evening talk that presented by Professor D.D. Sharma, who is a professor at the India-DESY Science at Bangalore. And he is going to give a presentation on layered resolved photoelectron spectroscopy using tunable high-energy photons. So please. So total actually 45 minutes, 40 plus 5.
Thank you very much, Dr. Mishra. I start by thanking the organizers, Professor Kanishtha Biswas and Professor Sanjay Singh and others to have invited me to take part in this fantastic conference. I apologize for having come a little late. I joined in the afternoon after lunch session. I've been listening, and the wonderful work that has been going on under this program is really remarkable. And I congratulate everybody who has, from the beginning, who have made this program possible. And I'll mention a little bit about that at the end, because I think it's a unique program which has benefited a very large cross-section of Indian science and scientists, particularly youngsters, the PhD students and postdoctoral students and young scientists, and facilitated many very modern, cutting-edge experimentation and science activities. And I think it's really wonderful to know that this program is going to be further supported and will continue into the future. What I'm going to talk about today is layer resolved photoelectron spectroscopy. And I start by, of course, acknowledging the funding, very generous funding that you have had, not only under this program and many other programs which support other access to other synchrotron activities, as well as our own research program in the laboratory. Coming from Nanovision of India, Department of Science and Technology, Government of India, Council of Scientific and Industrial Research, all to being different arms of the Ministry of Science and Technology, Government of India. And I'm really very grateful that we have been having this. The parts that I'm going to talk about are the main players, because I'm going to cover many, many years. It's a development of an idea, and much of which actually has been introduced by various speakers, making my task somewhat easier so that I can skip through some of the slides, which I'll just flash through because those have been covered by other speakers, I understand. But the part that I'll be emphasizing, the main players in those parts from the Bangalore group are Shumanta Mukherjee, Banabir Pal, Devraj Chaudhary, Pulay Satra, Anshuman Nag, Aviz Hazarika. You can see that it's actually quite an old history that I'm going to talk about, because all of them are now very senior scientists and professors at various institutions. And also, of course, we have had a lot of interactions for the specific talks that are part that I'm going to talk about. There are contributions from Petra, quite majorly, and that's how it comes. And right on top, Kulgeet Drube's group in Petra, but we also did work at DST, where Mihaela Gorga's group, Uppsala, which involved Olof Karis, who is now incidentally the director of MAX4, which is a Swedish synchrotron facility, Johan Ackerman, Jobu Matsuna, and Paul O'Brien. But the work that I'm going to talk about, which is mainly driven by those people mentioned there, nothing in science stands alone. There's always some precedence, some foundational work on which further work is done. And I must acknowledge the foundational work that had happened prior to these people coming in and using synchrotron extensively in our group, and that involved Kalabaran Maiti, who introduced the idea of using photoelectron spectroscopy to separate out surface electronic structure and bulk electronic structure in the context of strongly correlated systems many years ago. I've just given a couple of representative citations there. And then Jagjit Nanda, who pioneered in our group applying the photoelectron spectroscopy in order to uncover the structure of nanoparticles, semiconducting nanoparticles, which are very complex, using laboratory X-ray photoelectron sources, and those are the couple of representative papers. Those were all using both Kalwaran's and Jagjit's work that are cited here, were using the laboratory source. It was Samir Sapra, which I think mainly started using the synchrotron radiation and using very heavily the fact that at the synchrotron radiation, you can change the photon energy at will. You can change photon energy every 1 electron volt, every 10 electron volt, or every half an electron volt, depending on what you want. And that gave a tremendous power and moment to this particular activity that I'll be talking about. But I'll not also talk about Samir's work so much, because Samir's work was mainly involved with DESI and pre-Petra regime. You can see that 2006. I don't remember when exactly Petra program started, but I think it is after 2006 or around that time. Yeah. So the plan of the talk is going to be that I'll talk about 4 different applications, and I'll jump into the applications. I'll not go deep into the science, because my purpose today is not to deal with a particular science and understand very deeply about the science, but to tell you how synchrotron radiation, the particular variety that I have chosen to talk about today, photoelectron spectroscopy, where synchrotron allows you to do photoelectron spectroscopy with different photon energies, and why that takes on a very significant meaning and a very powerful tool. In fact, I call it a microscopy. Normally a microscopy gives you a spatial resolution in the lateral dimension. But this is the only spectroscopy that gives you a sort of an idea of vertical direction resolution, and that's where layer resolution would come. And I'll explain that as I go along. So I'll apply it to 4 different contexts. The first one would be highly luminescent semiconductor nanoparticles. It's somewhat chronological, the applications that I've chosen, but also it develops one from the other. Then I'll apply it to something called a magnetic tunnel junction, and I'll tell you why that's important. And then finally, it'll connect to what Professor Middo was talking about, strontium titanate, lanthanum aluminate, and different kind of oxide heterostructures, and telling you what kind of information science or powerful insight that you can obtain by applying this particular technique. So let's get started with the first one, highly luminescent semiconductor nanoparticles. I'll not talk about both the works, and if I'm not mistaken, the first paper cited there is actually Shomkota Acharya's paper, which also had some input from this kind of activities. And the next one, Journal of Physical Chemistry of Letters, I think was driven by Kodai and Anshumar. And so let me tell you what we did. The question really was that in these early days of semiconductor nanoparticles, of course, which got the Nobel Prize recently, are brilliantly emitting things that you all know, you have seen how beautiful colors come out. But the quantum efficiency, to start with, if you took cadmium selenide, which is the normal nanocrystal that people use for this brilliant display of color across the entire visible spectrum, is only about 10%. The reason it has very low quantum efficiency is because that you have this excitation here, as you can see, and then quickly this excited electron comes down to the bottom of the conduction band, and the hole rises up to the top of the valence band, and you expect this electron to jump down to fill this hole, and giving out the photon whose energy would be equal to the band gap. But instead of doing that, a lot of these excited electrons, rather than jumping down and giving a photon of that energy, prefers to come through a cascade of defect levels available, providing gaps within the gap region. And therefore they don't emit because they couple to the phonons, they dissipate their energy to the phonon spectrum, or they emit very much in the longer wavelength that we are not interested in, because we have designed the cadmium selenide to emit in the visible range, and we want a brilliant color. So the defects are very bad for these cadmium selenide emitting particles. They kill the efficiency. And much of the defect actually comes because of this surface that you're seeing over here, because a nanocrystal is defined by a surface. And a surface defines a defect, simply because a surface means one of the coordinating atoms of the surface atom is missing. That's why it's surface. If an atom on the surface would have all the coordination, then it's not at the surface. By definition, surface atoms are those which have one atom, at least one atom, missing. And this missing gives rise to a dangling bond, and that dangling bond is the one whose energy appears within this band gap region, and that's why you have the quenching of the quantum efficiency. So synthetic chemists immediately thought of that, let's do one thing. Let's put a hard band gap material like this blue material, zinc sulfide, around cadmium selenide, and therefore what would happen is, first of all, of course, there will be still dangling bond, but those dangling bonds would be associated with zinc sulfide. zinc sulfide itself has a much larger band gap. So when I excite anywhere in this nanoparticle, that excitation will quickly come to the band gap of the inner core cadmium selenide, and that cadmium selenide doesn't have any defects because defects have been expelled to the surface on top of the zinc sulfide, and therefore, okay, it's not because I'm showing you the one I'm seeing which is in future. I'm always ahead of my time, particularly in presentations. Sorry for that. So thank you for pointing this out. Now on I should pay attention whenever I see Kanishka whispering, I should know that something's going wrong. No, you should point out. This is your time of revenge. Okay, coming back. So this is the zinc sulfide layer, and the defect levels have been pushed out. So now that the excitation electron hole is residing here, they don't see these bad guys, which are the defect states outside. So quantum efficiency goes up enormously to 50%. But it was found that if you didn't do all that, if you didn't first make the cadmium selenide, then coated it very carefully with zinc sulfide on top, but put everything into the reaction mixture and allowed it to form whatever it wants to form, and it formed, let's say, a cadmium sulfide selenide. So instead of zinc sulfide, suppose I say that I want to form a cadmium sulfide layer on top. You'll do something similar like this. It was observed that if you now actually form a cadmium sulfide selenide, we do not know what exactly happens here, but the quantum efficiency jumps up and becomes nearly unity. And the question is, what is happening there? And this is what we try to understand. And this is where TEM, X-ray diffraction, any technique that you know would fail and cannot give you the internal structure simply because it doesn't have the contrast between the sulfide and selenide to tell you whether you have a sharp core shell structure or an alloy system. Why should we think that photoelectron spectroscopy can solve that problem? I'm now going to flip forward very quickly, not talking about these because this has been somewhat talked about. You have already seen this mean free path diagram. Essentially, the idea is that I'm going to do photoelectron spectroscopy. Photoelectron spectroscopy, if I do it a fixed photon energy, whatever be the photon energy, let me choose a particular photon energy and take two different samples. One, a homogeneous alloy, and the other, which is an inhomogeneous alloy. And I'm looking at it from top. And I'm now going to shine it with photons, and if the photon energies are not very large, then what would happen is that I'm going to look only a little piece of the top part. It is not because photon cannot penetrate. Actually, photon penetrates a lot more. It is the electrons that are getting generated by absorbing the photon cannot come out from the depth because they don't have enough kinetic energy. The kinetic energy of the electron that's coming out is directly proportional to the photon energy. So if I have very low photon energy, I'm going to look at only the top layer. If I now systematically increase the photon energy, I'll see another slice. I increase it a little more, another slice. So if I do the spectrum at this level and at this level, what I'm going to see is that in the homogeneous alloy, the composition is not changing. The signal remains the same. But whereas here, I'll see a systematic change as I keep changing the photon energy, looking deeper and deeper into the material. And this change can be unraveled. For example, you can see that if I take the difference between this, the spectrum I see at this level and at this level, what I'm going to see is essentially this layer which is in between these two plain cuts that I'm showing here. So I'll see essentially yellow spectrum. If I increase the photon energy a little more, I'll see the green spectrum. If I increase a little more, I'll see the blue part of the spectrum. That's how we can find out and reconstruct what the atom looks like. And that's the application that we did. And the question is, when I change this by little photon energy, does the photoelectron spectrum changes? Does it have the sensitivity? Conceptually, it is all very nice. I change photon energy, kinetic energy changes, and I'm looking farther and farther inside the sample. If only this change is sensitive enough. And I demonstrated that with an early example with lead selenide, that tremendous changes take place. This lead selenide covered with something called topo, which has phosphorus in it. And this topo molecule could be chemisorbed on surface or physisorbed on surface. And chemisorbed and physisorbed surfaces will give rise to different phosphorus binding energies. This is the phosphorus core level, and this is the lead core level coming in the same region, and I'm doing photo emission with different photon energies. For example, it goes from, no, it's not moving even. Okay, it's not moving. Can somebody help? It's maybe escape. No, it doesn't escape also. So what you can see while it's being fixed, can you do that? I can bring the laptop. Okay. Coming here is not going to help. Imagine the plots and the photon energies were written here. It's going to be encircled like this, and you'll see that it changes from about 200 electron volt to all the way up to 1.5 electron volts. Yeah. So from 200 to 600 to 800 to 1500 electron volts. And you can see very quickly how the spectrum is changing. Why is it changing so rapidly? Remember, at the lowest photon energy, that strongest one, that means it is the outermost layer. That's the physisorb topo, the physisorb phosphorus. Now, when I increase the photon energy a little bit, this one increases at the chemisorb phosphorus. If I increase further, then I begin to see the lead, and lead has two components, this light blue and the strong blue. And when I increase it further, I see deeper inside, this strong blue becomes almost the entire. So there's a surface lead, and that's a bulk layer. So you can get the information about the physisorb topo, the chemisorb topo, the surface layer of lead, and the lead that is in the bulk of the numbers. And this is, then you can quantitatively convert this to get exact numbers of the structure, and this is what we did. Now, it only works in his hands. Whoever got it right, or it's this slide. It's got stuck, so that's right. And in the meantime, you can ask a question.
Any cross-section gets involved?
Very much. Cross-section is definitely so, but if you take the ratio, the cross-section cancels out, geometric factors cancel out. And in order to quantitatively translate, in terms of nanometers, you need the cross-section. The cross-sections for these core levels are very well calculated, simply because these are like atomic functions that can be exactly solved with great accuracy. Not exactly great accuracy, and the matrix elements are. Is it? ठीक है, इसके बाद में देखता हूँ, फिर फंसेगा तो.
नहीं, आपको पहले बात हो चुका.
Okay. So one needs to know the cross-section to convert exactly. So I'll tell you the story, we'll proceed with it. So when we apply this technique, what we found is cadmium sulfide selenide is neither a core shell structure, nor a homogeneous alloy of cadmium sulfide selenide. It's very peculiar. It had a cadmium selenide core, depending on the concentration I take, a small cadmium selenide core, then a region where selenium and sulfur ratio kept changing, going from cadmium selenide to all the way to cadmium sulfide, and then it became cadmium sulfide only. So it had a core of cadmium selenide, a graded alloy composition, where the composition kept changing, ending with a cadmium sulfide. Now the advantage, one has to understand why should that give rise to such an enhancement of the quantum efficiency. I said that it went from 50%, which was the core shell structure, it went to 85%, 90% when you have this graded alloy structure. The reason for that is rather simple to know, and he's moved. Oh, and it is also moving, that's great. I wasn't too sure. So basically what I told you is this, that you have this graded structure where the composition is continuously changing, and now I'll tell you why that should have an impact on it. The point is, when you are making this core shell structure, what we are forgetting that you cannot grow one material on top of another material just because you want to. The lattice parameters are different. If the lattice parameters are different, imagine that you have two different materials. One is shown over here with the lattice parameter 5% more than the other material's lattice parameter. And then you try to grow one on top of the other. You necessarily will have defects, interface defects, simply because the lattice parameters don't match. So the core shell structure that we were making had these interface defects. We thought that we have pushed out all the defects to the surface of the shell, but that is not true. You had these internal defects still remaining, and those were the ones that were quenching the photoluminescence efficiency. But when I have a graded structure, what I'm doing is slowly changing the lattice parameters, maintaining the lattice match all through, so that I do not have any dangling bonds. And that is the reason why this quantum efficiency goes up. And that's, in fact, we had proven it by different technique. One is here, where there's essentially time dissolved photoluminescence, but I'll not go into that because it's not connected to synchrotron. But there are techniques by which we know that indeed, when you have a graded structure, the effect of defects are much more reduced compared to partial structure. Not only that, there are other things that happens. For example, the potential, well, of a partial structure, of course, will look like this. As you can see that this part is dominated by whatever is your shell. That's a cadmium sulfide, there's a cadmium selenide, your wave functions are separate, spread that way. But when you make the core shell structure with a graded alloy in between, actually the potential looks like this. So the potential looks like a funnel that sucks in the valence band and the conduction band to the center of the nanoparticle, therefore making the electron and hole wave function overlap more strongly, so the transition probability increases and they stay away from the interface and the surface, and that's avoiding the defect level and the bad effect on the quantum efficiency. So that's basically the story. I'll now tell you about the magnetic tunnel junction. And magnetic tunnel junction is again an old work. And you know, magnetic tunnel junction, why you need to worry about, because I'm sure many of you use these hard disks to back up all your data. If you open it up, the material inside has this, in the read head, you have this magnetic tunnel junction. Oh no, that, again, magnetic tunnel junction, that's here. And the working of it is very simple, that you have a fixed layer, a ferromagnetic layer, which is aligned movement in one direction. The other one, depending on a field, can switch either this way or that way. And so, if it is this way, the two are aligned, it will be in a low resistance state. If it is pointing in the other direction, if you measure it to pass current, for the same voltage, the current will drop. That means it's in a high resistance. What is in between is an insulator, because you want the tunneling current across, and that's typically magnesium oxide. The way the best performing materials were found to be cobalt iron boron for these ferromagnetic alloys and MgO separation. And the boron was used for a purpose of growth, being easy, but one then finally annealed the system. And one wanted to know what happens when you anneal the system. This is the question that was asked, and there were lots of surprises. And I'm going to go through very quickly, tell you what the confusion was when we walked into this field. The question was, what does this boron do? The boron was originated there to make COFE amorphous, but then we anneal it to make COFE into crystalline. What happens to boron? Now, boron, one said, I'm not going to tell you what how they said it, but the summary of this particular paper, 2007, said boron diffuses into MgO. The next paper also said boron diffuses into MgO. The other paper also said boron diffuses into MgO. So where's the problem? No problem, because somebody else came along and said boron moves away from MgO, boron moves away from MgO. We love this. So depending on whatever you say, you get some support, somebody opposite, and then you are clever, you say boron doesn't do anything. Okay, so also that is possible. So all the choices were with us. Somebody might come and say there is no boron, but that I haven't come across. So the question still remains. So what was happening and why? These are not people who are, they're very serious people. They did find boron moved one way, other way, and not moving. How can that happen? Well, this was really a surprise. So what we did, we also started, we made a half device. This is the, don't worry about that part, the active part of the blue. You have this magnetic layer covered with the insulator layer. In bracket is in nanometer, what is the thickness of the material. We looked at it with different photon energy, exactly, remember, looking down into, as I increase the photon energy, I'm looking deeper into the device. This is top, on top, and as I keep increasing, I look more from the interface and then more into the bulk of this. And I see some small changes. As I'm increasing, that means looking deeper into COFB, iron oxide signal goes down, boron oxide signal goes down, which implies that essentially, if I look at that, if I take the boron oxide to boron ratio, the boron oxide, you notice, I should have pointed out, is here, and this is the clean boron signal. So you can see that that is going down as I'm increasing the photon energy. Remember, increasing photon energy, I'm looking farther in. And boron oxide intensity is going down as I'm looking inside, farther and farther. But if I'm looking at the boron oxide by magnesium, that is increasing as I'm looking at. When you put all these things together, basically what you understand, this oxide layer is forming at this interface between MgO and COF. It's on top of copper, iron, boron, that's why boron oxide by boron goes down, but it's below MgO, that's why this one is going up. And this can be converted quantitatively also, as I've said, and that quantitative definition is here, we'll not worry about that. Then we anneal this one, and as soon as you anneal, you find that the iron oxidation goes down. At the same photon energy, this oxide peak went down compared to the unannealed. So if I anneal, iron becomes cleaner, but boron becomes hugely oxidized. This is the oxide peak of boron, and this is the metallic peak of boron. As soon as I anneal, boron gets very strongly oxidized. I can analyze this and then tell you what the picture finally is. This was unannealed. We have the cobalt, iron, boron here. This is the boron oxide layer, and then MgO pure. And if I now annealed it, boron went merrily into the magnesium oxide, being oxidized all over. And there was a little layer of CFB, and this became clean of boron. So for us, boron moves into the magnesium oxide. We were happy till we took the actual device, which is this magnetic layer insulated this magnetic layer capped with tantalum, and then we did the experiment. First of all, we don't find any oxide. Before and after annealing, nothing happens. No movement of boron. You can see iron and this boron. This little oxide, it remains exactly as it was before and after. There's absolutely no movement. Is it because then three layers when I have COFEB, MgO, COFEB, boron doesn't move? And when I have two, the top, this one is not there, then it moves. So we started compiling all the results together, trying to understand this very peculiar result. And that I'll be able to explain to you as soon as my young friend comes and helps me a little more, because it's not moving. Only boron moved. The slide's not. So what you would find is happening is that all the structures, I'm going to summarize, this little tantalum that I have written over here, now it's, okay, we're having a more drastic operation. So, since you did not understand, I'm going to repeat. Revision time. So at this point, we started compiling all the results that we have seen so far. And what we found is that this is a summary of all the results that these ones, boron did not diffuse, and these diffused, and these did not. And then we saw that what actually is controlling, because there were three layers here, and boron diffused. Here three layers, boron didn't diffuse. Actually, what is making the difference is the tantalum capping on top of this layer, which is completely unacceptable and unthinkable, because this tantalum capping is several nanometers, tens of 15 nanometers away from the lower cobalt iron boron level from which boron is moving into MgO. It's something that's very, very far away, controlling what happens to boron movement. And in order to prove this, what we did was to take the two-layer device. There is only this, and put a tantalum capping on it. And then looked at it, you can see that the capped one, now annealed and unannealed look identical, with hardly any movement of the boron oxide. Slight movement is there, but much less. So it is the tantalum capping that makes all the difference whether and decides whether boron will move or not. This eventually, in fact, you can understand in terms of theory of oxidation that was given by, in 1950s by Mott and Cabrera, because Cabrera's PhD thesis work, which essentially pointed out how oxidation happens. I'll not go into the details of it. For the oxidation to happen, the oxide layer must absorb on top of the already formed oxide layer. And then the material, the metal, can diffuse through that oxide layer, but the driving force is provided by oxygen coupling to the top layer. When you have tantalum on top, the oxygen cannot come and sit down there because tantalum doesn't, it's totally inert. But if I didn't have tantalum, if I have cobalt, iron, boron, or magnesium oxide, the oxygen comes and sits there, allows the boron to be driven towards that oxygen which is sitting 10 nanometer, 20 nanometer away. In search of that, boron begins to migrate, getting itself oxidized. That's the basic story. And you can, of course, get very detailed picture of what the device looks like after annealing, before annealing from this depth and layer resolved spectroscopy. I am at about 28 minutes. Is it okay? Do interrupt me. Okay, now this is something that, since Shimant already talked about quite a bit, I'll be very as quick as I can be, because I will not get into all the introductory part, because these are extraordinarily exciting physics that is going on. And I'm going to, does it show? Can I take the laser pointer without any risk? Let me try. You know, being adventurous is always nice. Okay, so this which I'll call the S2L. There's a lot of discussion about it. Essentially, the idea is that you have one layer, strontium titanate here. There is a sample that we actually studied, cross-section TM of that. And there is about 6 layers of lanthanum aluminate on top of that. Both lanthanum aluminate and strontium titanate are band insulators. There's nothing to do with correlation here. They are very wide band gap insulators. And the funny part of it is that when you make this heterostratic, you're seeing that as soon as you have this interface seems to be high mobility metal, superconducting, magnetism shows up. So these are all D0 materials. Large band gap, completely non-magnetic materials. 2 of them, that you put them together, and they begin to show properties that are not there in any of the parent materials. And there are a lot of theory, a lot of speculation about how this comes about. And we wanted to probe it and understand. And our probing method was exactly what we said. We're going to look from top again and keep increasing the photon energy. If I come with very low photon energy, I'll see only lanthanum aluminate. And I'll keep increasing the photon energy and keep looking farther deep inside, so that I know exactly where it becomes metallic and what makes it metallic. By layer, we'll look inside and understand what makes it metallic, what character does it have. And that's how we'll look at it. First of all, I'll show you the strength of the technique. So we have lanthanum aluminate on top, strontium titanate below. So if I coming from top and if I increase the photon energy, my strontium intensity will increase, right? I'm looking down deeper inside. So relatively strontium intensity will increase, lanthanum intensity will go down. So the ratio of strontium to lanthanum or lanthanum to strontium ratio will keep going down. So here is the ratio of lanthanum to strontium. You can see how for two different samples, how the intensity keeps going down as I increase the photon energy, as it should, because I'm looking deeper inside. And you can now analyze it quantitatively, and this is where the matrix element comes in, and you take the matrix elements that are known. This really has, do I have to change the cable again? Okay, so what we'll do is that try to fit this data that is over here by assuming that this thickness is something. The lanthanum aluminate thickness is something. And then I can calculate, once I'm told what is the lanthanum aluminate thickness on top, 4 nanometers, I can calculate exactly how the lanthanum aluminate 5 nanometers, I know how it changes. 6 nanometers, I know how it changes with photon. So I'll calculate for very defined thickness of lanthanum aluminate on top and compare it with data and see if any of these plots, standard plots, can fit my experimental data so that I know what is the thickness of lanthanum aluminate. And what I want to show you first, with what accuracy this can be done, and that is given over here. So this is the accuracy with which you can see that here, this line is 2.9 nanometer if I take it. It's above all the data points. Okay, you can't see, sorry. Laser point. At the risk of again getting stuck. Okay, 2.9 nanometer, this is the theory line, which is above all the experimental point. 2.6 nanometer, it's below all the experimental points. That means I can pin down my layer thickness, LAO, as 2.75 plus minus 0.15 nanometer. And accuracy 1.5 nanometer. That's for the disbelievers. For the believers like Carlo, myself, and other practitioners of spectroscopy, actual accuracy is here, which is the bound shown over here, and it again doesn't move. Let me see the. Restart the program. Can you see that? No. It's telling me restart the program, close the program, wait for the program to respond. Which one shall I do? Huh? Yeah. Anyway, I'll finish. I will do it. Can you just try this? So, before it goes, this level, it's an accuracy of plus minus 0.5 nanometer. No, 0.05 nanometer. 0.5 angstrom. So I can determine the thickness of the LAO layer with an accuracy of essentially to an atomic dimension, better than an atomic dimension. And that tells me that I actually have absolutely flat interface without roughness, because the roughness would be of the atomic dimensions. A flat top layer of LAO. Having understood that, now what I'll do is that first I'll pick up the signal of what makes it metallic, and that already Shrimant has shown you that if we look at the titanium 2p core level, with the strontium titanium, which is titanium 4+, you also get a titanium 3+ like signal, which comes at a lower binding energy and is very, very distinct. Okay, so should I use this? Then okay. Sorry for all the interruptions, but it gives you time to mull over what I'm claiming. So that was the accuracy that I was trying to tell you about. No, is there a comment? There is some mouse moving? Yeah, there is. Now I've got it. Okay, so you can see that it's a 0.05, plus minus 0.05 nanometer accuracy that this translates. So that tells us how accurately we can determine the layer thickness. Now, here you have this titanium 3+ signal that I told you about. What we are going to do is to take the intensity under this. That tells me how many electrons are doped into the system. Of course, I don't know where they are. I'm going to normalize this one with this titanium 4+ signal and then change the photon energy to figure out how this intensity is varying. And once I do that, I find that, look, for two different samples, as I increase the photon energy, the intensity of the titanium 3+ signal is going down, which means this electron density is more near the interface. And because with higher photon energy, I'm looking farther and farther down. Strontium titanate doesn't have any titanium d electrons. So when I'm seeing more strontium titanate, the intensity is going down because titanium 4+ is not giving me any signal. But the part that is near the interface is possibly has been this particular electrons. Both of them go that way. Now I start to model it, and I say, okay, let me take one kind of distribution, because the most dominant hypothesis was that there is an electron layer right at the interface, atomic layer thing. It's a two-dimensional electron gas that forms. So if you take that assumption and try to fit, and then the fitting doesn't work. You can see this is the red is the experiment, and the best fit that you can get with any amount of electron tied to the interface is the black curve, which says that the electron at the interface is no way ever going to explain what I'm saying. You say, okay, let it not get tied to the interface, put it anywhere, and give it any width, a constant electron density distribution of any arbitrary width at arbitrary depth from the interface. Can I fit that? The best fit is shown over in this plot. That also doesn't fit, which means taking one single kind of electron distribution, I cannot fit it. Then you say, okay, allow for two different distribution. And the two different distribution immediately begins to fit it much better. You can see the dashed line is the calculated one, and those are the experimental data. And the electron distribution is exactly, so what I'm showing over here is gray part is lanthanum aluminate, and this is the semi-infinite strontium titanate block. You can see there's a high density of electron gas right at the interface, as has been hypothesized, but there is also a low electron density all through the strontium titanate, and only when you take both of them do you get this description correctly. And it is true for all the samples that we look at. And then the question is, where is it coming from? What is the origin of this electron distribution? And that immediately you start asking the question, and that question was asked in Srimanto's talk also, what are the oxygen vacancies doing? It turns out that in photoelectron spectroscopy, you can also see the signature of the vacancy. You would ask, how can you see a vacancy? How can you see what is not there? What you actually see is not what is not there, but its influence on those which are there around it. So the oxygen atoms which are near another oxygen vacancy has a slightly different binding energy, and that signal you can pick up, and you can analyze that signal to figure out how this vacancy distribution is. And it turns out, and that is what is shown over here, I'll only tell you the result, that there is always vacancy on top of the lanthanum aluminate, and there's a vacancy that's distributed throughout strontium titanate. And if you look at the quantitatively, it turns out that they're very similar because each vacancy of oxygen will donate 2 electrons. So 0.14 vacancy will give me about 0.3 electrons. And this number that you're seeing here is very close to, corresponds to 3 electrons per vacancy being donated from here into this place. Similarly, the vacancies here, 0.01 vacancy, will give you about 0.02 electrons per unit cell, and this independent measure is 0.06. Given the fact these are very small numbers, they're in the same ballpark. For the other sample, it matches even better, telling you that it's the oxygen vacancy that drives the physics of it, but it has something to do with the dominant hypothesis that I mentioned, which is called some kind of catastrophe. It's a polar catastrophic model, but I'll not go into the detail of that. I'll just take 2 minutes. Is that okay? So to tell you, so basically in this case what happens is that you have these vacancies here that donate electrons to the interface, and there are vacancies throughout strontium titanate which account for this distribution of electrons throughout. Then since I promised to talk about very quickly, for this last one, which is still to be published, because I didn't want you to see only the papers that are published some years ago. There's still unpublished result. And this talks about strontium titanate and lanthanum titanate. I mean, you may wonder, taking out aluminium and putting titanium, why should make any difference? It makes a fundamental difference because strontium titanate, a lanthanum aluminate is a band insulator, whereas lanthanum titanate, titanium is 3+, it has 1 d electron. It's an insulator, but its insulating nature is because of strong electron correlation. I'll not go into the details of it, it's a completely different physics, and one wanted to understand what happens when you have a Mott insulator, meaning correlation-driven insulator, and a band insulator on top of each other, and compare it with the band insulator, because this is driven by Barabir Pal, and these are the other people involved in it, and this is the group that are involved, and this is again from Petra. So theoretically, there are many different and conflicting reports. That's the motivation, and that is what we wanted to look at. This is from Andy Millis's group that says it should have electronic structures. These are electronic structures. I'm sorry that I'm not explaining, but I'll come back to this picture later. That electronic structure, this is strontium titanate here. You can see this is the conduction band of strontium titanate. This is the chemical potential. Almost entirely it is above, that means it's D0. As you come to the interface layer, which is here, and this lanthanum titanate is a Mott insulator. This is the lower Hubbard band, this is upper Hubbard band with a very small coherent peak. As you approach from this side and that side, this peak remains where it was, only the relative intensity is changed, and then it dopes strontium titanate to some extent, this particular picture. But another picture, for example, this one, has a very different behavior. You can see here, things are moving. Here, they didn't move at all. They remained exactly in their position. Whereas here, the lower Hubbard band is continuously moving. And so they're completely contradictory claims, and we wanted to figure out which is the right one. And I'll just show you the results. Again, these are very hard experiments, because what we are looking at is the state there. You see nothing there. But when there is nothing, that's a place that, very crazy spectroscopists begin to look at, if you have dedicated students, very motivated students, then they find that the signal is actually like this as a function of photon energy, so that you know exactly what is going on. And final solution I'll give you straight away. Basically, this spectral feature can be separated into what you call the coherent part and incoherent part, the two features with which the theoretical predictions are in conflict with each other. We extract their intensities and compare. So this is the theory that we believe works best, where the incoherent part of the lower Hubbard band remains exactly at its place, its intensity goes down, and the counterpart of that from experiment is here. This huge inside lanthanum titanate, huge incoherent part whose intensity keeps going down. There is the coherent part whose intensity goes up to the interface, and then begins to go down very rapidly, exactly as you find here. That is within the occupied part, it vanishes. So this is the theory that captures the description properly. With that, let me end my talk. Thank you for your attention, but also thank you to the Petra program, and this is where I think DST has played a very important role, and the early players like Milan, and it's a pity that he is not here, I'm really missing him here, Ajay Sood, Professor Sienna Rao, who was really the mentor all through of this program and many other programs, and many secretaries of DST and many officers of DST, including Dr. Mohanty, Dr. Poonam, who have nurtured this program all through, and also those who are keeping it running, that includes Kanishka and Jayachandra, Kulkarni's tutelage, and I think it's been a wonderful journey, and I hope this journey continues for the younger generations forever. Thank you very much.
The third part was very inspiring talk and was always pleasure to listen. So this is open for quick question and answer.
Hey, go ahead.
Thank you one more time. So I have two questions. One question is in general when you do measurements, you see charging effects, and if you see charging effects, can we get rid of it?
So I have to give specific answer because it's a very specific question. For the nanocrystals, you can see charging effect, but there's a way of getting over it. What you do is to mix it with graphite or graphite powder. And if you mix it well, it's a very thin layer and the graphite has very low cross section and doesn't interfere, and you can get good signal reasonably. You have to really play with the proportion. For the magnetic tunnel junction, MTJ, there is no charging because it's a metallic sample. It's about MTO layer is there, but it's a few nanometers that it does. When you come to NaOH2, etc., it's a LAO that can, but you have this conducting layer, and that shorts out, it doesn't. But you can have problems. One thing actually, it turns out that the problem is much less than you would anticipate. The reason being that, particularly hack space, if you're doing, the way you do is to illuminate the whole surface for a technical reason, to maximize the intensity. But what it does is that makes the whole surface conducting by photoconductivity. Because the photoemission process creates so much of Auger decay, so many holes get generated, that your surface becomes partially conducting. And that neutralizes, and this is something that is often not appreciated enough, that what actually is giving me a steady state spectrum in an insulator, why can I do if without charging neutralization, I can still do photoelectron spectroscopy. So that helps, but you can have charging, you have to be careful about it. You've noticed that none of this, we depended on the binding energy per se, which gets shifted. Intensities don't get so much messed up unless the charging is very high. So these studies are somewhat protected against them. Yeah. Both are happening. So the oxidation, see, you cannot have boron diffusing into MgO and becoming boron oxide reducing magnesium. That's not going to happen. The fact that boron gets oxidized in the MgO layer is because also oxygen ions are coming in. And the tantalum stops that. That's why boron is, because it was a puzzle. I mean, something that's 20 nanometers away, and your atomic size is so small, how the hell does boron know that there's going to be oxygen or not? So it's really driven by the chemical potential of having an oxygen on top. We didn't anneal those. Titanium one was not annealed. Those are different units, different samples right there. In that case, let me go there. Are you talking about this one? Afterwards? Because this is the first time I showed you titanium spectrum. Yeah, I'm just moving down. After this, I didn't show you any titanium spectrum. I showed you the analyzed results. And I flipped through too fast here for you to know what I was doing. And I didn't show any core level spectrum here because I was focusing on only the valence band. But if you remember something core level spectrum, that would be from before. And let me go back, and that's empty jam. There I did anything. So your question might be actually related to not titanium, but to the iron. Yeah, this one, or do you want before? Okay, sure. There was another that I showed you. I think the one that this or even before. Here I showed you the first set. This is without annealing. This is only with photon energy changing, trying to understand where the boron oxide is forming. The relative change tells me if I'm increasing the photon energy when I'm looking deeper down, the oxide peaks are decreasing, which means that basically it was forming a boron oxide layer between the MgO and the COFeB. My perceived structure is COFeB, sharp interface MgO. What this result is saying, it's not sharp MgO, there's a layer of boron oxide in between MgO and that. That is the thing that comes about, and that is, here you can see that structure, a 0.9 nanometer of cobalt iron boron oxidized layer in between MgO and COFeB. This is the starting sample without annealing. Then if I anneal, then I see the changes shown over here. And then I can, here I am showing you the changes that happens on annealing, and the annealed spectrum, the change in photon energy is shown here. And this one I then analyze this one to give you the structure of what happens after annealing, which is this. There you can see that this boron oxide is in the same layer as MgO, totally oxidized. And then if I put a tantalum layer on top here, it completely stops the boron from moving towards this side. It otherwise keeps moving this side because it wants to marry the oxygen that is out there. That's the driving force.
Okay, so let's thanks.
When you are dealing with this LAOST, the top layer is only what few units and like
6 units and 4 units, and we have done experiments with the 2.
You also do show the fitting any quantum confinement issues?
Quantum confinement issues are very much there. Basically, the electron density, that's for the core levels not. I mean, that's any quantum confined because everything is atomic dimension. The wave function doesn't exist. But the electron gas is 2-dimensional, and that has many interesting consequences of that. So that the fact that you have a 2-dimensional electron gas is a question of quantum confinement in the perpendicular direction, and that comes from the fact that the LAO layer is imposing a polar field to narrow it down there, which eventually translates into not a polar field that gets compensated by the oxygen vacancy, but the oxygen vacancy has an electrostatic potential then, which then confines this the doped charge in the 2-dimensional layer. So it's a 2-dimensional quantum confined electron gas.
The other question is, you do this depth profiling by varying the photon energy. You recall your own work earlier was 4 levels, screening effect can shift the 4 levels, influence, shoulder formation, right? So you don't see any such things?
Yes, you do. In fact, then I have to go back even further into history. And this started actually with my PhD work. We were looking at metal oxidation, and you would get metal oxide, just like boron oxide and boron you saw, and that could be converted into a thickness of the oxide layer. And then we were studying how the oxide layer thickness changes. It was in spirit, it was very similar, but we didn't have tunable energy. And when valence fluctuation were being studied, and I was involved in the late 80s, early 90s, it was understood that the screening effect near the surface is very, very different. And this is also, those were rare earth alloys, etc., which then Carlo looked at in the context of metal insulator transition and found the screening effects are very, very different near the surface. That's why the electronic structure near the surface and the electronic structure in the bulk were very different. And so we had to separate out, and we could say that what the electronic structure of the surface looks like and what the bulk looks like separately. So the screening effects do change quite a bit. Core levels, there can be some hypercohesion where the changes would be, but core level is a little more gross effect because you have a very large energy associated with it, which sort of tends to homogenize. But if you look at the valence band, then these effects show up much more subtly and much more strongly, but the effect is subtler. It's a revenge time. I asked him a question in 1998, and he has kept it in his heart. He's getting back at me now. But maybe you should use the mic because so that others can hear. It certainly does. Why do you think they put tantalum? This is from real device physicists, not from us. This is part of device, people who actually make those MTG junctions and those who transfer the technology to the device companies. Stuart Parkin and people of that kind are involved in this work. And they always prefer tantalum, and now they know why. Yeah, also. Copper will not help because it will oxidize very easily and will become a source of incipient oxygen, and so it will not. So you need molybdenum, tantalum, highly refractory, both of them. You also need to anneal them and be very oxygen resistant. So that's the reason tantalum is preferred.
Tantalum tube, the many processes can be used for many reactions.
Yes, exactly. Tantalum seal tube reactions. Some molybdenum also. Molybdenum and tantalum are the good refractory metals that can withstand high temperature and doesn't oxidize, which means at room temperature it's extremely resistant.
I was thinking about apart from those aspects, if there is an electrostatic effect or spin-orbit coupling or something.
No, tantalum and these, no, certainly not spin-orbit coupling physics will not come in this because it's too far away from the activity in this particular case. Yeah.
Okay,
They also diffuse very easily.
Second one is in the last example that STO, LTO. So there you have seen this coherent and incoherent features. So how the distribution changes if you go away from the interface?
That is what I showed. I went too fast. Basically, as you go deeper, slowly it recovers the LTO picture of a very large incoherent feature, very weak coherent feature. And as within the LTO layer, you are coming closer to the STO, but the layer result, the intensity of the incoherent feature goes down and coherent feature goes up. Though you are looking at an LTO layer, but by the virtue of coming close to STO, it becomes weaker, the coherent part.
Some kind of a doping effect?
You can try to think of it that way because what you also see electrons leaking onto the STO side, that means you're getting the LTO more hole doped, and that drives it to be more conducting, reducing the incoherent feature. So that way you can think about it.
Okay, so let's try to take it one more time, and I think.
Thank you. Thank you.
Okay, now I request Professor Shravan Kumar Mishra sir to give Professor D.D. Sharma a token of love and affection. Please give a huge round of applause. Yes, sir. Indeed, it was an insightful session by you. So, I request Professor Kanisk Vishwas sir to give you a momentum. Thank you. So, this is the ending of the session, today's session. So, we will meet here for the today's dinner at 7 p.m. Thank you. Thank you all. In the dinner hall, downstairs. Thank you.